Have you ever wondered why, amid the relentless pace of the modern world, people continue to seek comfort in leaves, blossoms, roots, and the gentle fragrance of nature to soothe their souls? Perhaps, long before modern medicine came into existence, medicinal plants were more than remedies for the body. They were quiet companions, walking beside those who longed for peace. Carl Gustav Jung believed that beneath each person's conscious mind lies a deeper realm, where ancient symbols continue to exist silently within the collective unconscious. And it is remarkable that forests, ancient trees, and even the smallest herbs have appeared throughout myths, legends, and human dreams for thousands of years, gently reminding us that nature has always carried within it the power to heal both body and spirit. Tonight, we will set out on a slow and peaceful journey, where every story about medicinal plants not only reveals fascinating discoveries made by science, but also opens the door to gentle reflections on the profound connection between humanity and the natural world. You will encounter plants that have accompanied human civilization since its earliest beginnings. Discover why the fragrance of a single leaf can calm the mind, why so many cultures believe that forests preserve the memory of the earth, and how these seemingly simple wonders reflect the deeper layers of the human soul that Jung so thoughtfully described. This is not a journey in search of miracles, but an opportunity to listen to quiet stories, where science and symbolism meet in the stillness of the night. Welcome to Stories for Sleep, where every night becomes a gentle journey into the worlds of psychology, philosophy, nature, and the enduring mysteries of being human. If you enjoy slow-paced stories filled with depth that help your mind unwind after a long day, we invite you to take a quiet moment to subscribe and turn on notifications. Each new video is meant to be a gentle companion, guiding you a little closer to inner peace and to inspiring new ways of seeing life. Now, make yourself as comfortable as you can. Adjust your pillow. Take one slow, gentle breath in. Let your shoulders soften, and allow your eyes to grow a little heavier as the night quietly embraces the world beyond your window. We will step together into the ancient garden of medicinal plants, a place where every leaf, every blossom, and every delicate fragrance carries a story that nature has carefully preserved through countless generations. And perhaps, somewhere among those stories, you may discover a small piece that has been quietly waiting for you all along, hidden within the garden of your own soul. The hidden nature of reality. Perhaps one of the strangest aspects of physics is not found among distant galaxies or enormous black holes, but in the very way we perceive reality itself. Every day, we open our eyes and naturally believe that the world before us is solid, clear, and entirely understandable. A table is simply a table. A wall is simply a wall. The space between them appears completely empty. Time quietly flows forward, the same for everyone. Light seems to be nothing more than the thing that allows us to see. Yet the deeper we journey into the world of modern physics, the more these seemingly obvious truths begin to dissolve like morning mist beneath the first light of dawn. Carl Gustav Jung once wrote that the greatest mystery is not what exists out there in the universe, but the limits of the human mind in perceiving the world. He believed that consciousness is only a small island floating upon the vast ocean of the unconscious. In many ways, science appears to be telling a remarkably similar story. What our senses reveal is merely the surface of a reality that runs far deeper, a realm where everything follows principles profoundly different from ordinary human intuition. Tonight, as you lie quietly beneath your warm blanket, imagine gently drifting farther and farther away from the familiar room around you, far beyond your city, far beyond the earth, far beyond even the Milky Way. Then, from that quiet distance, look upon the entire universe as an endless expanse of stillness. At first glance, that immense space appears completely empty, but physics tells us that this, too, is an illusion. For many centuries, people believed that a vacuum was a place where absolutely nothing existed. No matter, no light, no sound, no energy. A perfect emptiness. It seemed like a perfectly reasonable idea. If all the air were removed from a glass container, it would appear that nothing remained inside. Yet when quantum mechanics emerged in the 20th century, that picture began to change in a way that was almost impossible to imagine. Physicists discovered that even a vacuum is never truly silent. What we call empty space is, in reality, always filled with invisible quantum fields. You might imagine them as a vast ocean stretching throughout the entire universe. Every fundamental particle we know, whether an electron, a photon, or a quark, corresponds to its own unique quantum field. What is truly remarkable is that these fields are never completely still. Even when no particles are present, they continue to fluctuate ever so slightly. Those fluctuations are so incredibly small that none of our senses can detect them. Yet the equations of physics predicted their existence long before experiments were able to confirm them. This is what scientists call the quantum vacuum, an emptiness that is never truly empty. If this feels a little difficult to picture, don't worry. Even some of history's greatest physicists admitted that ordinary intuition can scarcely keep pace with the quantum world. Imagine the surface of a lake in the quiet hours before sunrise. At first glance, the water appears perfectly smooth, like polished glass. But if you look closely, tiny ripples continually emerge and quietly disappear. The quantum vacuum is much like that. At scales smaller than the atom itself, absolute stillness seems not to exist. From these unimaginably tiny fluctuations, physics leads us to an even stranger idea: the existence of virtual particles. The name can be a little misleading, as though these particles were somehow unreal. In truth, the word virtual does not mean imaginary. It simply describes quantum states that exist for such extraordinarily brief moments that they cannot be observed as ordinary particles. According to quantum mechanics, pairs of particles and antiparticles can briefly emerge from fluctuations within quantum fields before almost immediately disappearing once again. This process unfolds continuously throughout the universe, right where you are resting at this very moment. Within the vast distance between the Earth and the Moon, even in the seemingly empty space that stretches between distant galaxies. This is not because matter is created from nothing in the ordinary sense, but because, at the quantum scale, energy and fields exist according to laws far more subtle than anything we experience in everyday life. By now, reality may begin to feel a little softer than it once seemed. There are movements unfolding that our eyes will never witness. There are transformations taking place every moment that our conscious minds have never perceived. It calls to mind one of Jung's most beautiful reflections. He believed that most of what shapes a human life unfolds beneath the surface of consciousness, like an underground river quietly guiding our thoughts and emotions. Science neither confirms nor denies that perspective. Yet, it is fascinating that both depth psychology and modern physics gently remind us of the same possibility. What we can see may never be the whole story. If the vacuum is not truly empty, then perhaps time is not nearly as simple as the quiet ticking of the clock hanging on the wall each night. For most of human history, we believed that time flowed like a steady river. 1 minute for you was 1 minute for me. An hour on a mountaintop was exactly the same as an hour at sea level. Then Albert Einstein transformed that entire understanding. According to the theory of relativity, time is not a single universal clock shared by everyone. It is far more flexible. If two people experience different conditions of speed or gravity, time itself passes differently for each of them. This is not merely a metaphor. It is a phenomenon measured with extraordinarily precise atomic clocks. Every day, GPS satellites orbiting the Earth must account for the effects predicted by relativity. Without these corrections, positioning errors would accumulate rapidly, and before long, locations could be off by several kilometers. That means each time you open the map on your phone, you are quietly relying on one of the strangest discoveries physics has ever made. Time truly does not pass at the same rate everywhere. Gravity also has the power to slow the passage of time. It sounds almost like science fiction, yet this has been confirmed through careful experimentation. Closer to objects with stronger gravity, clocks tick ever so slightly, more slowly than clocks located where gravity is weaker. Here on Earth's surface, the effect is incredibly small. We cannot notice it. But near unimaginably dense objects, such as neutron stars or black holes, the difference becomes extraordinary. If one person remained close to a black hole while another stayed far away, the passage of time they each experienced could be dramatically different by the time they met again. For one, only a few hours might have passed. For the other, many years could have slipped by. It is a remarkable thought. It reminds us that even one of life's most certain ideas, time itself, is not nearly as unchanging as we once believed. Perhaps no phenomenon reveals the strange beauty of nature more clearly than light. For centuries, scientists debated what light truly is. Is it a wave, or is it made of tiny particles? In the end, nature's answer turned out to be both. In many experiments, light behaves like a wave spreading gracefully through space. Yet under different conditions, it appears as individual photons, behaving like particles. One of the most famous demonstrations of this mystery is the double-slit experiment. The hidden nature of reality continued. When photons are fired through two narrow slits, the pattern they create is not what we would expect from tiny marble-like particles. Instead, they produce the distinctive interference pattern of a wave. Even more astonishing to physicists is that this pattern gradually emerges even when photons are released one at a time, one individual particle after another, over countless repetitions. The quantum world seems unwilling to follow the intuitions that the human brain evolved to understand. Perhaps that is also a gentle reminder. Not every mystery needs to be conquered immediately. Sometimes, simply accepting that the universe is far greater than our imagination can fully embrace is, in itself, a quiet form of peace. And eventually, we arrive at a truth that causes many people to pause for a few thoughtful moments the first time they hear it. The pillow supporting your head, the bed upon which you are resting, even your own body. Almost all of it is empty space. An atom consists of an incredibly tiny nucleus at its center, while its electrons exist within regions of probability surrounding it. If the nucleus were enlarged to the size of a single pea placed at the center of a football stadium, nearly everything else would be empty space. Then why does everything feel so solid? The answer lies in the electromagnetic force. The electrons within the atoms of your hand cannot simply overlap with the electrons inside your pillow in the ordinary way. It is the electromagnetic interaction between these particles that creates the sensation we experience as solidity. In other words, what you feel is not because atoms are pressed tightly together like solid little spheres, but because the fundamental forces of nature are quietly preventing them from passing through one another. It is a beautiful place to pause during the first part of our journey tonight. For the deeper we explore the nature of reality, the more we discover that the things which appear simplest often contain the greatest wonders. And perhaps, just like the material world, the human soul is far more spacious than anything we can observe upon its surface. When we accept that not every mystery must be solved all at once, we may gently smile, softly close our eyes, and allow that quiet curiosity to guide us a little closer toward peaceful sleep. If the previous part of our journey revealed that empty space is not truly empty, that time does not pass at the same rate everywhere, and that matter is not nearly as solid as it appears, then what comes next will carry us into places even stranger still. We will leave behind the familiar world of Earth and lift our gaze toward the most extreme objects in the cosmos, where the laws of nature are pushed to their very limits. Carl Gustav Jung believed that human beings are naturally drawn toward things that lie beyond their control, not because they make us feel insignificant, but because their vastness reminds us that life contains many more layers of meaning than the ordinary eye can perceive. Perhaps that is why, whenever we look up into the night sky, we often feel both peaceful and wonderfully humble. There are stars in the universe that no longer shine in the way they once did. Having lived through nearly the entirety of their lives, they have consumed almost all of the nuclear fuel within their cores. Once they no longer possess enough energy to resist their own immense gravity, they begin to collapse inward. Yet what appears to be an ending becomes the birth of one of the strangest objects the universe has ever created: a neutron star. If our sun were compared to a gigantic sphere more than 1 million kilometers across, a neutron star would typically measure only about 20 kilometers in diameter, small enough to fit comfortably within the boundaries of a large city. Yet, inside that remarkably modest size lies a mass roughly equal to 1 or even 2 suns. Imagine holding a tiny spoon and somehow scooping up just a small amount of material from the surface of a neutron star. That spoon would no longer feel light. Its tiny contents could weigh billions of tons here on Earth. The number is so enormous that it almost escapes imagination, not because the material itself has become magical, but because the atoms inside a neutron star have been compressed to almost unimaginable extremes. Electrons and protons no longer exist separately as they do in ordinary matter. Under immense pressure, they combine to form neutrons, transforming the entire star into an enormous sphere, composed almost entirely of these particles. What makes this even more fascinating is that the same quantum laws we explored earlier now become the very reason the neutron star does not continue collapsing forever. A quantum effect, known as neutron degeneracy pressure, helps resist the pull of gravity, allowing the star to exist in a delicate balance. Once again, the universe quietly reminds us that the smallest things sometimes determine the fate of the greatest ones. If neutron stars astonish us because of their extraordinary density, light surprises us with a limit that appears almost impossible to cross. In everyday life, we become accustomed to the idea that something can always travel faster. A runner moves faster than someone walking. An airplane is faster than a car. A rocket is faster than an airplane. Speed seems merely a matter of technology. But nature has drawn a boundary. It is the speed of light in a vacuum, approximately 300,000 kilometers per second. According to our current understanding of physics, no object with non-zero rest mass can ever be accelerated to or beyond this speed. Not because our engines are insufficient, but because as an object with mass approaches the speed of light, the energy required to increase its speed even slightly grows enormously. Within the framework of relativity, reaching the exact speed of light would require an infinite amount of energy, something that is fundamentally impossible for objects that possess mass. It is remarkable to think that although human imagination can travel without limits, the universe itself seems to preserve a boundary that cannot simply be crossed. Perhaps every garden needs its fence. Every piece of music needs its moments of silence, and every universe possesses limits that allow its laws to remain beautifully consistent. Yet just when we begin to think we are finally understanding the world, quantum mechanics quietly opens the door to another mystery. It is called quantum entanglement. Albert Einstein famously described it as spooky action at a distance. His words reflected his deep astonishment at the predictions of quantum mechanics. When two particles are prepared in a special quantum state, measurements performed on them can reveal remarkably strong correlations, even after they have been separated by enormous distances. What is important to understand is that this does not mean information is traveling faster than light. Rather, it means the state of the two-particle system cannot be fully described by considering each particle independently. Over many decades, increasingly sophisticated experiments have confirmed that these quantum correlations are indeed real. Today, scientists are exploring them as the foundation for quantum communication and quantum computing. For many people, Quantum entanglement serves as a humble reminder that nature has never promised to behave according to human intuition. Jung himself was deeply interested in meaningful connections within human experience and described certain psychological phenomena as synchronicity, meaningful coincidences that carry psychological significance. It is important to be clear that synchronicity is a concept within analytical psychology, not a physical explanation for quantum entanglement. Even so, both ideas invite a similar feeling. Sometimes the world is simply larger than the simple models we use to explain it. Perhaps the greatest beauty is not in finding every answer, but in never losing our sense of wonder. And now, as our journey gradually approaches its close, one final paradox quietly awaits us. Among the four fundamental forces of nature, gravity is actually the weakest when compared at the scale of elementary particles. The electromagnetic force is vastly stronger. The strong nuclear force is stronger still. So why is gravity the force that shapes the entire universe? The answer lies in one remarkable characteristic. Electric charge comes in two forms, positive and negative. They can cancel one another out. The nuclear forces act only across extraordinarily tiny distances. Gravity is different. Everything that possesses mass or energy contributes to a gravitational field. And according to our current models, gravity is always attractive, allowing the influence of countless objects to accumulate across immense distances. A grain of dust has almost no noticeable gravity. A single person has very little as well. A mountain possesses a bit more. A planet, much more still. A star, vastly more. And a galaxy containing hundreds of billions of stars creates immense rivers of gravity that guide the motion of countless stellar systems over billions of years. It is gravity that gathers clouds of gas together to form stars. It is gravity that keeps planets faithfully orbiting their suns. It is gravity that shapes galaxies, galaxy clusters, and the immense cosmic web that modern telescopes continue to observe. The weakest force, yet also the most patient. It never needs to hurry. It simply waits. Millions of years, billions of years, and in the end, it helps create worlds where life itself can emerge. There is something profoundly beautiful in that thought. In our daily lives, we are often drawn toward things that are powerful, loud, and immediate. But nature seems to tell a different story. Sometimes the influences that endure the longest come from the quietest beginnings. A small word of encouragement can change an entire life. A good habit repeated each day can slowly shape an entirely new person. And a force as gentle as gravity, through nothing more than unwavering patience over billions of years, has helped build the very structure of the universe we call home. Perhaps this is another gentle lesson that nature quietly offers each of us. There is no need to shine brilliantly every single moment. There is no need to transform everything overnight. Sometimes the deepest peace is built from movements that are very small, very slow, and wonderfully persistent. As you lie here, listening to stories about invisible particles, about light, about time, about stars compressed beyond imagination, and about gravity, quietly embracing the entire universe, perhaps you may begin to sense something beautifully simple. We are not separate from the universe. We are part of it. The atoms within your body obey the very same laws that shape the stars. The light that has just reached your eyes is the same light that has traveled across the immense reaches of the cosmos. And every passing moment you experience is woven into the vast fabric of space-time that Einstein so elegantly described. Now let those thoughts settle gently within you, like the surface of a peaceful lake becoming perfectly still after the final evening breeze has faded away. For in the next part of our journey, we will leave behind the fundamental laws of reality and travel even farther still, exploring the remarkable wonders unfolding among the stars, the galaxies, and the immeasurable reaches of the universe, where every distant light carries a story that began millions, and perhaps even billions, of years ago. The strange wonders of the universe. As we gently bring our exploration of the deeper nature of reality to a close, perhaps there is still a quiet sense of wonder lingering in your mind. A vacuum turns out not to be empty at all. Time does not flow evenly, like the quiet ticking of the clock upon the wall. Objects that seem perfectly solid are composed mostly of empty space. And gravity, so incredibly weak at the scale of elementary particles, patiently shapes the entire architecture of the universe. If all of these things are true, then perhaps the strangest thing is not that the universe is hiding its secrets from us. Perhaps the strangest thing is that the universe has always been here before our eyes. It is simply that the human mind has not evolved to perceive the whole picture. Carl Gustav Jung wrote a beautiful sentence in Memories, Dreams, Reflections. The least of things with a meaning is worth more in life than the greatest of things without it. Perhaps science is much the same. Every scientific discovery does more than expand our understanding of matter. It also expands the way we understand ourselves. Each new truth becomes a small doorway, allowing consciousness to move a little closer toward what Jung called individuation, the lifelong journey of gradually realizing that reality is always greater than the self we imagine ourselves to be. Tonight, we will continue our journey very slowly, not to conquer the universe, but simply to listen to it. Perhaps no object in the universe inspires both awe and humility quite like a black hole. Simply hearing those words, many people immediately imagine an enormous mouth swallowing everything around it. Science fiction often portrays black holes as gateways from which nothing can ever return. Yet reality is even stranger. The first astonishing thing is not that black holes attract matter, it is that they transform light itself. According to Albert Einstein's theory of general relativity, gravity is not merely an invisible force pulling objects together. Mass and energy curve the very fabric of space-time, and light follows those curved paths. As light struggles to escape the immensely powerful gravitational field surrounding a black hole, it gradually loses energy. Its wavelength becomes stretched, its frequency decreases, and the light shifts toward the red end of the spectrum. This phenomenon is known as gravitational redshift. Imagine listening to a piece of music that is slowly being played at a lower and lower speed. The high notes become deeper. The familiar rhythm begins to stretch. Light behaves in much the same way, not because light itself grows weary, but because the very structure of space-time surrounding the black hole has altered its journey. This means that even light, the very symbol of speed and freedom, is not entirely independent of the shape of the universe through which it travels. There is something deeply beautiful in that thought. It reminds us that nothing exists entirely on its own. Everything is quietly in conversation with the world through which it moves. Perhaps human beings are no different. Our experiences, our memories, and our emotions do more than change the way we see the world. They also shape the people we gradually become. But if black holes have the power to slow light, then the stars are the quiet places where everything inside your own body was first created. Take a gentle look at your hand, your skin, your veins, the steady rhythm of your heartbeat, the quiet flow of your breath. At first glance, all of these things seem entirely your own. Yet astrophysics tells a very different story. A story that began billions of years ago. Shortly after the Big Bang, the universe consisted almost entirely of hydrogen, helium, and a tiny amount of lithium. Heavier elements scarcely existed. There was no carbon, no oxygen, no calcium, no iron, which means there were no rocks, no oceans, no forests, and certainly no human beings. It took hundreds of millions of years before the first stars began to form. Deep within their cores, under temperatures of millions of degrees and unimaginable pressure, nuclear fusion continuously transformed simple hydrogen atoms into heavier and heavier elements. Carbon was born. Oxygen was created. Silicon appeared. Eventually, iron. But the story did not end there. When massive stars reached the ends of their lives, many exploded as spectacular supernovae. Those tremendous explosions scattered the elements they had forged into space. Over millions of years, new clouds of gas and dust gathered together, eventually forming new generations of stars, planets, and finally, life itself, which means the carbon inside every one of your cells once lived within a star. The calcium in your bones did as well. The iron flowing through your blood was also born there. Perhaps no one has expressed this truth more beautifully than astronomer Carl Sagan. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. This is not merely poetic imagery. It is a profoundly moving scientific truth. We are not simply living in the universe. We are part of its billions of years-long history. Perhaps Jung would have smiled at that thought, for he believed that human beings truly mature only when they recognize that they belong to something greater than the individual ego. In Jungian psychology, every person is part of the collective unconscious. In physics, every atom within our bodies is part of a story the stars began telling long before the Earth itself existed. Two different paths, yet both lead toward the same feeling: connection. Now imagine yourself standing inside a spacecraft. Beyond a small window, the Earth glows with a deep blue brilliance. There is no sky, no horizon, only the immense darkness of space, with our blue planet silently turning below. You gently release your hand from the wall of the spacecraft. Suddenly, you begin to float. Many people call this zero gravity, but that description is not entirely accurate. Astronauts aboard the International Space Station are not floating because they have traveled so far from Earth that gravity no longer reaches them. In fact, at an altitude of roughly 400 kilometers, Earth's gravity remains surprisingly strong, about 90% as powerful as it is at the planet's surface. So why do they float? The answer lies in continuous free fall. The International Space Station travels sideways at an extraordinary speed. While gravity continuously pulls it toward Earth, the station is also moving forward so rapidly that it keeps missing the ground. Its orbit is, in essence, an endless fall around the Earth. The astronauts inside the station are falling at exactly the same rate as the spacecraft itself. Because everything is accelerating together in nearly the same way, they do not experience the supporting force of a floor beneath their feet as they do while standing on Earth. That is what creates the remarkable sensation we call microgravity. The strange wonders of the universe. Continued. There is something wonderfully peaceful about that image. A human being quietly drifting through space. Not because gravity has disappeared, but because both the traveler and the spacecraft are sharing the very same journey. That brings us to another fascinating truth. If you were to shout as loudly as you could in the emptiness of space, no one would hear you. Not because the distance is too great, but because sound cannot travel through a vacuum. Sound is, in essence, a mechanical vibration. To propagate, it requires a material medium, such as air, water, or a solid. Molecules collide with one another, passing the vibration from one place to the next. In the vacuum of space, there are almost no particles to carry those vibrations. That is why the tremendous explosions of stars, the colossal collisions between celestial bodies, and the violent eruptions upon the sun's surface produce no sound that can travel through space in the way we hear sounds here on Earth. In that sense, the universe is quieter than we have ever imagined, a silence so profound that it is almost absolute. Perhaps it is this very silence that has inspired people throughout history to gaze at the night sky with a feeling that is both peaceful and mysterious. Jung believed that silence is not the absence of meaning. Sometimes it is the place where meaning quietly begins to speak. Perhaps the universe is much the same. It does not need words. It does not need sound. It does not need an echo. Simply through light that has traveled millions of light years before reaching our eyes, it continues telling the longest story ever written. And as you gently close your eyes, breathe in slowly, and let your breath flow softly back out. Perhaps you will begin to understand something that astronomers often discover. after years of studying the heavens. The more deeply we understand the universe, the more we learn to listen to its silence. Because sometimes, it is within that stillness that we realize we have never truly been separate from the stars. Perhaps, after quietly drifting through the silent vastness of space where light may spend millions of years reaching human eyes, and where the atoms within our bodies were once born inside the hearts of stars, you may begin to feel something truly remarkable. The universe never seems to stop surprising us. Each time we believe we have understood one of its laws, nature gently opens another doorway, leading us towards something even more subtle. Carl Gustav Jung once wrote, "The pendulum of the mind oscillates between sense and nonsense, not between right and wrong." Perhaps those words describe the history of science as well. Many ideas once dismissed as absurd have, with time, become the very foundation of our understanding of the world. What seems impossible is often nothing more than something human intuition has not yet learned to recognize. And one such discovery began with the sun itself. For thousands of years, humanity has looked upon the sun as a giant sphere of fire shining across the sky. Its light appears to travel in perfectly straight lines. Our intuition tells us exactly that. When you shine a flashlight through the darkness, its beam moves in a clear, straight direction. Unless something blocks it, it simply continues onward. Then Albert Einstein proposed a remarkably bold idea. According to general relativity, gravity does more than pull objects with mass. It bends the very fabric of space and time. And because light always follows the geometry of spacetime, its path also bends whenever it passes near an object of immense mass. In other words, the sun does not pull light like an invisible rope. Rather, the space surrounding the sun is itself gently curved, much like a soft sheet pressed downward beneath the weight of a heavy ball. Imagine rolling a marble across a perfectly flat mattress. Now place a bowling ball at its center. The mattress sinks. The marble no longer travels along a perfectly straight path. Instead, it gently changes direction as it passes through the depression. Light behaves in a similar way. Of course, this is only a simple analogy. The four-dimensional fabric of space-time is far more complex than any stretched sheet could ever represent. But the image helps us grasp the central idea. Mass changes the geometry of the universe itself. In 1919, astronomer Arthur Eddington observed a total solar eclipse to test Einstein's prediction. As the moon blocked the brilliant light of the sun, astronomers were able to photograph stars located close to the sun's edge. Their apparent positions had shifted ever so slightly, exactly as general relativity had predicted. It became one of the most celebrated observations in the history of science, not because it proved Einstein was a genius, but because it demonstrated that human intuition does not always reveal the true nature of reality. Some truths reveal themselves only when we are patient enough to observe. That thought recalls one of Jung's most beautiful reflections. He believed that life's most meaningful symbols rarely appear amid noise and excitement. They arrive quietly, slowly, almost imperceptibly, like the light of a distant star that has silently crossed millions of years of space before finally reaching the eyes of someone quietly gazing into the night. If that story revealed that light itself can follow unexpected paths, the next one brings us back to something much more familiar: a simple glass of water. Almost everyone has watched water freeze. If you placed two identical glasses into a freezer, common sense would suggest that the colder water should freeze before the hotter one. That seems perfectly reasonable. After all, hot water must first cool down before it can begin to freeze. Yet for centuries, people have occasionally observed something rather surprising. Under certain conditions, hot water can actually freeze faster than cold water. Today, this phenomenon is known as the Mpemba effect. Named after Erasto Mpemba, a student from Tanzania who courageously questioned what he had observed during the 1960s. At first, many people assumed he had simply made a mistake. How could such a thing possibly happen? Yet later experiments confirmed that the phenomenon can indeed occur under certain experimental conditions. What makes it especially fascinating is this. Even today, there is still no single explanation accepted by all scientists. Several different mechanisms have been proposed. Hot water may evaporate more quickly, leaving less water to freeze. Convection currents inside hot water behave differently than those in cold water. The amount of dissolved gases changes with temperature. The formation of ice crystals may also be influenced by a variety of additional factors. Under different conditions, one or several of these mechanisms may play important roles. In other words, the Mpemba effect is not a universal law stating that hot water always freezes faster than cold water. It is a phenomenon that can occur under particular circumstances, and scientists continue studying it to better understand exactly why. Perhaps that is what makes the story so special. Not because we already possess every answer, but because science is humble enough to admit that some questions remain open. Perhaps this is one of science's most beautiful qualities. It is never afraid to say, "We are still learning." Carl Gustav Jung devoted much of his life to exploring aspects of the human mind that could not yet be fully explained. Although his approach differed greatly from that of physics, both share something deeply admirable: curiosity joined with humility. The world does not become any less mysterious as we understand more about it. Quite the opposite. Every answer quietly opens the door to many new questions. Perhaps that is why, after thousands of years of watching the stars, centuries of studying nature, and countless experiments conducted in laboratories, humanity has never stopped being astonished. The universe is not a book with only one chapter. It is more like an ancient forest. The deeper we wander into it, the more we realize there are still paths ahead that no one has ever named. And much like the dreams Jung often described, each new layer of meaning gently leads us toward another, deeper layer of reality. Every day, billions of people open their phones to find directions, request a ride, locate themselves on a map, or follow the flight of someone they love. We touch the screen, wait only a few seconds, and trust completely that the tiny glowing dot truly marks where we are standing. It all happens so quickly that we rarely stop to ask, how can such a small device resting in the palm of our hand know our exact location upon an entire planet? Behind that answer lies far more than technology. It depends upon one of the boldest ideas humanity has ever discovered about the nature of time itself. The Global Positioning System, or GPS, works through dozens of satellites quietly orbiting Earth at an altitude of roughly 20,000 kilometers. Each satellite continuously broadcasts radio signals containing extraordinarily precise time measurements generated by atomic clocks. Clocks so accurate that over many years of operation, they lose only tiny fractions of a second. Your phone does not actually see where it is. It simply listens. By receiving signals from multiple satellites and measuring how long each signal takes to arrive, your device calculates its distance from every satellite. Combining those distances allows it to determine your location with astonishing precision. At first, everything seems to be nothing more than a problem of geometry. But there is one complication. A complication so profound that, had Albert Einstein never published his two theories of relativity, the GPS system we rely on today would quickly become useless. Physics, in everyday life, we already know that time is not an absolute, universal flow. GPS satellites race around the Earth at tremendous speeds. According to special relativity, clocks aboard those rapidly moving satellites tick ever so slightly slower than clocks on Earth's surface. But at the same time, those satellites orbit much farther from Earth's center, where gravity is weaker. According to general relativity, clocks in weaker gravitational fields tick faster. These two effects happen simultaneously. They do not perfectly cancel one another. The final result is that the clocks aboard GPS satellites run about 38 microseconds faster each day than clocks here on Earth. 38 millionths of a second. It sounds unimaginably small, far smaller than the blink of an eye. Yet for radio signals traveling at nearly the speed of light, that tiny difference would accumulate into a positioning error of roughly 11 kilometers every day if left uncorrected. Before long, the map on your phone would no longer know where you are. The road you appear to be traveling would gradually drift away from reality. An ambulance could be sent to the wrong location. An aircraft could no longer navigate with the precision it requires. What is truly remarkable is that billions of devices continue to work accurately every single day because engineers incorporated Einstein's relativistic effects into the system from the very beginning. In other words, every time you open a map application, you are using a technology that could exist only because time does not pass at the same rate everywhere. There is something deeply beautiful in that thought. A theory once considered far too abstract and far removed from everyday life now quietly accompanies every step we take. Perhaps this is also how science grows. Questions that once seemed relevant only to theoretical physicists gradually become the foundation of ordinary daily life. That thought recalls one of Carl Jung's most profound observations. Who looks outside, dreams. Who looks inside, awakes. Jung wrote these words about the journey into the inner world. Yet, in its own way, science follows a remarkably similar path. The deeper we explore the nature of reality, the more we discover that the simplest things contain the richest layers of meaning. A beam of light is not merely light. A drop of water is not merely water. A signal from a satellite is not merely data. Behind every phenomenon lies a story stretching across centuries, a story written through curiosity, patience, and humanity's enduring desire to understand the universe a little more deeply. Perhaps that is what quietly connects science with the deeper life of the soul. Jung believed that maturity does not come from collecting countless answers. It comes from learning to live peacefully alongside realities greater than ourselves. Modern physics offers a similar feeling. It does not make the world seem colder or more distant. Quite the opposite. It makes the ordinary world surrounding us even more precious. The light of dawn has crossed space before reaching your eyes. The atoms within your body were forged inside the hearts of ancient stars. The time you experience is not exactly the same as the time unfolding aboard satellites quietly orbiting high above the Earth. And all of this is happening right now, whether we notice it or not. The night has grown a little deeper. Perhaps your eyelids have become a little heavier as well. If so, allow these thoughts to settle gently within you, like the ripples upon a quiet lake after the final evening breeze has faded away. You do not need to remember every concept. You do not need to memorize every number. Simply carry with you one gentle feeling. The universe is far greater than anything we can see. And because of that, life is far more wonderful than we often imagine. In the next part of our journey, we will leave behind the immense spaces between the stars and return to the familiar world of everyday life. Together, we will discover how physics quietly reveals itself within every rainfall, every rainbow, every flash of lightning, every drop of water, and the countless ordinary events that surround us each day without asking for our attention. Perhaps you will be surprised to discover that the universe's greatest mysteries are not hidden only among distant galaxies. They have been quietly waiting all along within the ordinary world around us. Physics in everyday life. After traveling together through the silent spaces between the stars where gravity bends light itself, and where the atoms within our bodies were born, inside the hearts of ancient suns, you may begin to feel that the universe is an unimaginably distant place. But as we gently bring our attention back to Earth, back to the quiet room where you are resting at this very moment, something remarkable begins to reveal itself. The same laws that shaped entire galaxies are quietly present in the smallest moments of everyday life. You do not need a telescope to find them. You do not need a spacecraft. You do not even need to leave Earth's atmosphere. All you need is a single drop of water, a ray of sunlight, a piece of glass, or perhaps a small magnet resting upon a desk. Carl Gustav Jung once wrote in Modern Man, In Search of a Soul, "The shoe that fits one person pinches another." There is no recipe for living that suits all cases. Perhaps nature works in much the same way. No law exists entirely on its own. No phenomenon stands alone. Every small event forms part of an immense network connecting everything throughout the universe. And the more carefully we observe ordinary things, the more we discover that wonder has never been very far away. If you have ever watched a figure skater perform, perhaps you have wondered how they can suddenly spin so incredibly fast. At first, their arms are stretched wide. Their body turns slowly, gracefully, effortlessly. Then, within a single moment, they pull their arms close against their body, and almost magically, their spinning speed increases dramatically. No engine suddenly switches on. No invisible hand pushes them from behind. So what happened? The answer lies in one of the most elegant principles of mechanics: the conservation of angular momentum. When there is essentially no significant external torque acting upon the skater, the total angular momentum remains constant. As the skater draws their arms inward, their moment of inertia becomes smaller. To keep angular momentum unchanged, their rotational speed must increase. At first glance, this seems like nothing more than another equation from physics, but viewed through a quieter state of mind, it almost feels like poetry. So often, we believe that moving forward more quickly requires finding something outside ourselves: more strength, more opportunity, more recognition. Yet the skater offers us a completely different image. It is precisely by drawing inward, by finding balance, by making every movement simpler and more centered, that greater speed naturally appears. It brings to mind the journey Jung called individuation. He did not see maturity as collecting ever more social roles or identities. Quite the opposite. It was the gradual process of returning to one's own center. Perhaps physics and psychology, though they travel along different paths, occasionally meet in a surprisingly beautiful place. Both remind us that inner balance often possesses far greater strength than the loud movements of the outside world. If human movement tells a story about balance, then the sky after a rainfall tells another story, a story about light. Almost everyone remembers standing quietly after the rain, looking upward as a rainbow stretches across the horizon. 7 gentle colors arch gracefully across the sky, so beautiful that many cultures have imagined it as a bridge between heaven and earth. Physics, however, tells us that this beautiful wonder begins with something astonishingly small: a single raindrop. The sunlight we casually call white light actually contains many different wavelengths. As sunlight enters a raindrop, it is refracted. Its direction changes because light travels at a different speed in water than it does in air. Inside the droplet, part of the light reflects from the inner surface before being refracted once more as it leaves the water. The important detail is that each color bends by a slightly different angle. That is why white light separates into the beautiful spectrum our eyes can see. A rainbow does not truly exist as an object suspended in the sky. It is the result of countless raindrops interacting with sunlight, and with the eyes of the person who is quietly watching. Physics in everyday life continued. If you take a few steps forward, the rainbow moves with you. No two people ever see exactly the same rainbow. There is something wonderfully gentle about that thought. Some kinds of beauty exist only in the meeting between the world and the one who is looking at it. Carl Gustav Jung devoted much of his life to studying the symbols that arise within the human mind. For him, a symbol did not exist only within the object itself. It also emerged from the relationship between the outer world and the inner one. In a way, a rainbow is much the same. It is not merely light. It is not merely water. It is also perspective. Perhaps many of life's most beautiful experiences begin simply by learning how to see. Then, as night quietly arrives, the sky begins telling an entirely different story. A flash of lightning suddenly tears across the heavens. Brilliant, blinding, gone in less than a second. Only afterward does the thunder follow. In many ancient cultures, lightning was believed to be the weapon of the gods. Today, science has given us a clearer understanding. Yet that understanding has not made lightning any less extraordinary. If anything, it has made it even more astonishing. Air is normally a very good electrical insulator, but when the electric field inside a thunderstorm becomes strong enough, the air begins to ionize, creating a conductive path through which an enormous electric current can flow. As that immense current surges through the channel, the temperature rises with astonishing speed. Inside a lightning channel, temperatures can reach about 30,000 Kelvin, far hotter than the sun's visible surface, known as the photosphere, which is roughly 5,800 Kelvin. This does not mean the entire sun is cooler than lightning. Deep within the sun, especially in its core, temperatures reach millions of Kelvin, but the glowing surface we actually see is indeed cooler than the peak temperature inside a lightning bolt. It is an almost unbelievable fact, right here in Earth's own sky. During a moment, lasting only a few thousandths of a second, nature can create temperatures hotter than the visible surface of the very star that has sustained life upon our planet. Perhaps that reminds us that true power is not always measured by size. Sometimes an event lasting only an instant contains astonishing amounts of energy. And when the lightning has faded away, turn your attention toward the window beside you. Perhaps there is a pane of clear glass there. You look through it every day, rarely giving it much thought. Yet glass itself is one of the strangest materials humanity has ever learned to use. For centuries, people assumed that glass was simply another ordinary solid. Today, materials physics paints a far more subtle picture. Glass is what scientists call an amorphous solid. Its atoms do not arrange themselves into the repeating crystal lattice found in many other solids. Instead, they possess short-range order without forming a repeating pattern over large distances. This gives glass the mechanical properties of a solid while possessing an internal structure quite unlike that of most familiar crystals. You may have heard the popular claim that glass is actually a liquid that flows very slowly. This is a common misconception. According to modern scientific understanding, ordinary window glass at room temperature does not slowly flow like a liquid. The uneven thickness seen in very old windows is primarily the result of historical manufacturing techniques, not centuries of glass gradually flowing downward. There is something quietly beautiful about that. A material that is transparent, that appears delicate, yet is strong enough to shelter us from rain and wind. A structure that lacks the perfect order of a crystal, yet remains remarkably stable. Perhaps people are not so different. We do not need to become perfectly ordered according to some rigid pattern in order to have value. Our memories, our scattered experiences, our moments of joy, and even our wounds. Sometimes it is precisely these things that create a soul transparent enough for the light of life to pass through. As the night grows quieter still, allow these images to remain gently in your thoughts. A figure skater spinning upon the ice, a rainbow after the rain, a brilliant flash of lightning, a silent pane of glass beside a window. All of them are quietly telling the same story. Physics does not exist only inside laboratories or among galaxies millions of light years away. It is present within the ordinary moments of everyday life. Now that we have quietly finished our stories about rainbows, lightning, and the silent pane of glass standing faithfully beside the window, perhaps you are beginning to notice something rather wonderful. The greatest marvels of physics do not always require galaxies millions of light years away. Sometimes, they fit into the palm of your hand, hidden inside a small magnet, a pot of boiling water, or a train that appears to glide without ever touching the ground. Carl Gustav Jung once wrote, "In all chaos there is a cosmos, in all disorder a secret order." Perhaps that is exactly what physics has always tried to reveal. Behind events that appear random, nature quietly follows laws that are subtle, enduring, and deeply beautiful. Let us begin with something almost everyone has held in their hand: a small magnet. As children, many of us watched with fascination as two magnets suddenly pulled toward one another or pushed each other apart without ever making contact. It felt almost magical, an invisible force. No color, no scent, impossible to see, yet powerful enough to pull a steel nail from several centimeters away. Today we understand that magnets produce a magnetic field, a region of space where magnetic forces act upon suitable materials or particles with magnetic properties. In ferromagnetic materials such as iron, many of the electrons' tiny magnetic moments naturally align in the same direction, creating a measurable magnetic field extending beyond the object itself. The remarkable thing is this: you have never actually seen a magnetic field with your own eyes. What you see are only its effects: iron filings arranging themselves into graceful curves, a compass needle quietly pointing north, an electric motor beginning to turn. Some of the most important things in life are much the same: trust, love, faith. No one can see them as clearly as they see a stone, yet they quietly shape the ways human beings connect with one another. Perhaps that is why Jung devoted so much attention to the invisible world of the mind. Not everything that is real must also be visible. If magnets already seem remarkable, the next phenomenon astonished physicists even more. It is called superconductivity. Normally, whenever electric current flows through a wire, part of its energy is inevitably converted into heat because of electrical resistance. That is why wires become warm. It is also why power transmission always loses some energy. Yet in certain materials, once they are cooled below a critical temperature, their electrical resistance falls to levels too small to measure with existing techniques. This remarkable state is known as superconductivity. It means that electric current can continue circulating within a superconducting loop for extraordinarily long periods with almost no loss due to electrical resistance. To physicists, at the beginning of the 20th century, this seemed almost impossible to believe. How could nature permit such a thing? The answer lies once again within quantum mechanics. At sufficiently low temperatures, electrons inside a superconductor can form what are known as Cooper pairs. These paired electrons move collectively in a manner fundamentally different from individual electrons, within the framework of the BCS theory. This collective quantum behavior explains why electrical resistance disappears in many conventional superconductors. Once again, the quantum world quietly reveals itself within everyday life, never loudly, never demanding attention, simply working beneath the surface of matter itself. From superconductivity, humanity developed one of the most elegant forms of transportation ever created: the maglev train. If you have ever watched videos of these remarkable trains, you may have had the impression that they are flying. Motion in the solar system continued. In reality, maglev trains do not truly fly like airplanes. Instead, they levitate above the track, using specially engineered magnetic systems. Depending on the technology, the train may be supported by electromagnetic attraction or electrodynamic lift, and some systems employ superconducting magnets capable of generating extremely powerful magnetic fields. Because there is no direct mechanical contact between wheels and rails while the train is moving, friction is dramatically reduced. As a result, these remarkable trains can exceed 500 kilometers per hour. Yet for many people, the greatest beauty of maglev technology is not its speed. It is its silence. The familiar rumble nearly disappears. The vibrations become almost imperceptible. The train glides so gently that it seems to float upon the air itself. There is something deeply meditative about that image. Sometimes, the fastest movement comes not from adding more power, but from removing unnecessary resistance. Perhaps the human mind works in much the same way. We do not always need to try harder. Sometimes what we truly need is simply to let go of the things that have been quietly holding us back. And now, we arrive at a phenomenon whose very name sounds as though it belongs in a work of science fiction: quantum tunneling. According to everyday intuition, if a ball lacks enough energy to roll over the hill before it, it simply rolls back down. That makes perfect sense. Yet in the quantum world, particles are described by wave functions, and under certain conditions there exists a finite probability of finding a particle on the opposite side of an energy barrier, even when it does not possess enough energy to climb over that barrier. This remarkable phenomenon is called quantum tunneling, not because the particle literally digs a tunnel through the barrier, nor because the laws of physics are somehow broken, but because the quantum nature of matter is fundamentally different from the intuition we developed while living in the macroscopic world. Without quantum tunneling, many modern technologies, including the scanning tunneling microscope, would never exist. The phenomenon also plays an essential role in several natural processes, including the nuclear fusion reactions taking place deep within the hearts of stars. What seems impossible is quietly happening throughout the universe. Once again, nature gently reminds us that reality is always richer than our first intuition can imagine. After all these extraordinary discoveries, let us return to an old and familiar friend: water. Perhaps no substance is at once so ordinary and so remarkable. You drink it every day. You bathe in it. You watch it fall as rain. You see it flowing in rivers. You gaze upon it stretching across the sea. Yet water possesses many truly unusual properties. One of its most famous characteristics is this: when water freezes, it expands instead of contracting, as most substances do. That is why ice is less dense than liquid water and floats upon the surface of lakes and ponds. If this were not true, lakes and rivers in colder regions could freeze from the bottom upward, creating profoundly different conditions for aquatic ecosystems. Scientists understand that the hydrogen bond network between water molecules plays a crucial role in producing this extraordinary behavior, a tiny change occurring at the molecular scale, yet one that profoundly influences life across an entire planet. Perhaps that reminds us of something important. Not everything that truly matters needs to be enormous. Sometimes a single, delicate property of one simple molecule helps shape the entire history of life. Finally, before we close this chapter, imagine carrying a glass of water to a very unusual place. Not to the top of a mountain, but inside a vacuum chamber. You begin lowering the surrounding air pressure. Then something unexpected happens. The water begins to boil, even though its temperature remains far below 100 degrees Celsius. At first, this seems to contradict everything we learned as children, yet the explanation is beautifully simple. The boiling point of water depends upon pressure. Water boils when its vapor pressure becomes equal to the pressure of the surrounding environment. When the external pressure decreases, that condition is reached at a lower temperature. That is why water boils at temperatures below 100 degrees Celsius on high mountains. And inside a sufficiently strong vacuum, water can begin boiling at temperatures close to ordinary room temperature. Once again, nature quietly reminds us that many things we imagine to be absolute laws are actually true only under the familiar conditions of everyday life. Perhaps human beings are not so different. Many of the limits we believe cannot be changed may simply reflect the environment in which we happen to live, rather than the full extent of our potential. Tonight, we have wandered together among invisible magnets, superconducting materials, levitating trains, mysterious quantum particles, and ordinary drops of water that quietly conceal extraordinary secrets. If there is one lesson physics gently whispers to us, perhaps it is this: the wonder does not come from the world trying to become extraordinary. The wonder comes from the fact that the world has always been this way. We simply seldom pause long enough to notice. Perhaps that is also the greatest gift of peaceful evenings. When life slows down, when the mind grows quieter, we begin to recognize the beauty that has always surrounded us. And in the next part of our journey, we will leave behind the familiar objects of Earth and lift our eyes toward the heavens once more, beginning an exploration of the graceful motions of our solar system, where every planet, every orbit, and every ray of sunlight has been telling a story billions of years in the making, patiently waiting for someone willing to listen beneath the quiet night sky. Motion in the solar system. Now that we have gently concluded our stories about water, magnets, and the quiet physical laws operating within the ordinary objects around us, perhaps you are beginning to notice something rather remarkable. The world in which we live has never been separate from the sky above us. Every drop of water in the ocean feels the influence of the moon. Every sunrise is the consequence of immense celestial motions throughout the solar system, even as your body rests peacefully upon your bed this very moment. It is traveling around the sun at nearly 30 kilometers per second, while the solar system itself continues its own journey around the center of the Milky Way galaxy. And yet, we feel none of it, perhaps because the human mind naturally judges the world through what it can directly sense. Carl Gustav Jung once wrote, "Who looks outside, dreams. Who looks inside, awakes." He wrote those words about the journey into the inner world. Yet physics, in its own quiet way, teaches something remarkably similar. The more deeply we observe the invisible motions of the universe, the more awake we become to the realization that our own lives are woven into rhythms vastly greater than ourselves. Tonight, let us raise our eyes toward the heavens once again, not to search for something unfamiliar, but to discover that we have always been part of the slow and beautiful symphony of the solar system. If you have ever watched live broadcasts from the International Space Station, or ISS, you have probably experienced a curious feeling. Astronauts drift gently through the station. Tiny droplets of water float as perfect spheres. A pencil needs only the lightest touch before it slowly glides across the entire cabin. Everything appears free from gravity. Yet reality is more subtle. The ISS is not standing still in space, nor has it escaped Earth's gravity. In fact, the station circles Earth at roughly 7.7 kilometers per second, completing one orbit in only about 90 minutes. That means astronauts aboard the station witness approximately 16 sunrises and 16 sunsets every single day. For them, a day is no longer measured by one sunrise and one sunset, as it is on Earth. Instead, it is measured by their endless journeys around our blue planet. Perhaps the most remarkable part is this: the ISS does not orbit Earth despite being pulled downward. It orbits Earth because it is constantly being pulled downward. Imagine throwing a stone horizontally. Throw it gently, and it soon falls to the ground. Throw it harder, and it travels farther before landing. If you could throw it fast enough, then while Earth curves away beneath it, the stone would continue falling around the planet without ever striking the surface. That is the essential idea behind an orbit. The ISS is falling, yet it continually falls past the surface of the Earth. There is something deeply beautiful about that image. Sometimes what keeps us exactly where we belong is not remaining perfectly still. It is continuing to move within a delicate balance. Jung believed that a healthy soul is not one that never changes. Rather, it is one that discovers harmony among the opposing forces living within it. Perhaps an orbit is a beautiful symbol of that same balance. If the International Space Station helps us understand motion around the Earth, then one famous experiment performed on the Moon forever changed humanity's understanding of gravity. On the 2nd of August 1971, during the Apollo 15 mission, astronaut David Scott stood upon the lunar surface, holding two objects in his hands. Motion in the solar system continued. In one hand, he held a hammer. In the other, a feather. If this experiment were performed on Earth, the hammer would certainly strike the ground first, not because it is heavier, but because air resistance slows the feather's descent. The Moon, however, has virtually no significant atmosphere. David Scott released both objects at exactly the same moment. What happened astonished millions of people watching. The hammer and the feather reached the lunar surface at almost exactly the same time. More than 3 centuries earlier, Galileo Galilei had proposed that, in the absence of air resistance, all objects fall with the same gravitational acceleration, regardless of their mass. Now, humanity was witnessing that idea demonstrated upon another world. It was one of the most beautiful moments in the history of science. There was no triumphant music, no dramatic special effects, only a hammer, a feather, and a wonderfully simple truth. Nature treats every object equally. Perhaps that thought also says something about life. Many of the differences we believe to be fundamental are, in reality, simply the result of the environments surrounding us. When resistance is removed, the true nature of things quietly reveals itself. Perhaps Jung would have appreciated that idea. Much of his life's work was devoted to helping people discover who they truly were after gradually laying aside the masks that society had placed upon them. Yet the moon is not only a place where fascinating experiments have been performed, it is also quietly changing its position. Even now, as you listen to this story, the moon is slowly drifting away from the Earth at an average rate of about 3.8 centimeters each year. It is an incredibly small distance, about the speed at which a fingernail grows. Without extraordinarily precise instruments, we would never notice it. Scientists know this because the Apollo missions placed laser retroreflectors upon the lunar surface. By sending laser pulses from Earth to those mirrors and carefully measuring the time required for the light to return, researchers can determine the Earth-Moon distance with remarkable precision. So what is gradually carrying the moon farther away? The answer lies in the tides. The moon's gravity raises tidal bulges across Earth's oceans, but our planet rotates faster than the moon orbits around it. This interaction transfers a small amount of angular momentum from Earth's rotation into the moon's orbit. As a result, Earth's rotation gradually slows ever so slightly, while the moon slowly moves into a higher orbit, a dance that has lasted billions of years. Never hurried, never loud, changing only a few centimeters at a time. Perhaps many of life's most important transformations happen in much the same way. Great changes rarely arrive overnight. They are built from countless tiny movements that we scarcely notice. And speaking of the moon, we cannot ignore one of the oldest natural rhythms humanity has ever known: the tides. For thousands of years, fishermen learned to watch the sea rise and fall in steady cycles. They knew nothing of gravity, nothing of celestial mechanics. Yet they understood that somehow the oceans were responding to a rhythm written across the sky. Today, we know that the moon's gravitational pull is the primary cause of Earth's tides, while the sun also contributes, producing variations such as spring tides and neap tides. Even more fascinating is that the oceans are not the only things that respond. Earth's own crust rises and falls ever so slightly under the influence of these gravitational forces. Our entire planet gently flexes to a rhythm we never consciously perceive. There is something profoundly peaceful in that thought. When night falls and the tides quietly rise somewhere along Earth's distant shores, the ocean never needs to see the moon. It simply answers the silent invitation of the companion that has traveled beside it for more than 4 billion years. Perhaps human beings carry similar rhythms within themselves. Old memories, quiet emotions, dreams. They sometimes move silently beneath the surface of consciousness, just as the tides move beneath the light of the moon. Jung called them the currents of the unconscious. Physics calls them gravity. 2 different languages, yet both describe invisible influences capable of creating very real movements. As you slowly breathe in and gently breathe back out, imagine that somewhere far beyond the horizon, the tides are still rising and falling according to that ancient rhythm. Now that we have quietly departed the orbit of the International Space Station, watched the hammer and feather land together upon the moon, and followed the moon as it slowly drifts away from Earth, centimeter by centimeter, in a dance lasting billions of years, perhaps you are beginning to sense something extraordinary. The solar system is not a cold machine. It is more like a symphony. Every planet has its own rhythm. Every moon carries its own story. Every beam of light is undertaking a journey far longer than our imagination can easily comprehend. Carl Gustav Jung once wrote, "We cannot change anything unless we accept it." Perhaps that is equally true of science. Humanity cannot understand the universe if we insist that nature must always behave according to our intuition. We truly begin learning only when we accept that reality is sometimes stranger than even our most beautiful stories. If there is one planet that has repeatedly changed astronomers' understanding of time itself, it is Venus. Seen from afar, Venus is often called Earth's twin. Its size is remarkably similar. Its mass is remarkably similar. For a long time, people even hoped that life might exist there. But the more closely scientists studied it, the more they realized it is an entirely different world. One of its strangest characteristics is this: a day on Venus lasts longer than its year. It sounds almost like a paradox. Yet, it is entirely true. Venus requires about 225 Earth days to complete one orbit around the Sunday. Meanwhile, it takes about 243 Earth days to complete one rotation on its axis, its sidereal rotation period. In other words, if you could stand upon the surface of Venus and patiently wait for the planet to rotate just once, it would already have completed an entire year in its journey around the Sunday. Even more remarkable, Venus rotates in the opposite direction from most planets in our solar system. Scientists continue investigating how this unusual rotation developed. Several hypotheses have been proposed, including massive collisions early in the solar system's history and long-term interactions between Venus's extraordinarily dense atmosphere and the Sunday. Perhaps the greatest beauty of this story does not lie in the numbers, but in the realization that even concepts as familiar as a day and a year do not mean the same thing everywhere in the universe. Time is not a single universal clock, it is a dance, and every world moves to its own rhythm. If Venus surprises us through its relationship with time, then Saturn delights many people with a fact that sounds almost like a fairy tale. You may have heard someone say, Saturn could float on water. This does not mean that if we found an unimaginably enormous lake, we could simply place the planet into it. It is merely a comparison based upon average density. Saturn's average density is lower than the density of water. In theory, if an impossibly vast and stable ocean existed large enough to contain an entire planet, Saturn's average density suggests that it would tend to float. The comparison is physically meaningful in that limited sense, while also inspiring the imagination. A planet nearly 9 times Earth's diameter, so enormous that hundreds of Earths could fit inside it, yet, on average, less dense than water. It quietly reminds us that size alone never tells the whole story. Something immense is not necessarily solid. Something small is not necessarily light. In the universe, as in life, appearances reveal only part of the truth. Leaving Saturn behind, our journey carries us onward to Jupiter, the largest planet in the solar system. If Earth were a small pebble, Jupiter would resemble an enormous mountain. Its mass exceeds the combined mass of all the other planets in the solar system. For many years, astronomers have recognized that Jupiter's immense gravity profoundly influences the orbits of countless asteroids and comets. You may sometimes hear people say that Jupiter protects the Earth. There is some truth in that idea, but the full picture is more subtle. Jupiter's gravity can deflect or capture certain small bodies, while also altering the orbits of others in remarkably complex ways. Its role in Earth's long-term impact risk is therefore not simply that of a shield, but of an enormously important dynamical influence within the solar system. Rather than diminishing the beauty of the story, this makes it even richer. The planets do not exist independently. Every motion influences another. Every orbit contributes to the balance of the whole. Perhaps Jung would have seen in this a symbol of human life itself. No one truly lives alone. Every encounter, every relationship, every decision quietly alters the trajectories of others. Now let us turn our eyes toward the center of this entire planetary family, the Sunday. Every morning we watch it rise. Every day we feel its warmth. Yet few of us stop to consider that. Every passing second, the sun is losing a tiny portion of its own mass. Deep within its core, nuclear fusion continuously transforms hydrogen into helium. A very small fraction of that mass becomes energy, according to Einstein's famous equation, m². That energy becomes the sunlight and warmth spreading throughout the solar system. Every second, the sun converts roughly 4 million metric tons of mass into energy. The number sounds almost unimaginable, yet compared with the sun's total mass, it is extraordinarily small. According to current models, our star will therefore continue shining for approximately another 5 billion years. There is something profoundly moving in that realization. Light is always accompanied by giving, to warm the planets, to nourish life, to allow plants to perform photosynthesis. The sun must continuously transform part of itself into energy. Nature does not create light from nothing. Even the stars must give something of themselves. And finally, lift your eyes toward the sky on a quiet morning. Watch the sunlight touch the window. The trees, extreme stars, and extraordinary objects. Continued. Feel the sunlight resting upon your face. It is easy to imagine that those warm rays have only just left the Sunday. But in reality, their journey began about 8 minutes and 20 seconds ago. Light travels at nearly 300,000 kilometers per second. Even at that astonishing speed, it still needs more than 8 minutes to cross the average distance of nearly 150 million kilometers between the Sun and the Earth, which means, whenever you watch a sunrise, you are always seeing the Sun as it was more than 8 minutes ago. If the Sun were to undergo a sudden change in its visible light, we would not know until that new light finally arrived. In reality, dramatic changes of that kind do not occur in the sudden way we often imagine. That thought makes every ray of sunshine feel a little more precious. The light warming your skin has crossed an immense ocean of space, never rushing, never stopping, simply continuing its quiet journey. Perhaps people are much the same. Kind words spoken today may not bloom within someone's heart until many years later. Small acts of kindness may continue spreading in ways we will never fully know. Jung believed that every experience leaves its mark upon the deeper layers of the soul. Light does something similar. It always carries the imprint of where its journey began. Tonight, we have traveled among ever-moving orbits, planets with strange rhythms of time, giant worlds less dense than water, a star that quietly shines by transforming its own mass into energy, and rays of sunlight that have crossed space for more than 8 minutes before reaching the Earth. Perhaps the greatest lesson the solar system offers us is not found in its numbers, but in its rhythm. Everything is moving, yet nothing is in a hurry. Everything is changing, yet an extraordinary harmony remains. Perhaps the human soul longs for that same rhythm, not a life that stands perfectly still, but a life moving in balance. A change gentle enough that we can still recognize ourselves as time quietly flows onward. As your eyes gradually grow heavier, imagine that somewhere above tonight's sky, the planets continue tracing their ancient orbits exactly as they have done for billions of years. And in the next part of our journey, we will leave the solar system behind and travel toward even more extreme worlds. Astonishingly dense neutron stars, pulsars spinning like cosmic lighthouses, and neutrinos silently passing through your body by the trillions every second, leaving almost no trace that they were ever there. Extreme stars and extraordinary objects. Now that we have left the solar system behind, leaving its planets quietly following their ancient paths and the sunlight that traveled more than 8 minutes before reaching Earth, perhaps you can feel a very special kind of silence. It is the feeling many people experience whenever they begin looking beyond the roof above their heads, beyond the blue sky, beyond the Sunday, beyond everything familiar. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, "The decisive question for man is Is he related to something infinite or not? Perhaps that is the very question the night sky has quietly asked humanity for thousands of years. Are we truly connected to something greater than ourselves? Or are we merely small creatures that happen to appear upon an ordinary planet? Science does not answer that question in quite the same way philosophy does. Yet every new discovery about the universe seems to whisper the same message. We are small, but we have never been separate from the greater picture. Tonight, we continue our journey towards some of the most extreme objects nature has ever created. Places where matter itself no longer behaves as it does on Earth. Perhaps no star inspires greater awe among physicists than the neutron star. Earlier in our journey, we learned that a neutron star is the remnant left behind when a massive star ends its life in a supernova explosion. But tonight, let us look at it in another way. Imagine yourself standing far away in space. Before you lies a star that has just experienced the most violent moment of its existence. The brilliant light of the explosion slowly fades into darkness. Immense clouds of hot gas race outward across the universe. And what remains is only a tiny sphere, roughly 20 kilometers in diameter, yet more massive than our Sunday. It is almost impossible for the human mind to picture such a thing. If the Earth were compressed to the density of a neutron star, our planet would become dramatically smaller than it is today. That is the astonishing degree of compression gravity can achieve when a massive star reaches the end of its life. Inside such a star, matter no longer resembles anything familiar. Atoms can no longer maintain the structures found in a table, a chair, or even your own body. Under unimaginable pressure, electrons and protons combine to form neutrons. What remains is something like an immense ocean of neutrons packed together beyond ordinary imagination. Perhaps what makes neutron stars truly beautiful is not merely their extraordinary density. It is the quiet reminder they offer. Even after the most violent ending, nature can still create something entirely new. Jung devoted much of his work to understanding periods of crisis in human life. He never saw crisis as mere destruction. He believed that the dissolution of an old self sometimes becomes the doorway through which a deeper form of existence can emerge. The stars tell a similar story. To become a neutron star, a massive star must first die. Yet from that death, heavy elements are scattered throughout space, eventually helping form new generations of stars, planets, and perhaps even life itself. In the universe, an ending and a beginning are often simply two names for the same process. Yet if a neutron star appears silent, it can also become one of the most precise clocks nature has ever created. When a neutron star spins rapidly, while emitting beams of electromagnetic radiation from its magnetic poles, astronomers call it a pulsar. Imagine a lighthouse standing alone upon the ocean at night. The lighthouse itself does not blink. It simply turns. Each time its beam sweeps across your position, you briefly see a flash of light, then darkness, then light again. A pulsar behaves in much the same way. Its beams sweep across space as the star rotates. If Earth happens to lie within that sweeping beam, our telescopes detect an extraordinarily regular series of pulses. Some pulsars rotate only a few times each second. Others spin hundreds of times every second, so quickly that it almost escapes imagination. Even more astonishing, many pulsars are so stable that astronomers can predict their rotation periods with extraordinary precision over many years. Within a universe filled with explosions, filled with collisions, filled with constant change, such enduring rhythms continue quietly. It reminds us of the human heartbeat, or breathing, or waves endlessly returning to the shore generation after generation. Some rhythms require no conductor. They simply remain true to their own nature. Perhaps a healthy soul is much the same. Not perfectly still, not unchanging, but always able to return to its own quiet rhythm. Pulsars are not only beautiful, they are also extraordinarily valuable to science. Because their pulses remain so remarkably stable, astronomers use pulsars to investigate many questions in astrophysics, including testing certain predictions of relativity in suitable binary systems and studying the interstellar medium. There have even been proposals to use networks of pulsars as cosmic lighthouses, helping future spacecraft navigate across deep space. There is something deeply moving about that idea. A star that has already died, still helping those who come afterward find their way. There is something profoundly human in that image. The greatest things we leave behind are not always grand monuments. Sometimes, they are simply a signal, a light, a quiet landmark that helps someone else become a little less lost. Jung believed every person could become a guiding symbol for others, not through perfection, but through faithfulness to their authentic self. Perhaps pulsars are doing exactly that. They are no longer the brilliant young stars they once were. Yet in becoming something new, they have become the lighthouses of the universe. When we look into the night sky, we often imagine that the stars are telling only their own stories. But perhaps they are telling ours as well. The atoms within your body were forged inside stars that died long ago. The laws keeping your heart beating are the same laws allowing neutron stars to exist. The distance between humanity and the stars has never truly been a distance of matter, only a distance of understanding. Jung believed that the deeper we journey into ourselves, the more we discover that we belong to something greater than our individual ego. Astronomy quietly leads us toward the same realization. The farther we look into the universe, the more clearly we understand that we have never truly been separate from it. Perhaps that is the greatest gift these extraordinary stars offer us. Not astonishment, not fear, but humility, a quiet kind of peace. Like standing beneath a sky filled with stars on a windless night. You know you are very small, and strangely, that does not make you feel alone. Instead, it makes you feel exactly where you belong. Neutrinos are among the strangest particles nature has ever created. They carry no electric charge. Their mass is incredibly small. Although we now know that neutrinos are not completely massless, as scientists believed for many decades. What makes neutrinos remarkable is not merely their size or their tiny mass. It is the way they interact with the universe. Light is easily absorbed by a wall. A stone cannot pass through the ground. Yet neutrinos pass through ordinary matter with astonishing ease. Most neutrinos can travel through an entire planet without colliding with a single atom. It sounds almost like a fairy tale, yet it is one of the most beautiful truths in modern physics. Most of the neutrinos passing through your body at this very moment were born inside the sunday. Deep within its core, nuclear fusion produces not only light and heat, it also creates countless neutrinos. Unlike sunlight, which takes about 8 minutes to reach Earth after leaving the sun's surface, neutrinos also travel outward at speeds extremely close to the speed of light. Because they interact so weakly with matter, they escape from the sun's dense core almost immediately after being created, while photons must undergo an extraordinarily long and complex journey through the sun's interior before finally emerging from its surface. It is a remarkable thought. Every second, you are quietly bathing in a stream of particles that began their journey inside the heart of a star nearly 150 million kilometers away, and you feel absolutely nothing. For many years, neutrinos puzzled physicists. Early experiments detected far fewer solar neutrinos than theoretical models predicted. For a time, scientists wondered, had we misunderstood the sun itself? Or was there still some hidden secret within the neutrino? After decades of research, the answer gradually emerged. Neutrinos are capable of neutrino oscillation. Simply put, as neutrinos travel through space, they can transform among 3 different varieties, commonly known as electron neutrinos, muon neutrinos, and tau neutrinos. This remarkable discovery not only solved the long-standing solar neutrino problem, it also demonstrated that neutrinos must possess non-zero mass, a profound discovery that expanded our understanding of particle physics. Perhaps the most beautiful part of this story is not the mathematics. The greatest mysteries of the universe. Continued. Perhaps the most beautiful part of this story is not the mathematics. It is the patience. Some questions require decades. Some mysteries take generations of scientists before they begin to reveal themselves. The universe has never been in a hurry. Perhaps we do not need to hurry either. Carl Gustav Jung devoted his entire life to exploring layers of the human mind that ordinary consciousness cannot easily perceive. He wrote, "Until you make the unconscious conscious, it will direct your life and you will call it fate." Jung was speaking about the human unconscious. Neutrinos are not symbols of the unconscious, and science does not equate these two ideas. Yet it is fascinating that both physics and psychology quietly remind us of something remarkably similar. The forces that shape our lives are not always the ones we can easily see. Invisible forces keep planets in their orbits. Invisible particles quietly pass through entire planets. And invisible memories, emotions, and experiences silently shape the way we live, often without our even realizing it. Not everything important stands beneath a bright light. Some truths reveal themselves only when we become patient enough to listen to the silence. Today, scientists study neutrinos using enormous observatories built deep underground, beneath mountains, or buried within the ice of Antarctica, not because neutrinos prefer the darkness, but because those quiet places shield the detectors from countless other particles, allowing the extraordinarily rare signals from neutrinos to be observed. There is something profoundly beautiful about that image. To hear the universe's most delicate whispers, humanity must first seek silence. It reminds us of a simple truth about our own lives. We rarely come to understand ourselves during the noisiest moments. Only when life begins to slow, only when night arrives, only when the voices of the outside world become quieter, do we begin hearing what has always been present within our own hearts. If you look back across tonight's entire journey, you may notice an invisible thread connecting every story, from the atoms inside your body to neutron stars compressed beyond imagination, from pulsars spinning like cosmic lighthouses to neutrinos quietly passing through entire planets. Everything gently reminds us that the universe is not built only from things that shine brightly and easily capture our attention. It is also woven together by countless quiet things. Perhaps life is much the same. What shapes a person is rarely only their greatest achievements. Sometimes, it is a single word of encouragement, a small habit practiced each day, a gentle memory, or a quiet decision that no one else ever notices. Those seemingly invisible things can change an entire life. The night has grown deeper. Perhaps your eyes are slowly beginning to close. If so, allow your thoughts to rest upon one final image. Imagine the immense night sky above you. The stars continue shining quietly. The pulsars continue sending their patient, steady pulses across the universe. The neutrinos continue their nearly endless journeys through space. And you are resting peacefully upon a small planet, warmed by an ordinary star within an ordinary galaxy. Yet that does not make your life ordinary, because the atoms that form your body were once born inside the stars, because the same physical laws that sustain distant celestial objects are quietly present within every beat of your own heart. And because the uniquely human ability to look upward, to ask questions, and to stand in awe before the beauty of the universe has made us a truly remarkable part of its story. In the next part of our journey, we will travel even farther still, exploring some of the greatest mysteries modern science continues to investigate: dark matter, dark energy, the cosmic microwave background, and the ancient traces left behind from the very dawn of the universe itself. There, at the delicate boundary between what we know and what remains unknown, we will continue walking forward with curiosity, humility, and a mind always willing to be surprised. The greatest mysteries of the universe. Now that we have quietly completed our journey among neutron stars compressed beyond imagination, pulsars spinning like cosmic lighthouses, and neutrinos silently passing through our bodies by the tens of trillions every second, perhaps a very special feeling has begun to settle within your mind. It is a feeling shared by many astronomers. The more we discover, the more we realize how much remains unknown. Perhaps that is one of science's greatest gifts. Not certainty, but humility. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, "The more unconscious we are of ourselves, the more we will experience the world as outside." Jung was speaking about the journey inward. Yet, in another sense, those words also invite us to reflect upon our journey outward into the universe. Each time humanity discovers another answer, we realize there are still deeper layers waiting to be understood. Tonight, we enter the most mysterious territory in modern astronomy. No longer the realm of stars, no longer the realm of planets, but the realm of things we cannot see, yet which appear to shape the entire universe. If you stepped outside beneath a cloudless night and looked upward, seeing thousands of stars scattered across the heavens, you might naturally believe you were seeing most of what exists. It is an understandable feeling. Human beings instinctively trust their eyes. Where light reaches, the world seems to end. Modern physics, however, tells a different story, one that astonished even the scientists who uncovered it. According to today's cosmological models, built from many different kinds of astronomical observations, everything we ordinarily recognize as matter, every star, every planet, every galaxy, every nebula, every human being, every atom of ordinary matter, accounts for only about 5% of the universe's total mass energy content. Everything else appears to belong to things we have never directly observed. One of those mysterious components is called dark matter. The name dark matter sometimes leads people to imagine some mysterious black substance drifting between galaxies. But the name can be misleading. It is not necessarily dark in the sense of color. It is called dark because it has never been directly observed through emitting, reflecting, or absorbing light in the way ordinary matter does. When a planet reflects sunlight, we see it. When a star emits light, we see it. Dark matter behaves differently. To this day, we have never directly observed its microscopic nature. We know of its existence only through the gravitational influence it appears to exert. It is rather like the wind. You cannot see the wind itself, yet you know it is there because the leaves begin to move. Or like invisible currents beneath the surface of a lake. You cannot see the flowing water, yet the ripples reveal that something beneath the surface is moving. Dark matter is much the same. We cannot see it, but galaxies appear to move as though they contain far more mass than the luminous matter we observe. One of the first scientists to present compelling evidence for this idea was the astronomer Vera Rubin. During the 1970s, she carefully measured how stars orbit within many spiral galaxies. Based on ordinary matter alone, astronomers expected stars far from the galactic center to move much more slowly, just as planets farther from the sun orbit more slowly than those closer in. Yet observations revealed something quite different. The stars in the outer regions of galaxies continued moving much faster than expected. It was rather like swinging a stone tied to a string. If the string were too weak, the stone would fly away. Yet galaxies somehow continued holding together, as though an enormous amount of invisible mass were quietly helping to keep them intact. This became one of the strongest reasons scientists concluded that some as yet unidentified form of matter exists throughout and around galaxies. Today, galactic rotation curves are only one part of the evidence. Gravitational lensing, observations of the universe's large-scale structure, and several other independent measurements all strengthen the modern dark matter model. One important point is worth remembering. Dark matter represents a scientific model strongly supported by many observations. Yet if dark matter truly consists of undiscovered particles, those particles themselves have not yet been conclusively identified. That is why laboratories around the world continue searching with remarkable patience. Perhaps the greatest beauty of this story lies not in dark matter itself, but in humanity's attitude toward the unknown. Science never says, "We already know everything." Instead, science says, this is what our observations currently suggest. We will continue testing, questioning, and searching. There is something deeply humble about that approach. It recalls the path Jung so often encouraged. He never urged people to rush toward easy answers simply to fill empty spaces. He believed that maturity sometimes begins with the willingness to live alongside unanswered questions. The poet, Rainer Maria Rilke, once wrote in Letters to a Young Poet, "Be patient toward all that is unsolved in your heart and try to love the questions themselves." Although those words belong to Rilke rather than Jung, their spirit feels beautifully aligned with the way science moves forward. Some questions require many generations before humanity can move even a little closer to an answer. And perhaps that journey itself is one of knowledge's greatest forms of beauty. If you gently close your eyes now, imagine the entire Milky Way galaxy slowly turning within the darkness. Hundreds of billions of stars, immense clouds of glowing nebulae, planets that have never been given names. And surrounding them all, perhaps an invisible component we have never directly seen, yet which appears to help shape the motions of the entire galaxy. There is something profoundly poetic about that thought. Some of the universe's most important ingredients do not shine. Not everything must become visible before it can be real. Perhaps the human soul is much the same. The qualities that truly shape a person, kindness, patience, compassion, and love, cannot be measured by light or color, yet they quietly help keep our lives in stable orbits, much as dark matter appears to help galaxies remain together across the vastness of space. As that thought settles gently into the quiet of the night, we are ready to step one stage deeper into an even greater mystery. If dark matter astonishes us because it appears to help prevent galaxies from drifting apart, then what comes next carries us into an even deeper unknown, a mystery involving not merely stars, not merely galaxies, but the destiny of the entire universe. For centuries, humanity shared one very natural intuition. The greatest mysteries of the universe continued. For centuries, people shared one very natural intuition. If gravity is always pulling things together, then after the Big Bang, the expansion of the universe should gradually slow down. That seems perfectly reasonable. Imagine throwing a ball high into the sky. At first, it rises rapidly, but gravity steadily slows it down. Many astronomers once believed the universe would behave in much the same way. Then, toward the end of the 20th century, observations of extremely distant type Ia supernovae produced a result that astonished the scientific community. The universe was not merely expanding, its expansion appeared to be accelerating. It was as though the ball did not slow down at all. Instead, it kept moving faster and faster. That discovery transformed almost everything we thought we knew about modern cosmology. To describe this phenomenon, scientists use the term dark energy. The important thing to understand is this: dark energy is not a mysterious black fluid filling space, nor is it a mystical source of energy in the sense often imagined in science fiction. Rather, it is the name given to a component of today's cosmological models that accounts for the observed, accelerated expansion of the universe. In other words, we have given a name to a phenomenon whose underlying physical nature is still not fully understood. According to the current standard model of cosmology, if the model continues to be confirmed by future observations, dark energy makes up roughly 68% of the universe's total mass energy content. That means most of what appears to govern the evolution of the universe remains something we cannot yet fully explain. There is something wonderfully strange about that. After thousands of years spent studying the heavens, after centuries of modern physics, humanity still lives within a universe whose largest components remain mysterious. Yet rather than discouraging us, that realization carries a quiet beauty. It reminds us that science is not a book that has already been finished. It is a story that is still being written. Carl Gustav Jung once wrote, "Knowledge rests not upon truth alone, but upon error also." It is a beautiful thought to carry with us while reflecting upon the history of science. Each generation builds its understanding from what proves to be true, and also from ideas once believed to be true, but later refined or corrected. Science advances precisely because it is willing to acknowledge its mistakes. Perhaps the same is true of human growth. No one discovers who they truly are if they are afraid to change the way they see the world. If dark matter and dark energy remind us how much remains unknown, another question naturally follows. How much of the universe can we actually see? When we gaze into a sky filled with stars, it often feels as though we are looking into infinity. Modern physics tells a more subtle story. Astronomers often speak of the observable universe. This is not the entire universe. It is simply the region from which light, or other signals, has had enough time to reach us since the universe became transparent to light. Because light travels at a finite speed, and because the universe is approximately 13.8 billion years old, according to current cosmological models, there is therefore a natural limit to what we can directly observe. An especially fascinating detail is that the radius of the observable universe is not merely 13.8 billion light-years. While the light has been traveling toward us, space itself has continued expanding. Current estimates place the radius of the observable universe at roughly 46 billion light-years, giving it a diameter of approximately 93 billion light-years. Numbers so immense they almost escape imagination. Even if you could travel at the speed of light every second, it would still take tens of billions of years simply to cross the observable portion of the universe. And, perhaps even more astonishing, no one knows with certainty what lies beyond that horizon. Perhaps the universe continues indefinitely. Perhaps it is finite, yet unimaginably vast. Or perhaps its structure is far more complex than we currently imagine. Science is still searching. There is something deeply beautiful about that limit, not because it restrains us, but because it reminds us that human observation always has a horizon. Jung believed that ordinary consciousness represents only a small part of the human psyche. Beneath it lies the personal unconscious, and deeper still, the collective unconscious. It is important to remember that this is a psychological model, entirely separate from the cosmological models used to describe the universe. Yet both invite us toward a remarkably similar feeling, that what we see has never been the whole picture. Some things lie beyond our sight, not because they do not exist, but because we have not yet developed the means to perceive them. Perhaps that is the greatest gift the night sky offers humanity. It does not simply provide answers. It teaches us how to ask questions. Each time our telescopes become more powerful, each time another spacecraft is launched, each time astronomers discover another distant galaxy, the horizon of knowledge expands just a little farther. Yet at the very same time, we also realize how much still remains unknown. Perhaps true maturity does not lie in eliminating every mystery. Perhaps it lies in learning to live peacefully alongside them. Jung repeatedly suggested that human beings do not need to control everything in order to live meaningful lives. Sometimes accepting that there are still regions of darkness beyond our understanding is itself a sign of wisdom. The universe teaches exactly the same lesson, not through words, but through its vastness. As you lie quietly here in your peaceful room, it is easy to forget that Earth is only a tiny point within the solar system. The solar system is only a small corner of the Milky Way galaxy. The Milky Way is only one among hundreds of billions of galaxies within the observable universe. And even that observable universe may itself be only part of something even greater. Rather than making us feel insignificant in a painful way, that thought carries a quiet gentleness. It reminds us that we do not have to carry the entire universe upon our shoulders. We do not need answers for every question. Even the universe continues keeping some of its own secrets, and perhaps it is precisely those mysteries that allow the journey of discovery to continue. Allow your mind to rest within that feeling, like a traveler pausing beneath a sky filled with stars. There is no need to walk faster, no need to understand everything. only to know that you are part of a story far larger than yourself. If the universe were an enormous book, then the cosmic microwave background would be one of its oldest surviving pages. The remarkable thing is that we do not have to imagine it. We can actually observe it. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with atomic nuclei, forming the first neutral atoms, primarily hydrogen and helium. Before that time, light was constantly scattered by charged particles and could not travel freely. Once neutral atoms formed, light was finally able to move almost unhindered through space. That ancient light has continued its journey ever since. As the universe expanded, its wavelength stretched from visible light into the microwave region of the electromagnetic spectrum. That ancient radiation is what we now call the cosmic microwave background, or CMB. In 1965, physicists Arno Penzias and Robert Wilson discovered this signal almost by accident while calibrating a radio antenna. No matter where they pointed the instrument, a faint background hiss remained. At first, they suspected a problem with the equipment. They checked the electronics. They checked the atmosphere. They even cleaned pigeon droppings from inside the antenna. Yet the mysterious signal remained. Eventually, they realized they were listening to one of the oldest surviving echoes of the universe itself. There is something profoundly moving about that story. Sometimes the discoveries that reshape science do not begin with thunder. They begin with an almost imperceptible signal, with the patience to listen carefully to what others might dismiss as mere noise. Carl Gustav Jung once wrote, "Your vision will become clear only when you can look into your own heart. Who looks outside dreams. Who looks inside awakes." Jung was speaking about the inner world. Yet science quietly teaches a similar lesson. Sometimes the greatest discoveries come not from seeing more, but from learning to observe more carefully what has always been there. When that first light was finally free to travel through space, an entirely new chapter in the universe began. The first atoms appeared, mostly hydrogen, some helium, and a tiny amount of lithium. It is remarkable to imagine how simple the early universe truly was. There was no oxygen for us to breathe, no carbon from which life would one day emerge, no iron flowing through human blood, no calcium within our bones. None of the familiar elements that now surround us had yet come into existence. And yet, from that astonishing simplicity, all later complexity gradually unfolded, like a magnificent symphony beginning with only a handful of quiet notes, or an immense forest growing from a single tiny seed. Perhaps nature has always loved simplicity. Its most intricate structures are often built from the simplest beginnings. Then hundreds of millions of years passed. Under the pull of gravity, vast clouds of hydrogen and helium slowly collapsed. The first stars were born. Deep within their cores, temperatures and pressures rose high enough for nuclear fusion to begin. Hydrogen fused into helium. Helium helped create carbon, then oxygen, neon, silicon, and eventually, within stars massive enough, iron. It is one of the most beautiful stories physics has ever told. The chemical elements did not all appear at once. They were forged across many generations of stars, each generation leaving behind the raw materials for the next. In that sense, the stars truly became the great forges of the universe. Carl Sagan expressed this beautifully in one of his most famous reflections: the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, were made in the interiors of collapsing stars. Every time one reads those words, it is difficult not to pause in quiet wonder. The greatest mysteries of the universe continued. It is difficult to read those words without falling into a quiet sense of wonder, because they almost erase the distance between humanity and the stars. We are not merely living beneath the sky. We are made from the very history of the sky itself. Yet, there remains an entire family of elements that even ordinary stars cannot easily produce. Among them, gold. For thousands of years, gold has been a symbol of value. We wear it on our hands. We keep it in vaults. We shape it into works of art. Yet very few people ever stop to ask, where did gold come from? Today, astronomical observations and models of nuclear astrophysics indicate that one of the most important sources of many heavy elements is the merger of neutron stars. Imagine two neutron stars orbiting one another. Gradually, they lose energy by emitting gravitational waves. Their orbit slowly shrinks until, at last, they collide. It is one of the most violent events in the universe. Within that extraordinarily neutron-rich environment, a process known as rapid neutron capture, or the R process, can create many of the universe's heaviest elements, including a substantial portion of its gold, platinum, and numerous others. When astronomers observed the neutron star merger GW170817 in 2017, they obtained compelling evidence supporting the idea that such mergers are among the primary cosmic factories responsible for forging these heavy elements, which means a gold ring, a necklace, or any treasured piece of gold jewelry may carry within it a story that began billions of years ago, when two extraordinary stellar remnants collided somewhere in the depths of space. That is a different kind of beauty. No longer the beauty of monetary value, but the beauty of time, the beauty of cosmic history preserved inside every atom. Perhaps this is also the moment we begin to realize something profoundly meaningful. From the cosmic microwave background, to the first atoms, to the first stars, to the chemical elements, to gold itself. Every story follows naturally from the one before it. Like chapters within a single book, no chapter exists alone. Without the early universe, there would have been no stars. Without stars, there would have been no carbon, no oxygen, no life. No human being lying here tonight, listening to this story. Jung devoted much of his life to searching for the invisible threads connecting the symbols that appear within the human mind. Physics searches for invisible threads connecting the phenomena of the universe. Two very different paths, yet both seem to lead toward the same quiet realization. Behind all diversity, there exists a deeper unity. The night has grown very late. Perhaps your breathing has become slower than when our journey first began. If so, carry with you one final image before we continue. Imagine the entire history of the universe as one immense river. At its source, the first light, a little farther downstream, the first atoms, then the first stars, the first galaxies, supernova explosions, neutron star mergers, heavy elements, planets, oceans, life, and finally, you, not standing outside that river, but existing as one small yet genuine part of its endless current. Perhaps that is the most beautiful gift science and quiet contemplation can offer together. Not the feeling that humanity is the center of the universe, but the feeling that we truly belong within it. And as that thought gradually dissolves into the silence of the night, our journey now leads us to the next chapter. A place both awe-inspiring and mysterious. A place where space, time, and light themselves bend in ways that challenge nearly every intuition human beings have ever possessed. Black holes. Now that we have finished our story of the first atoms, of the ancient light still echoing from the dawn of the universe, and of the gold atoms forged during neutron star mergers billions of years ago, perhaps another feeling has begun to grow quietly within you. It is no longer merely curiosity, it is reverence. The more we learn about the universe, the more we realize that nature never needs to announce its greatness. A single tiny atom may carry billions of years of history. A faint ray of light may still be telling the story of the universe's earliest moments. And now, we arrive at one of the most mysterious places science has ever explored. A place that has become a symbol of the unknown. A place that has carried human imagination farther than almost any other object in the cosmos. The black hole. The name alone stirs countless emotions. In films, black holes are often portrayed as gigantic cosmic abysses that swallow everything passing nearby. endless cosmic vacuum cleaners, doorways from which nothing can ever return. These images are undeniably captivating. Yet the true physics is even more subtle, and, in many ways, even more beautiful. Carl Gustav Jung once wrote in Psychology and Alchemy, "The greatest and most important problems of life are all fundamentally insoluble. They can never be solved, but only outgrown." Perhaps black holes resemble one of those great mysteries. Each time humanity believes it has finally understood them, another deeper layer of reality reveals itself. Not because black holes deliberately hide their secrets, but because our intuition evolved within a world utterly unlike the extreme conditions where these extraordinary laws of nature unfold. The first misunderstanding most people have about black holes is this: black holes suck everything in. At first, that sounds perfectly reasonable, but from the perspective of physics, it is not quite accurate. A black hole does not pull on distant objects with some mysterious new force simply because it is a black hole. Outside the object, gravity depends primarily upon its mass. Imagine a simple thought experiment. Suppose, by some miracle of physics, the sun were suddenly transformed into a black hole, while keeping exactly the same mass it has today. What would happen to the Earth? Many people imagine that our planet would immediately spiral inward and disappear into the black hole. Yet the true answer is remarkably different. According to general relativity and the laws of orbital mechanics, Earth would continue orbiting that black hole in almost exactly the same path it follows around the Sun today. No new gravitational force would suddenly appear simply because the Sun had become a black hole. The greatest change would be something else entirely. There would be no more sunlight, no more warmth, no more sunrise, no more golden afternoons. Life on Earth would face catastrophic consequences because it had lost its source of energy, not because the planet was instantly swallowed. That truth makes black holes far stranger than our imagination first suggests. They are not cosmic vacuum cleaners. They simply obey the laws of gravity, but at one of the most extreme limits the universe has ever produced. So what truly makes a black hole unique? The answer lies in a concept known as the event horizon. Imagine standing on the bank of a very wide river. Near the shore, the current is gentle. You could easily swim against it. But the farther you move toward the center, the faster the water flows. Eventually, you reach a point where the current becomes so powerful that, no matter how hard you swim, you can never make it back. Of course, this is only an analogy. Inside a black hole, there is no rushing river. Instead, it is the very fabric of space-time that becomes so profoundly curved that, once the event horizon has been crossed, every possible path into the future leads deeper inward. Seen from the outside, the event horizon is not a wall. There is no doorway, no glowing boundary, no warning light. If a sufficiently large spacecraft approached a supermassive black hole, theory suggests that the astronauts might not notice the precise instant they crossed the event horizon through any local physical sensation. What makes the event horizon extraordinary is not its appearance. It is that once this boundary has been crossed, even light can no longer carry information back to distant observers. That is why it is called a horizon. Not because it is the universe's final wall, but because it marks the limit beyond which no signal can return to the outside world. There is a strangely beautiful idea hidden within that thought. Even light, humanity's oldest symbol of knowledge and understanding, has places from which it cannot return. Yet science does not stop there. Quite the opposite. Because we cannot look directly inside a black hole, we have learned to listen to the traces it leaves behind. We observe stars orbiting an invisible object. We observe brilliant disks of hot gas glowing as matter spirals around a black hole. We observe the gravitational waves released when two black holes merge. It is rather like an archaeologist who can no longer see an entire ancient city, yet reconstructs its story from the stones that remain. Perhaps Jung would have appreciated that image. He spent much of his life studying symbols, dreams, and the subtle traces left by the unconscious within conscious experience. He never assumed that what could not be seen therefore did not exist. Sometimes, the invisible leaves the clearest footprints. Modern physics approaches black holes in much the same way. We do not see the black hole itself shining. We see how it quietly transforms everything around it. Perhaps this is the first lesson black holes offer us. Do not trust intuition too quickly. Some ideas that seem perfectly obvious turn out not to be entirely true. A black hole is not a monster endlessly swallowing everything nearby. It is an extreme solution to the equations of gravity, where space-time becomes so profoundly curved that the familiar rules governing everyday life are no longer sufficient to describe reality. That does not make the universe more frightening. Quite the opposite. It makes it more subtle, more beautiful, more profound. Much like the human soul, the things that matter most rarely exist only on the surface. They usually reside in deeper layers that reveal themselves only through patience and humility. A moment ago, we stood at the threshold of the event horizon, where even light can no longer carry news back to the outside universe. Now let us take one step farther, not with our feet, but with our imagination. Picture yourself far away from a supermassive black hole. In the stillness of space, a spacecraft begins drifting slowly toward it. Every instrument aboard continues functioning perfectly. The clocks continue ticking. The lights remain on. The astronauts speak with one another just as they always have, from their own perspective. Nothing unusual seems to be happening. Yet if you were watching from an immense distance through a telescope powerful enough to see every detail, the story unfolding before your eyes would be entirely different. One of the most beautiful and perhaps strangest predictions of general relativity is this: time does not pass at the same rate everywhere. We encountered this idea earlier when discussing GPS satellites. Near a black hole, however, the effect becomes vastly stronger. According to Einstein, gravity does not merely curve space, it also curves time. This means that the closer a clock is to an extremely powerful gravitational field, the more slowly it ticks relative to a clock located far away. This is not an illusion. The clock is not malfunctioning. It is a genuine property of space-time itself. If two extraordinarily precise clocks were placed in regions with different gravitational fields and later brought together for comparison, they would show different amounts of elapsed time. Experiments using atomic clocks have confirmed precisely this effect. Although in gravitational fields, vastly weaker than those surrounding black holes, a black hole simply carries the phenomenon to one of nature's most extreme limits. Imagine the astronaut aboard the spacecraft looking down at the watch on their wrist. 1 second remains 1 second. 1 minute remains 1 minute. Their heartbeat stays steady. Their breathing remains calm. From their own point of view, time continues flowing normally. But for an observer watching from far away, that same clock appears to tick more and more slowly. Every movement aboard the spacecraft seems increasingly sluggish. The light arriving from the spacecraft becomes progressively redder because of gravitational redshift. If we ignore many practical complications and consider the idealized description from the viewpoint of a distant observer, the spacecraft appears to approach the event horizon ever more slowly, never quite seeming to cross it. It sounds almost impossible, yet this is exactly what Einstein's equations predict. Of course, the experience of the astronaut is different. If the black hole is sufficiently massive that tidal forces at the event horizon are not overwhelmingly strong, the falling observer may pass through the event horizon without encountering any physical wall at that precise moment. This is one of relativity's most fascinating features. Two observers, two different perspectives, both entirely correct within their own frames of reference. There is no contradiction, only a reality richer than ordinary intuition suggests. That realization has led many people to imagine time as a flowing river, yet perhaps even that image is incomplete. In a letter of condolence to the family of his friend Michele Besso, Einstein famously wrote, "For us believing physicists, The distinction between past, present, and future is only a stubbornly persistent illusion. It is one of his best-known reflections. He did not mean that time does not exist. Rather, he was suggesting that our everyday experience of past, present, and future may not fully capture the deeper structure of space-time described by physics. Perhaps this is why black holes inspire both awe and humility. They gently compel us to let go of some of our most familiar intuitions. Carl Gustav Jung never studied black holes, nor did he write about relativity, yet he devoted his life to contemplating another kind of time, the time of the soul. Some memories last only a few seconds, yet remain with us throughout an entire lifetime. Some years seem endlessly long while we are living them, yet, when we look back, they feel no more substantial than a dream. Physical time and psychological time are two entirely different ideas. One is measured by clocks. The other is measured by experience, and yet both quietly remind us of the same truth. Time is not always experienced in the same way. Perhaps that is why peaceful evenings feel so different. When life's pace begins to slow, when the phone has finally been switched off, when only the soft whisper of a fan remains in the room, an hour can suddenly feel wonderfully long enough for someone to reflect upon an entire lifetime. If time itself flows differently near a black hole, perhaps that can also help us look upon our own lives with greater gentleness. We spend so much time hurrying, worrying that today was not enough, fearing that we are falling behind everyone else. Yet the universe seems entirely unfamiliar with haste. A galaxy requires hundreds of millions of years to complete a single rotation. A star may live for billions of years. A black hole can patiently endure longer than almost every civilization humanity has ever known. Measured against such timescales, one human day is astonishingly brief, and perhaps that is exactly why it is so precious. Jung often reminded us that maturity is not found in moving faster. It is found in becoming more conscious of one's own journey. Physics does not teach us how to live, yet sometimes it allows us to see life from a different scale, a scale upon which problems that once seemed enormous quietly become smaller, and ordinary moments become infinitely more worthy of gratitude. As you lie here in the stillness of the night, the clock upon your wall is probably continuing its steady rhythm, second by second, minute by minute, beat by beat. Yet somewhere, near a supermassive black hole in a distant galaxy, another clock may be keeping time to an entirely different rhythm. Neither clock is wrong. Each is simply telling the story of space-time in a different part of the universe. There is something deeply beautiful about that thought. Time is not a tyrant. It is more like a piece of music. Every corner of the cosmos plays its own melody, and together, those countless melodies create the great symphony of the universe. Let that thought settle gently within you, like light drifting quietly across the endless darkness. After spending so long together at the edge of the event horizon, where even light cannot return, perhaps another feeling has begun to emerge. A black hole seems like the ultimate symbol of an ending, a place where every journey comes to a stop, a doorway with no path back. For many decades, even physicists believed something similar. If light could never escape, if all matter remained trapped forever, then a black hole must surely be perfectly black, eternal, unchanging, forever silent. But then, during the 1970s, a young British physicist asked a remarkably bold question. What would happen if we looked at a black hole not only through Einstein's general relativity, but also through quantum mechanics? That physicist was Stephen Hawking, and the answer he discovered became one of the most beautiful ideas in modern physics. The first thing to understand is this: even today, Hawking radiation remains a theoretical prediction. It emerges from combining ideas from quantum mechanics with the curved space-time surrounding a black hole under appropriate theoretical approximations. Its mathematical foundations are exceptionally strong, and it continues to be studied extensively throughout the physics community. However, Hawking radiation has not yet been directly observed from astrophysical black holes, because the predicted signal is extraordinarily weak for black holes with stellar masses or greater. That distinction is important. Science always distinguishes between what has been directly observed and what has been inferred from successful theoretical models. Perhaps that careful honesty is one of science's greatest forms of beauty. So what exactly is Hawking radiation? Imagine the surface of a calm ocean late at night. At first glance, the water appears perfectly still, but if you look more closely, tiny ripples are constantly appearing and fading away. According to quantum mechanics, what we call a vacuum is not truly empty. Quantum fields continue to exist even in their lowest energy state, and those fields exhibit fluctuations. This is a profoundly different idea from our everyday intuition. It does not mean that real particles are literally popping into and out of existence in the simple way often described in popular science. Instead, the familiar language of virtual particle pairs serves as an intuitive picture that helps illustrate certain aspects of quantum field theory. It should not be interpreted literally as tiny particles continually springing from empty space. What Hawking demonstrated was something subtler. When quantum effects are considered near the event horizon, the quantum state of the field can lead a distant observer to detect a stream of thermal radiation emerging from the black hole. The remarkable conclusion is this: a black hole is not completely black. According to theory, it possesses a temperature, and it can radiate. There is something wonderfully beautiful about that idea. An object once believed to imprison everything forever can, in a sense, glow, even if that glow is so faint that it is almost impossible to detect. This does not mean that light is escaping from deep inside the black hole. In Hawking's description, the radiation arises from quantum effects occurring near the event horizon itself, not from matter somehow climbing back out from the interior. That distinction is subtle, yet it is precisely what makes modern physics so captivating. Nature rarely behaves according to our first intuition. Another fascinating consequence of Hawking radiation follows naturally. If a black hole continuously emits energy as radiation, then according to Einstein's famous relationship between energy and mass equals, it must gradually lose an extraordinarily small amount of mass. In other words, according to theory, a black hole is not perfectly eternal. It can slowly evaporate. For the enormous black holes known throughout astronomy, however, the predicted evaporation time is vastly longer than the present age of the universe. That means there is no reason to worry that the black hole at the center of the Milky Way will disappear tomorrow, or even billions of years from now. Yet the simple realization that even black holes may not be absolutely permanent changes the way we think about the universe. Perhaps nothing stands completely outside the flow of time. Carl Gustav Jung once wrote, "Everything that irritates us about others can lead us to an understanding of ourselves." He was speaking about psychology. Yet it is intriguing to notice that many of the ideas that have puzzled physicists most deeply are precisely those that have opened entirely new horizons of knowledge. Black holes were once regarded as the place where physics came to an end. Instead, they became the place where general relativity and quantum mechanics are forced into conversation. The two great pillars of modern physics have still not been completely unified, and black holes remain one of the places where that incompleteness becomes most apparent. That makes a black hole far more than an astronomical object. It becomes an invitation to continue asking questions, to continue learning, to continue accepting that what we understand today may be only one chapter of a much larger story. Perhaps that is Stephen Hawking's greatest legacy. Not merely his equations, not merely his scientific papers, but his unwavering curiosity about the unknown. He once wrote in Black Holes and Baby Universes and other essays, "My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists at all." That was not only the goal of a physicist. In another sense, it has always been one of humanity's oldest longings, to understand where we are, to understand why anything exists at all, to discover whether our own lives hold meaning beneath these immense skies. Perhaps Jung would say that this journey does not lead only outward, it also leads inward, because every time we expand our understanding of the universe, we also expand the boundaries of our own minds. Now that the night has become wonderfully quiet, imagine an immense black hole resting silently in the depths of space. No longer the monstrous force that swallows everything, as so often portrayed in films, but a mysterious celestial object where the deepest ideas of Einstein and Hawking quietly meet, a place where even darkness itself proves far more subtle than we once imagined. And in the next chapter of our journey, we will leave behind the frontier where gravity and quantum theory intersect. Instead, we will travel closer to the very heart of our own galaxy, Sagittarius A, the supermassive black hole at the center of the Milky Way. There, millions of stars silently orbit an invisible object, as though the entire galaxy were engaged in a slow and graceful dance around one of the universe's oldest secrets. Now that we have stepped away from Stephen Hawking's extraordinary ideas, where even black holes may not be entirely immutable according to modern theoretical models, perhaps you find yourself wondering, do these strange objects truly exist somewhere out there? Or are they simply elegant mathematical ideas written upon paper? The answer is wonderfully simple. They are real, and even more remarkable, one of them resides within the very galaxy we call home. If, on a truly dark night, you leave behind the lights of the city and lift your eyes toward the heavens, you will see a faint river of light stretching across the sky. That is the Milky Way. Hundreds of billions of stars together create that gentle band of pale light. Across countless ancient cultures, people gave it names filled with poetry. Some called it the River of the Gods. Others believed it was the pathway along which souls return to the heavens. Today, science tells us that this luminous band is a spiral galaxy, the home of our solar system. Yet at the very center of that galaxy, hidden behind immense clouds of gas and dust, lies an object that is almost completely invisible, a supermassive black hole. Astronomers call it Sagittarius A, usually pronounced Sagittarius A star. For many years, we could not observe Sagittarius A times directly, not because our telescopes were too weak, but because a black hole does not emit light the way a star does. What astronomers could observe were the stars surrounding it. Imagine walking into a crowded town square. At the very center stands an invisible person. You cannot see them, yet everyone around them is racing in tight circles around a single point. Simply by watching those motions, you would know that something must occupy the center, something powerful. That is exactly how astronomers first confirmed the existence of Sagittarius A. For decades, they patiently tracked the orbits of stars extremely close to the center of the Milky Way, especially one famous star known as S2. S2 completes an orbit in only about 16 years. Near its closest approach, it races through space at thousands of kilometers per second. Only an object of enormous mass, concentrated within an extraordinarily small region, could hold a star in such an orbit. From those precise measurements, scientists concluded that the center of the Milky Way contains a black hole with a mass of approximately 4 million suns. The remarkable thing is this: we do not see the black hole itself. We see the way an entire region of space moves because of its presence. There is something in that story that feels deeply familiar. Not everything that exerts the greatest influence is easy to see. Some people quietly change another person's life. Some words are spoken only once, yet remain in memory for years. Some memories are no longer visible, yet they continue shaping the way we love, choose, and grow. Jung devoted much of his life to studying the invisible forces within the human mind. Not because he believed in mystery for its own sake, but because he understood that unseen things can produce very real movements. Sagittarius A times does much the same. It does not need to shine. It does not need to announce itself. it remains the gravitational heart of our galaxy. In 2022, humanity reached a remarkable milestone. The Event Horizon Telescope collaboration released the first image of the region surrounding Sagittarius A. What we often call a picture of a black hole is not actually a photograph of the black hole itself. A black hole emits no light for a camera to capture. Instead, the image reveals the glowing hot gas surrounding the black hole, together with the dark central region commonly known as the black hole shadow. That shadow appears because light is bent so dramatically within the immense gravitational field near the black hole. It was an achievement made possible through the collaboration of hundreds of scientists around the world. Radio telescopes located on different continents worked together as though they formed a single telescope nearly the size of Earth itself. There is something profoundly beautiful about that. Humanity could not observe the black hole alone, but by working together, sharing data, sharing ideas, remaining patient, we came one step closer to understanding one of the universe's greatest mysteries. Carl Gustav Jung once wrote, "The meeting of two personalities is like the contact of two chemical substances. If there is any reaction, both are transformed." Jung was speaking about people, yet science often grows in much the same way. Each new idea encounters a new observation. Each new telescope meets an old question. Each generation of scientists continues the conversation begun by those who came before. It is through those countless encounters that humanity's understanding slowly grows, not through endless dramatic breakthroughs, but through innumerable quiet, patient steps. Perhaps the most beautiful thing about Sagittarius A times is not its immense size, nor its extraordinary mass, nor the records it holds. Its greatest gift is something else. It reminds us that even at the center of a galaxy spanning more than 100,000 light-years, there are still mysteries humanity continues to explore. The universe continues expanding. Knowledge does too. Every answer opens another door. Every discovery leaves us more humble before the vastness of reality. Perhaps that is the greatest gift black holes offer the human mind. Not fear, but reverence. Not helplessness, but wonder. A very quiet wonder. A very gentle wonder. Like standing before the ocean at sunrise. You know how small you are, yet you never feel alone, because you understand that you belong within that immense picture. The night has now reached its quietest hours. Perhaps your breathing has become slower. Perhaps your eyelids are beginning to grow heavy. If so, allow one final image to remain gently within your thoughts. Imagine the Milky Way turning slowly through the darkness. Hundreds of billions of stars moving in silence. At its center, Sagittarius A times remains quietly present. It emits no light. It says nothing. Yet through gravity alone, it helps shape the motion of countless stars near the galactic center. Much like the most meaningful things in our own lives, they need not be loud to matter. They need not be seen to truly exist. Perhaps that is also what Carl Jung wished to remind us through his lifelong exploration of the deeper layers of the human psyche. Not every truth lives upon the surface. Some reveal themselves only when we slow down enough to observe, become quiet enough to listen, become humble enough to accept that the universe will always be larger than our imagination. And in the next chapter, we will leave black holes behind and widen our view to encompass entire galaxies. Immense islands of light drifting through space, colliding, merging, and together weaving the magnificent structure of the universe we call home. Galaxies, leaving behind the quiet darkness surrounding Sagittarius A, where even light must yield to gravity's immense power. We once again lift our eyes toward the night sky. Perhaps, after everything we have explored together, the heavens no longer look quite the same as they did when our journey began. The stars are no longer merely distant points of light. They have become witnesses to time itself. The atoms within our bodies were born inside stars that died long ago. The light reaching your eyes tonight began its journey long before many civilizations on Earth ever came into being. And even the black hole, once imagined as the ending of every story, has instead opened entirely new questions about the nature of space, time, and reality. Yet there is something even more astonishing. Even galaxies themselves, those vast cities containing hundreds of billions of stars, never stand still. As children, many of us imagined the night sky as a painting. The stars seemed permanently attached to an enormous black canvas. Night after night, they appeared unchanged. Any movement was far too slow for human eyes to notice. Yet science has gradually revealed a completely different reality. The universe is not a painting. It is more like a symphony. No note remains perfectly still. No silence remains forever unchanged. Everything is moving. Everything is participating in an immense cosmic dance that has continued for billions of years. Our own Milky Way is no exception. If you could leave Earth behind and travel far enough to view our galaxy from the outside, you would not see a motionless spiral. You would see a magnificent spiral structure stretching roughly 100,000 light-years across, slowly turning within the darkness of space. Hundreds of billions of stars, immense clouds of gas, brilliant glowing nebulae, young star clusters just beginning their lives, ancient stars approaching their final days. Everything circles the galactic center. Our own sun is part of that journey, traveling at roughly 220 kilometers per second. The solar system orbits the center of the Milky Way. Although that speed is extraordinary by everyday standards, one complete orbit still requires approximately 225 to 250 million years, which means the last time the Sun occupied exactly its present location within the Milky Way, the dinosaurs had not yet appeared. One galactic year is so immense that the entire history of humanity occupies only a tiny instant within it. Sometimes, simply changing our scale of time changes the way we see our worries. A single day can feel endless while we wait. A single year can pass quickly when we are happy. But 200 million years is almost beyond the reach of imagination. Perhaps that is why looking into the night sky leaves us feeling both wonderfully small and strangely comforted. The things that concern us today are still important, but they are not the whole story. Out there, the Milky Way continues turning quietly, never rushing, never hesitating, never stopping. Carl Gustav Jung once wrote in The Structure and Dynamics of the Psyche, "There is no coming to consciousness without pain." He was speaking about the growth of the human soul. Yet, those words also evoke a beautiful image when we look at the universe. No galaxy matures without countless transformations. No star is born without clouds of gas collapsing under gravity. No planet forms without millions of years of collisions, accumulation, and continual reshaping. Nature does not fear change. Quite the opposite. Change is the way the universe creates. Perhaps the human mind is much the same. The experiences we once wished to avoid often become the very places where a deeper version of ourselves first begins to emerge. But the Milky Way's journey is more than simply rotating around its own center. The entire galaxy is also traveling through space. It belongs to a small collection of galaxies known as the Local Group, a gravitationally bound family of more than 50 large and small galaxies. Within that family lives one very special neighbor, the Andromeda Galaxy. If you have ever seen what looks like a faint, misty patch in the night sky, there is a good chance you are looking at Andromeda, the most distant, large galaxy that can be seen with the naked eye beneath sufficiently dark skies. Its light requires about 2.5 million years to reach Earth, which means that when you look at it tonight, you are looking deep into the past. That light began its journey long before modern human beings existed on Earth. Time and distance are forever woven together throughout the universe. To observe space is also to observe history. There is something especially fascinating about Andromeda. Unlike most distant galaxies, it is not moving away from us. Because of the mutual gravitational attraction between the galaxies of the Local Group, Andromeda is slowly approaching the Milky Way. At first, that may sound alarming. two enormous galaxies racing toward one another. Yet the universe is not a crowded highway. The distances separating individual stars inside each galaxy are so immense that, even when the galaxies eventually merge, the chance of two stars colliding directly remains extraordinarily small. What will change most dramatically is the overall shape of the galaxies themselves as gravity gradually reshapes them. It will not be a violent explosion lasting a few minutes. It will be a dance lasting billions of years, a process so slow that, if you could witness it, you would notice beauty far more than destruction. Perhaps this is one of the quiet lessons nature continually whispers to us. The greatest transformations rarely happen with noise. They happen with patience. A seed becomes a tree. A child becomes an adult. A mountain is slowly worn away by the wind. A galaxy changes its form. Everything requires time. A great deal of time. Perhaps that is why Jung always regarded human growth as a journey rather than a single moment. The self does not awaken overnight, just as a galaxy does not change after only one turn through space. Every experience, every encounter, every loss is like one small revolution within the long orbit of the soul, quietly carrying us closer to the person we are capable of becoming. And in the next chapter, we will continue following that slow cosmic dance as we witness one of the grandest events astronomers expect to unfold, the future encounter between the Milky Way and Andromeda. From there, we will widen our perspective even further to explore an even stranger truth. Space itself is expanding, and across sufficiently vast distances, that expansion can cause galaxies to recede from one another at speeds greater than the speed of light, without contradicting Einstein's theory of relativity. As we pause before the image of the Milky Way turning silently through the night, perhaps you have already begun to sense a subtle change within yourself. At first glance, the night sky appears perfectly peaceful. The stars are still there. The silver river of the Milky Way stretches quietly across the heavens, just as it has for thousands of years. Yet beneath that calm appearance, the universe has never stopped moving. Galaxies do not merely rotate. Together, they participate in a cosmic dance, lasting billions of years. A dance so slow that no human lifetime can witness it in its entirety, yet so powerful that it reshapes the architecture of the universe itself. In the previous chapter, we met the Milky Way's nearest great neighbor, the Andromeda Galaxy. Its light has traveled approximately 2.5 million years before reaching our eyes, which means that every time we look toward Andromeda, we are seeing it as it was 2.5 million years ago. Not the present, but a preserved slice of the past. It is one of astronomy's greatest wonders. To observe space is also to observe time. Every telescope is, in its own way, a machine for looking backward through history. Modern observations show that Andromeda is approaching the Milky Way at a speed of a little over 100 kilometers per second along our line of sight. Because of the gravitational interaction between the two galaxies within the local group, astronomers predict that they will begin merging roughly 4 to 5 billion years from now. Hearing the word collision may immediately bring dramatic images to mind. Stars crashing into one another, planets being shattered, explosions illuminating the heavens. Yet the true story of the universe is far gentler. The distances separating stars are almost impossible to imagine intuitively. If our sun were no larger than a single grain of sand, the nearest star would still lie tens of kilometers away. Within a galaxy, most of the volume is empty space. So when two galaxies merge, the chance of direct collisions between individual stars is incredibly small. Instead, gravity slowly reshapes the orbits of hundreds of billions of stars. The graceful spiral arms of each galaxy are stretched and distorted. Great rivers of gas and dust become stirred. Entire regions of new star formation may blaze into life. And after billions of years, two separate galaxies become one, not through a single explosion, but through a process that is slow, orderly, and astonishingly beautiful. There is something about that story that feels deeply human. We often fear great changes. We fear losing what is familiar. We fear the closing of one chapter. Yet nature quietly tells another story. Many of life's greatest beauties do not appear because everything remained unchanged. They appear because everything transformed. A forest reborn after fire, a river finding a new course after a flood, a person growing stronger through difficult years, a new galaxy emerging from the meeting of two older ones. Carl Gustav Jung once wrote in Modern Man, In Search of a Soul, "I am not what happened to me, I am what I choose to become." Perhaps that same spirit quietly echoes throughout the universe. It never stops changing, never stops renewing itself, never stops becoming something new. But the story of galaxies leads us toward an even stranger truth. For nearly a century, astronomers have discovered that most distant galaxies are gradually moving away from one another. Not because some ancient explosion is still throwing them through space like scattered stones, but because space itself is expanding. At first, that idea feels difficult to picture. In everyday life, we imagine space as though it were a fixed box. Objects move around inside the box. Yet in modern cosmology, even the box itself can change its size. One familiar analogy is to imagine tiny dots drawn upon the surface of a balloon as it is slowly inflated. As the balloon grows larger, the dots do not crawl across its surface. The distances between them increase because the surface itself is expanding. It is only a two-dimensional analogy to help us visualize the concept. The real universe is not a balloon expanding into a larger surrounding space, but the image helps us grasp the idea that the expansion belongs to space itself. This leads to one of cosmology's most surprising conclusions. Across sufficiently great distances, the separation between two galaxies can increase faster than the speed of light. At first, that seems to contradict Einstein. In fact, it does not. Special relativity tells us that no object carrying information or energy can travel through space faster than light in a vacuum. In the case of extremely distant galaxies, however, what exceeds the speed of light is not the galaxies moving through space. It is the distance between them increasing because space itself is expanding. Those are two entirely different ideas. That subtle distinction is one of the profound achievements of modern cosmology. It reminds us that the intuition we developed while living on Earth is not always sufficient to understand a universe nearly 14 billion years old. Astronomer Carl Sagan once wrote in Cosmos, "We are a way for the cosmos to know itself." Few sentences capture humanity's place in the universe more beautifully. The atoms within our bodies were forged inside generations of ancient stars. Our brains evolved on a small planet orbiting an ordinary star, and yet those very brains are capable of contemplating galaxies millions of light years away. The universe did not merely create stars, it also created beings capable of asking questions about the universe itself. There is something profoundly humbling about that thought. We are small, but we are not insignificant. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, "Who looks outside, dreams. Who looks inside, awakes." Perhaps throughout this journey, we have done both. We have looked outward to witness galaxies turning through space, black holes quietly existing in darkness, and the universe itself continuing to expand. Yet every one of those discoveries has also opened a quiet space within us, a place where we realize that the human mind resembles the universe in its own way, vaster than we once imagined, filled with deeper layers than we ever knew, and always offering new horizons waiting to be explored. The night has become wonderfully still. Perhaps your breathing has slowed. Perhaps your eyelids are beginning to grow heavy. If so, allow one final image to remain gently in your thoughts. Imagine the Milky Way and Andromeda slowly drawing closer across the immense darkness. Never rushing, never chaotic, only a graceful dance unfolding across billions of years, guided by the same laws that have existed since the dawn of the universe. Now imagine something even greater. The entire fabric of space-time quietly continuing to expand. Space itself growing larger, galaxies drifting ever farther apart. the universe continuing to write its own story. Meanwhile, upon a small planet called Earth, one human being slowly closes their eyes, listening to the story of the stars. Perhaps that is the greatest gift science and philosophy can offer together. Not every mystery must be solved today. Sometimes it is enough simply to know that we belong to the story. And as sleep gently carries you deeper into the night, take that quiet feeling with you. Just as galaxies continue moving silently through the cosmos, the human soul always retains the ability to expand, to grow, and to discover new horizons, even within its deepest dreams. Relativity. After following the slow dance of galaxies together, watching the Milky Way and Andromeda gradually approach one another over billions of years, then widening our view to the expansion of space itself, perhaps a very natural question has begun to form. If everything in the universe is moving, is anything truly at rest? Is there some absolute point of reference? An absolute clock? A single flow of time shared by everyone? For thousands of years, humanity believed there was. We naturally imagined time as the current of a river, flowing steadily, never faster, never slower. Whether you stood upon a mountain, sailed across the ocean, or sat quietly inside your room, time seemed to pass exactly the same. Space appeared much the same. It was thought of as a fixed stage upon which every event unfolded. Objects could move across that stage, but the stage itself remained unchanged. That was how Isaac Newton, along with generations of scientists after him, imagined the universe. And for centuries, that picture worked remarkably well. It allowed humanity to calculate the motions of planets, build bridges, navigate across oceans, and launch the Industrial Revolution. Then, at the beginning of the 20th century, a young man working at the Swiss Patent Office in Bern began asking what seemed like an almost childishly simple question. What would happen if I could chase a beam of light? That young man was Albert Einstein. And from that simple question began one of the greatest revolutions in human thought. Einstein did not begin with a giant telescope, nor did he possess a vast laboratory. His greatest instrument was imagination. He often referred to these exercises as Gedankenexperimente, thought experiments. He imagined riding alongside a beam of light. He imagined moving clocks. He imagined trains racing past railway platforms. From those simple mental pictures, he realized something extraordinary. Perhaps it was not the equations that needed changing. Perhaps it was humanity's understanding of space and time themselves. Albert Einstein once wrote, "Imagination is more important than knowledge. Knowledge is limited. Imagination encircles the world." Perhaps imagination, when guided by unwavering honesty toward nature, opened a doorway that had remained unseen for centuries. The foundation of special relativity is, in fact, surprisingly simple. One of its central principles is this: the speed of light in a vacuum has exactly the same value for every inertial observer, regardless of how either the observer or the source of light is moving. Today, that speed is known with extraordinary precision: 299,792,458 meters per second, a number almost beyond imagination. Light can circle Earth more than 7 times in a single second. It takes roughly 8 minutes to travel from the Sun to Earth. Yet it still requires more than 4 years to reach the nearest star beyond our Sunday. That speed is not merely enormous. It serves as one of nature's fundamental limits. Our first intuition naturally asks, if that's true, why can't we simply build faster and faster spacecraft until one eventually reaches the speed of light? It is an entirely reasonable question. Yet nature gives us a very different answer. For every object possessing non-zero rest mass, the closer its speed comes to the speed of light, the more energy is required to accelerate it further. The closer you approach that limit, the greater the required energy becomes. Not merely a little greater. According to special relativity, it grows without bound. Which means, accelerating an object with mass to exactly the speed of light would require an infinite amount of energy. According to our present understanding of physics, that cannot happen. Light is not a finish line that material objects can eventually reach. It is more like the horizon. You can move closer and closer forever, yet you never actually arrive. That fact does not make the universe seem harsh. Quite the opposite. It reveals a profound order. Some limits do not exist to prevent us from exploring. They exist so that the entire structure of reality can remain internally consistent. If information could travel faster than light under all circumstances, the concepts of cause and effect would encounter deep paradoxes in certain reference frames. The speed of light is therefore not merely a number. It is woven into the very fabric of space-time itself. But then another, even stranger question appears. If light always travels at this remarkable speed, what would the universe look like from the light's own point of view? Could we somehow remain at rest beside a beam of light and observe the world through its eyes? This is where ordinary intuition begins to fail. Within special relativity, there is no inertial reference frame associated with light or with a photon. In other words, physics simply does not define a perspective in which a photon is at rest. This is not because scientists have failed to discover such a description. It is because the mathematical structure of relativity itself does not allow an inertial frame moving at the speed of light. That is why physicists generally avoid asking, "What does a photon experience?" Within the framework of special relativity, the question itself has no well-defined meaning. Some questions are not wrong. They are simply asked using a language that does not fit nature's deeper structure. Carl Gustav Jung once wrote in The Undiscovered Self, "The least of things with a meaning is worth more in life than the greatest of things without it." Perhaps science searches for meaning in its own way, not merely by collecting more facts, but by discovering the deeper structure hidden beneath them. Einstein did not simply discover another number. He changed the way humanity asked questions. He realized that sometimes what needs correcting is not the answer, but our original assumptions about the world. Perhaps human growth follows much the same path. We spend years searching for solutions to old problems. Then one day, what truly changes our lives is learning to see the problem from an entirely different perspective. Jung described this as the expansion of consciousness, a journey through which we gradually move beyond familiar patterns and encounter a reality larger than the ego itself. If special relativity had done nothing more than reveal that no object with mass can reach the speed of light, it would already rank among humanity's greatest scientific achievements. But Einstein went much further. He realized that if the speed of light must remain constant for every observer, then space and time themselves must change. Time no longer flows identically for everyone. Space is no longer the unmoving stage humanity imagined for centuries. Instead, they become two inseparable aspects of one unified structure that we now call spacetime. It is such a beautiful idea that, even more than a century later, it still causes many people to pause the first time they encounter it. As we finish reflecting on the universal speed limit imposed by light, perhaps you are still carrying a quiet sense of wonder. If light always maintains the same speed for every observer, if no object with mass can ever reach that speed, then what must change to keep the universe internally consistent? Einstein's answer was so astonishing that many scientists initially found it difficult to believe. It is not light that changes. It is space and time that prove far more flexible than anyone had imagined. That was the moment when time ceased to be a single river flowing equally for everyone. Instead, it became part of the fabric of space-time itself, able to stretch and bend depending upon motion and gravity. Imagine two close friends. One remains on Earth. The other boards a spacecraft capable of traveling at a speed very close to that of light. For each of them, the watch upon their own wrist continues ticking perfectly normally. Neither notices time slowing down. Neither feels anything unusual happening around them. That point is extremely important. Time always flows normally, according to the experience of the person living within their own frame of reference. The difference appears only when the two people compare their clocks after meeting again. According to special relativity, the traveler who has journeyed at extremely high speed will have experienced less proper time. This phenomenon is known as time dilation. Its name may suggest that time is somehow being stretched like a rubber band, but the true meaning is simpler. The measured interval between two events depends on the observer's state of motion. There is no single universal clock shared by everyone. At first, this sounds like science fiction, yet it is far more than a mathematical curiosity. Over the past several decades, countless experiments have confirmed this effect. Muons produced in Earth's atmosphere survive longer than classical physics would predict when they travel at speeds close to that of light. In 1971, the famous Hafele-Keating experiment flew atomic clocks around the world aboard commercial aircraft in opposite directions. When those clocks were later compared with identical clocks that had remained on Earth, tiny differences were measured. Differences that agreed with the predictions of relativity, once both the aircraft's motion and Earth's gravitational field were taken into account. Today, the Global Positioning System, GPS, used by billions of people every day, must continuously correct for relativistic effects. Without those corrections, positioning errors would quickly accumulate over time. An idea once dismissed as impossibly strange now quietly helps guide us every single day. But time is not the only thing that changes. Einstein also discovered that length depends upon motion as well. This phenomenon is known as length contraction. If an object moves at a speed very close to the speed of light relative to an observer, its length measured along the direction of motion becomes shorter. The remarkable thing is that the object itself never feels compressed. Within its own frame of reference, every dimension remains perfectly ordinary. Length contraction appears only when measurements are made from another frame moving relative to it. Once again, nature seems to whisper something profound. No single point of view possesses the entire truth. Every observer holds one piece of the picture, and the laws of physics ensure that all those pieces fit together perfectly. Perhaps this is also one of Carl Gustav Jung's deepest lessons. He once wrote in Psychological Types, "Everything that irritates us about others can lead us to an understanding of ourselves." Behind those words lies a beautiful idea. Human beings naturally assume that their own perspective is the only one. Yet, as we mature, we gradually realize that everyone is viewing the world from a different place. Relativity does not claim that everything is relative in the popular philosophical sense. Quite the opposite. It shows that although measurements of space and time may differ between observers, the laws of physics remain the same in every inertial frame of reference. That is not chaos. It is a deeper kind of order. Perhaps no equation in the history of science is more famous than A. Mc-Sword. Only 5 symbols. Yet they transformed humanity's understanding of matter itself. In that equation, E represents energy, I represents mass, C represents the speed of light in a vacuum. What Einstein revealed is that mass and energy are intimately related manifestations of the same physical reality. In many physical processes, a small amount of mass corresponds to an enormous amount of energy. Likewise, under appropriate conditions, energy can participate in the creation of particles. Because the speed of light is already an enormous number, its square is vastly larger still, which means even a tiny amount of mass corresponds to an extraordinary amount of energy. This principle explains how the sun shines. Within its core, nuclear fusion converts a small fraction of mass into radiant energy, sustaining life on Earth for billions of years. Sometimes I think that equation possesses the beauty of poetry. It tells us that things appearing completely different may, in fact, be deeply connected, like light and darkness, like consciousness and the unconscious in Jungian psychology. Not two separate worlds, but different expressions of the same ongoing journey of discovery. Yet perhaps the most famous story in relativity is still the twin paradox. Imagine identical twins. One remains on Earth. The other departs aboard a spacecraft, traveling at nearly the speed of light before eventually returning home. When they meet again, the traveling twin is younger. At first, this seems contradictory. If motion is relative, why can't we simply say that the astronaut remained at rest while Earth moved instead? The crucial point is that the two journeys are not symmetrical. The sibling who stays on Earth remains approximately within the same inertial frame throughout the experiment. The traveler, however, must accelerate, decelerate, and reverse direction before returning home. Those changes make all the difference. As a result, the two twins experience different amounts of proper time. So this is not truly a paradox. It is a perfectly consistent consequence of relativity once the entire journey is analyzed correctly. And the remarkable part is this: it is no longer merely a thought experiment. Experiments involving atomic clocks and fundamental particles have repeatedly confirmed the same underlying effects. Albert Einstein once said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." Perhaps it was precisely that curiosity that led him toward ideas that transformed all of physics, not because he possessed more data than everyone else, but because he dared to question what everyone else considered obvious. Is time truly the same for everyone? Is space really motionless? Does light behave according to human intuition? Sometimes, one good question is enough to open an entirely new era. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, "Who looks outside? Dreams. Who looks inside? Awakes." Perhaps that is exactly what we have been doing throughout this journey. We have looked outward to understand stars, black holes, galaxies, and the fabric of space-time. Yet every discovery has quietly brought us back to ourselves. Because when we realize that time is not absolute, we also learn to treasure every moment more deeply. When we understand that no single perspective contains every truth, we become better listeners. And when we discover that the universe is woven together by laws that reach beyond ordinary intuition, we also learn humility before all that we do not yet know. The night has now become wonderfully quiet. Perhaps the clock upon your wall is still ticking steadily. Yet, after Einstein's story, you may find yourself smiling at the thought that each of those passing seconds is not quite as simple as it once seemed. Somewhere in the universe, other clocks are keeping a different rhythm. Imaginary spacecraft continue racing among the stars. Photons still cross the vastness of space at their unwavering speed. And here, upon this small planet, you are slowly closing your eyes while carrying one gentle thought with you. Time is not merely what carries us toward old age. It is also the invisible fabric from which every memory, every meeting, and every dream is woven. Perhaps that is why understanding time is also one way of understanding our own lives more deeply. And in the next chapter, we will continue that journey as we step into a mystery even stranger than space-time itself, quantum mechanics, where the smallest particles in the universe challenge our intuition in ways even more extraordinary. The quantum world. After exploring Albert Einstein's extraordinary ideas together, where space and time are no longer separate and unchanging, but woven together into a single fabric we call space-time, perhaps you have begun to notice something remarkable. The universe seems constantly to invite us to let go of what once appeared obvious. Each time humanity believes it has finally understood the world, nature quietly opens another door. And behind that door, there is always something stranger still. If relativity taught us to see time through new eyes, then the next chapter of our journey will carry us somewhere even more surprising. A place where even the simple question, "Where is an object?" no longer has an ordinary answer. Welcome to the quantum world, a world so unimaginably small that if an atom were enlarged to the size of an entire stadium, its nucleus would be no larger than a pea resting at midfield, and the electrons would not move in the neat little orbits our imagination once pictured. For most of human history, we learned to understand the world through familiar experiences. A stone rolling downhill, a leaf falling from a branch, a planet orbiting the sun. These are deeply intuitive images. They encourage us to believe that if we know an object's position and velocity precisely enough, we can predict its future. At the scale of everyday life, that idea works extraordinarily well. But when scientists began exploring the deep interior of the atom, those familiar rules gradually proved insufficient. The microscopic world does not behave like the world our eyes evolved to see, not because nature is trying to deceive us, but because our intuition evolved to survive in a world measured in meters and kilometers, not at scales measured in billionths of a meter. Perhaps no field in modern science has been misunderstood more often than quantum mechanics. You may have heard someone say, simply observing reality changes it. Or perhaps, human consciousness creates the universe. Those statements sound mysterious, but they do not accurately reflect what quantum physics has actually discovered. What physicists truly study is far more subtle. In quantum mechanics, when we speak of a measurement, we do not simply mean a human being opening their eyes and looking. A measurement is a physical interaction between a quantum system and a measuring device, or, more broadly, with its surrounding environment. It is that interaction which can alter the quantum state of the system. In other words, the change does not occur because someone merely thinks about an electron. It occurs because obtaining information at the quantum scale always requires a physical interaction. In the very small world, you cannot touch something without influencing it in some way. Imagine a perfectly still lake at midnight. You want to know just how calm its surface truly is. But the only way to find out is to drop a tiny pebble into the water. The instant the pebble touches the surface, ripples appear. The moment you obtain information is also the moment the lake has changed. Of course, this analogy does not fully describe quantum mechanics, but it helps us sense an important idea. Sometimes, the act of measurement and the object being measured cannot be completely separated. The quantum world asks us to abandon the dream that an observer can always remain entirely outside the event being observed. We, too, are part of nature. Every measurement is an encounter between two physical systems. That does not make science vague. Quite the opposite. It makes science more humble. Physicists do not claim that everything is created by the human mind. They simply recognize that, at the quantum scale, the questions we ask and the answers nature gives are inseparably connected to the methods we use to observe. That is a profound distinction. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, "The least of things with a meaning is worth more in life than the greatest of things without it." Perhaps the greatest gift of science is not the creation of mystery, but the discovery of meaning within reality itself. Quantum mechanics does not need to be mystified in order to seem extraordinary. It already is. One of the most familiar images found in older textbooks depicts electrons orbiting the nucleus the way planets orbit the Sunday. It is a beautiful picture, an intuitive one, but today we understand that it serves only as an early stepping stone in the history of science. Modern quantum mechanics tells us that electrons do not travel along definite orbits the way planets do. Instead, they are described by a wave function, from which we derive atomic orbitals, regions of space where an electron is more likely to be found. This does not mean that an electron is simply a fuzzy cloud of matter surrounding the nucleus, nor does it mean that an electron literally exists everywhere at once, as popular explanations sometimes suggest. What the theory actually tells us is this: before a position measurement is made, the electron's state is described by its wave function. The outcome of that measurement can only be predicted probabilistically. It is an entirely new language. Gone are the perfect circular paths. Gone are the fixed planetary orbits. What remains are possibilities, described mathematically with astonishing precision. At first, this may seem to take certainty away from us. Human beings naturally love clear outlines, definite answers, but nature has never promised to conform to our intuition. Albert Einstein famously expressed his discomfort by saying, God does not play dice with the universe. He was dissatisfied with the probabilistic nature of quantum mechanics. Niels Bohr later replied, just as memorably, Einstein, "Stop telling God what to do." Those two brilliant minds debated one another for years, not because either wished to defeat the other, but because both were striving to understand reality more deeply. That is one of science's most beautiful qualities. Disagreements do not exist to divide. They exist to move knowledge forward. Perhaps Jung would have smiled at that. He devoted his life to exploring the unconscious, recognizing that the human mind does not function like a simple machine. There are hidden layers, motivations that reveal themselves only through patience. That does not mean the mind is chaotic. It simply means it is richer than the simple models we once imagined. The quantum world is much the same. It does not reject order. It simply shows us that order at the smallest scales is written in a different language, a language of probabilities, wave functions, and laws that everyday intuition struggles to imagine. Now that the night has grown even deeper, imagine every atom within your body. The electrons are not circling like tiny planets. They exist according to laws far more extraordinary. Those very laws keep atoms stable. They allow molecules to form. They give rise to water, air, stone, trees, and even the brain quietly listening to this story. At nature's smallest scales, there is no chaos, only a level of subtlety that requires us to learn an entirely new way of seeing. Now that we have left behind the strange world of quantum orbitals where electrons no longer move like miniature planets, but instead exist within regions of probability described by wave functions, perhaps another feeling has begun to settle within you. At first glance, quantum mechanics seems like a subject belonging only to laboratories. A world too small, too distant, too abstract. Yet the truth is exactly the opposite. Without these quantum laws, there would be no stable atoms, no molecules, no water, no air, no trees, no stars as we know them, and there would be no human being quietly listening to this story before drifting into sleep. Perhaps the most natural question is this: what prevents an electron from falling into the nucleus? Within the classical picture, this was once a deeply troubling problem. If an electron was simply a charged particle orbiting the nucleus like a planet orbiting the sun, classical physics predicts that it should continuously emit electromagnetic radiation, lose energy, and spiral into the nucleus within an extremely short time. Yet nature behaves differently. Atoms remain stable, stars continue shining, molecules survive for billions of years, which means our picture of the electron itself had to change. In quantum mechanics, an electron does not need to orbit the nucleus along a classical path in order to avoid falling inward. Instead, it exists in stationary quantum states, described by the Schrödinger equation. These states possess specific, quantized energy levels. When an electron occupies the lowest allowed energy state of a hydrogen atom, it does not spontaneously continue losing energy and collapse into the nucleus. That quantum structure itself is what gives atoms their stability. What binds the electron to the nucleus is the electromagnetic force. Electrons carry negative electric charge. Protons within the nucleus carry positive electric charge. Opposite charges attract through the Coulomb force. Yet if simple attraction were the entire story, classical physics tells us that atoms would be unstable. What creates stability is the electron's wave-like nature, together with the quantum rules that determine the allowed states in which it can exist. Imagine a violin string. It cannot vibrate at just any frequency. Only certain notes are permitted. Electrons behave in much the same way. They can occupy only specific quantum states. Nature does not choose arbitrary energy levels. It selects only the melodies that fit the structure of the atom. There is something wonderfully poetic about that idea. Matter is not built from chaos. It is built from an exquisitely delicate harmony. If atoms are the notes, then chemistry is the symphony. When two atoms approach one another, their electrons do not simply collide. their wave functions interact, new quantum states can emerge. That is the origin of chemical bonding. A water molecule, an oxygen molecule, a strand of DNA, a protein within every living cell, all exist because electrons obey the laws of quantum mechanics. In other words, chemistry does not merely use quantum mechanics. Chemistry is a consequence of quantum mechanics. Without the quantum structure of electrons, the periodic table would not exist in the form we know today. Carbon would not possess its characteristic 4 covalent bonds. Complex organic molecules could never form, and life, at least as it exists on Earth, would likely never have appeared. Sometimes we imagine that life is built from grand things, oceans, forests, mountains. Yet, the foundation of all of them lies within laws so small that no human eye will ever directly see them. A leaf trembling in the wind, a drop of water sparkling beneath sunlight, a heartbeat, a single breath. Every one of them begins with the arrangement of electrons around atomic nuclei. Perhaps there is no more beautiful reminder that the smallest things can produce the greatest consequences. And then we encounter one of nature's strangest and most essential rules, the Pauli exclusion principle, proposed by physicist Wolfgang Pauli in 1925. It states, no two identical fermions within the same system can simultaneously occupy the same quantum state. Electrons are fermions, which means no two electrons can squeeze into exactly the same quantum state. At first, that rule sounds almost impossibly abstract. Imagine a library. Each chair is assigned to one person. Once a seat is occupied, the next visitor must find another. It is only an analogy. Within an atom, the chairs are quantum states. The Pauli exclusion principle is what causes electrons to fill different orbitals, one after another. From that arrangement emerges the structure of the periodic table of the elements. Carbon behaves differently from oxygen. Oxygen differs from iron. Iron differs from gold. Not because nature made arbitrary choices, but because electrons are arranged according to remarkably precise quantum laws. If the Pauli exclusion principle did not exist, the world would be entirely different. Electrons could all collapse into the lowest possible energy state. Atoms would lose the shell structure we know today. The periodic table would cease to have meaning. The familiar chemical bonds upon which chemistry depends could never form. Matter as we know it might not exist at all. Its influence reaches far beyond atoms. On astronomical scales, the Pauli exclusion principle gives rise to electron degeneracy pressure, which helps support white dwarfs against gravity, and neutron degeneracy pressure, which plays a crucial role within neutron stars. Not only tiny atoms, but some of the universe's most extreme celestial objects bear the signature of this remarkable law. There is something astonishing about that. A principle written for particles far smaller than anything the human eye can ever see. Helps determine the structure of entire stars. Carl Gustav Jung once wrote in Aeon, "In all chaos there is a cosmos, in all disorder a secret order." Although Jung was speaking about the human psyche, those words also paint a beautiful picture of the quantum world. At first glance, it appears to be randomness, probabilities, invisible orbitals, strange and unfamiliar laws. Yet the deeper we look, the more we discover an extraordinary order hidden beneath that apparent disorder. An order invisible to the naked eye, yet present within every atom, every molecule, every cell, every star. The physicist Richard Feynman, one of the 20th century's greatest scientific minds, once remarked, "I think I can safely say that nobody understands quantum mechanics." That was not an admission of defeat. It was a reminder of humility. Even though the equations of quantum mechanics predict experimental results with astonishing precision, developing an intuitive picture of that world remains profoundly difficult. Perhaps the same is true of the human soul. We never fully understand ourselves. Yet that does not prevent us from continuing to explore. Quite the opposite. It is precisely what remains mysterious that makes the journey worthwhile. The night has become wonderfully still. You may never see an electron, never see an orbital, never see a wave function. But remember this, at this very moment, countless trillions upon trillions of atoms within your body are quietly obeying those quantum laws. Without a sound, without any display, only an invisible symphony unfolding within every cell. Perhaps that is the most beautiful story quantum mechanics has to tell. Beauty does not always belong to the grandest things. Sometimes it hides within laws so small that we can never see them directly. Yet those very laws support the entire world. And perhaps the human soul is much the same. The deepest transformations rarely begin with thunder. They begin with a single quiet thought, a gentle moment of understanding, a silence so still that only the night allows us to hear it. In the next chapter, we will travel even deeper into the mysteries of reality, where elementary particles, quantum fields, and questions about the ultimate nature of matter open another chapter in our exploration of the universe. And, perhaps, another chapter in our exploration of the human mind itself. Light and waves, as we gently close the door to the quantum world where electrons quietly inhabit invisible orbitals, and every atom within our bodies obeys subtle laws beyond ordinary intuition, you may begin to notice something surprising. Our journey has never really left everyday life behind, because all of those extraordinary ideas are already present all around you, in the gentle glow of your bedside lamp, in the moonlight slipping through your window, in the green of leaves, in your reflection upon a mirror, even in the eyes that are slowly growing heavier after a long day. Perhaps nothing is more familiar to humanity than light. Since the earliest days of our ancestors, we have awakened with sunrise and rested beneath the coming of night. Light brings life, warmth, direction. Yet only during the past few centuries have we begun to understand that light is far more remarkable than anything our eyes alone can reveal. If you were to ask a child, "What is light?" they would probably smile and point toward the Sunday, or switch on the lamp in the room. It is a wonderfully natural answer, but physics offers us a much larger picture. The light visible to human eyes is only a tiny portion of an immense ocean known as the electromagnetic spectrum. Imagine standing beside the sea. The wave touching your feet is only a single ripple. Beyond it stretches an ocean reaching all the way to the horizon. Visible light is like that one small wave. It occupies only a very narrow band within the entire electromagnetic spectrum. At one end lie radio waves, with their enormously long wavelengths, carrying radio broadcasts, television signals, and communication across thousands of kilometers. Next come microwaves, used both for communication technologies and in microwave ovens. Then comes infrared radiation, quietly emitted by your own body as heat. Beyond the narrow band visible to human eyes lie ultraviolet light, X-rays, and gamma rays, each possessing different energies and enabling their own remarkable applications and presenting their own unique challenges in science and medicine. The extraordinary thing is this: they are all electromagnetic waves. They differ only in wavelength, frequency, and energy. Nature did not create many different kinds of light. There is only one great family. Human vision simply allows us to perceive a very small part of it. That thought always fills me with a sense of humility. How many things surround us that our senses cannot perceive directly, not because they do not exist, but because our eyes evolved only to support life upon Earth. If our vision extended into the infrared, the night would glow with the warmth of trees, animals, and our own bodies. If we could see radio waves, the sky would overflow with invisible streams of information passing through it every second. If we could perceive X-rays, the world would appear entirely different. Perhaps reality has always been far larger than the story our senses tell. Carl Gustav Jung once wrote in The Undiscovered Self, "The world hangs on a thin thread, and that is the psyche of man." Although Jung was speaking of inner life, His words suggest another beautiful reflection. The world we experience is shaped not only by what exists outside us, it is also shaped by our own capacity to perceive. Every sense is a doorway, yet no doorway opens onto the entire house of reality. Perhaps that is why color itself is not quite what we once imagined. When we look at a red rose, we naturally say, "This flower is red." Yet physics tells a subtler story. White sunlight actually contains many different wavelengths. When that light strikes the petals, the pigments within the flower absorb certain wavelengths while reflecting others. Our eyes receive that reflected light. Our brains interpret it as the experience we call red, which means color is not an absolute property hidden inside an object. It is the result of an encounter between light, matter, and the observer's visual system. Without light, without eyes, the experience we call red would not exist in the form we know it. There is something deeply familiar about the way human beings understand one another. Two people may witness exactly the same event, yet carry away entirely different memories. Not because one is right and the other wrong, but because every mind reflects the world in its own unique way. Jung devoted his life to exploring precisely that mystery. He never denied reality, but that he understood that what reaches our conscious awareness is always the meeting place between the outer world and the inner one. Light gives rise to color, the mind gives rise to meaning, and then there is one object that has accompanied humanity for thousands of years: the mirror. At first glance, a mirror seems wonderfully simple. You stand before it, you see yourself. But what is really happening? When light reflected from your face reaches the surface of a mirror, most of it undergoes specular reflection, following a remarkably simple rule. The angle of incidence equals the angle of reflection. Billions upon billions of tiny rays obey that single law. Your eyes collect the reflected light. Your brain then reconstructs the paths those rays must have traveled and concludes that the image lies behind the mirror. Yet in truth, there is no face behind the mirror at all. There is only light, and the way your brain interprets light's journey. Once again, nature gently reminds us that what we see is always the result of an encounter between the physical world and the mind. Perhaps that is why polarized sunglasses are such an elegant invention. Light is an electromagnetic wave, and in many situations, it can be described by the orientation of its electric field, known as its polarization. When light reflects strongly from water, roads, or glass, part of the reflected light tends to become polarized in particular directions. Polarizing lenses are designed to block much of that glare-producing polarized light, allowing us to see more clearly and comfortably. The remarkable thing is this: the lenses do not make the world brighter, they simply remove much of the unnecessary signal, so that what truly matters becomes easier to see. Perhaps that is also a beautiful metaphor for the inner life. Growing wiser is not always about acquiring more. Sometimes it means quietly learning to let go of unnecessary noise, so that what truly matters can gently come into focus. Albert Einstein once said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and all science." Perhaps that is exactly the feeling light has always carried. The more we understand it, the more we discover that the most familiar things often contain the deepest mysteries. A ray of sunlight entering through a window, a rainbow after rain, a reflection in a mirror, the green of a leaf. Each is a story that light has been patiently telling for billions of years. Humanity has only recently learned how to listen. The night has grown even gentler. Perhaps the lamp in your room is still casting its familiar glow. But after our conversation, you may look at it a little differently. No longer as merely a source of illumination, but as one tiny part of the immense ocean of electromagnetic waves that fills the universe. An invisible ocean in which every wavelength carries its own story. Now that we have stepped away from mirrors and the gentle colors of the visible spectrum, perhaps another realization has begun to emerge. Light does far more than help us see the world. It tells us about the world. Change the wavelength just a little. Change the way electromagnetic waves interact with matter. And nature quietly opens entirely new doors. Doors that ordinary human eyes could never perceive on their own. Let us begin with one of the 20th century's most beautiful inventions, the laser. Today we encounter lasers almost everywhere, in barcode scanners, in fiber optic internet connections, in delicate surgical procedures, in distance measuring instruments, even in spectacular light shows. Yet what makes a laser extraordinary is not simply its power, it is the remarkable degree to which its light is monochromatic, highly directional, and coherent. The word laser stands for light amplification by stimulated emission of radiation. Inside an appropriate material, atoms or molecules are excited into higher energy states. When a photon possessing exactly the right energy passes by, it can stimulate an excited atom to emit another photon with the same energy, traveling in the same direction, and in phase with the original photon. The process repeats again and again, like a choir, in which every singer joins exactly the same note, at exactly the same rhythm, at exactly the same moment. The result is a beam of light that is extraordinarily narrow, remarkably stable, and capable of traveling long distances while spreading far less than ordinary light. There is something deeply beautiful about that idea. Sometimes strength comes not because each individual becomes greater, but because everyone moves together in harmony. Carl Gustav Jung once wrote in The Structure and Dynamics of the Psyche, "The creation of something new is not accomplished by the intellect, but by the play instinct acting from inner necessity." Perhaps nature creates in much the same way, without fanfare, only through simple rules working together. And from those simple rules, something extraordinary emerges. If the laser is the story of perfectly organized light, then the microwave oven is the story of invisible energy quietly interacting with molecules. Whenever we place a bowl of soup into a microwave oven, many people imagine that the food is heated from the inside. The reality is a little more subtle. A microwave oven produces microwave electromagnetic radiation. Its oscillating electromagnetic field interacts especially efficiently with polar molecules, most notably water. The water molecules continually attempt to align themselves with the rapidly changing electric field. That motion increases their thermal energy, causing the food to become warmer. Heat does not appear from nowhere. It is the result of energy being transferred from electromagnetic waves into matter. That simple process unfolds millions of times every day in kitchens throughout the world. Then there are infrared cameras. If our own eyes perceive only a tiny slice of the electromagnetic spectrum, an infrared camera is like a new pair of eyes. Eyes capable of detecting infrared radiation emitted or reflected by objects, especially radiation related to their temperature. Human beings, animals, a cup of hot tea, a wall warmed by the afternoon sunday, all leave their own signatures within the infrared. Infrared cameras are not magical devices that see through walls, as films often suggest. They simply record the infrared radiation reaching their sensors. Yet even that is enough to unlock countless applications, from nighttime search and rescue missions to astronomy, to detecting heat loss in buildings. Once again, science does not create a new world. It simply allows us to perceive parts of the world that have always existed. Farther along the electromagnetic spectrum lie X-rays. When Wilhelm Conrad Röntgen accidentally discovered this form of radiation in 1895, he named it X-rays. Because the letter X traditionally represents the unknown, the name has remained ever since. What makes X-rays special is their extremely short wavelength and higher energy compared with visible light. As X-rays pass through the human body, different tissues absorb them to different degrees. Bones, which contain elements with higher atomic numbers than soft tissues, absorb X-rays more strongly, and therefore appear brighter on an X-ray image. Because of that remarkable property, physicians can examine structures inside the body without surgery, an invisible form of light, helping to save countless lives. Perhaps that is another lesson nature quietly whispers. Not everything that proves most useful is easy to see. Some things work quietly, silently, yet they transform the lives of countless people. If you have ever watched a soap bubble beneath sunlight, you may remember the flowing ribbons of color continually shifting across its delicate surface. The extraordinary thing is this: those colors do not come from pigments. The soap film is almost perfectly transparent. So where does that tiny rainbow come from? The answer lies in thin film interference. Part of the light reflects from the outer surface of the film. Another portion enters the film, reflects from the inner surface, and emerges again. Those two waves meet. At certain wavelengths, they reinforce one another. At others, they cancel one another out. Because the thickness of the soap film is constantly changing, the conditions for interference also change continuously. The result is a tapestry of soft colors forever drifting across the bubble's surface. Those are not the colors of the soap. They are the colors of light itself. Exactly the same phenomenon appears in the thin film of oil floating upon rainwater. You may notice shimmering blues, purples, golds, pinks, not because the oil contains every one of those colors, but because the thin layer causes different wavelengths of light to interfere in different ways. A phenomenon of physics, yet one that paints a picture so beautiful it seems as though nature herself were holding a brush. Perhaps that is why I have always loved science. It never takes beauty away from the world. It simply helps us understand why the world is so beautiful. Albert Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." Perhaps every a laser beam, a microwave oven, an infrared camera, an X-ray image, a soap bubble, a thin film of oil floating on water. At first glance, they seem completely unrelated, yet at a deeper level, they are all chapters of the same story. The story of light, of electromagnetic waves silently carrying energy and information throughout the universe. The night has become wonderfully gentle. Perhaps the light in your room has softened, yet even as your eyes slowly begin to close, electromagnetic waves continue their endless journey. Starlight still crosses the vastness of space. Photons continue touching leaves, rivers, and the faces of those peacefully asleep. The world has never stopped singing its quiet song of light. We simply rarely slow down enough to hear it. And in the next chapter, we will leave light behind and turn to another remarkable kind of wave: sound. Together we will explore noise-canceling headphones, violin strings, resonance, the mystery of the Tacoma Narrows Bridge, the crack of a whip, and the sonic boom, where invisible waves continue telling the timeless story of harmony between science and nature. Fluid mechanics. As the last ripples of sound slowly fade into the night, as light finishes telling its story of photons quietly crossing the universe and invisible waves silently connecting all things, perhaps you begin to realize that science has never belonged only to observatories or enormous laboratories. It is here as well, in every breath, in every gentle breeze brushing your face, in every drop of sweat quietly evaporating from your skin after a warm afternoon, in an airplane crossing the sky, in a soccer ball unexpectedly curving through the air, even in the cool glass of water resting beside your bed. Perhaps the most familiar things are where nature quietly hides its most beautiful secrets. Close your eyes for a moment. Imagine yourself lying in a wide open meadow. Above you stretches a perfectly clear night sky. Suddenly, an airplane glides silently overhead. Its shape has disappeared into the darkness. Only a few tiny lights drift slowly among the stars. Perhaps you have wondered before, what truly keeps hundreds of tons of metal suspended in the sky? For many years, people often answered very simply, because the air moves faster over the top of the wing, creating lower pressure. There is truth in that explanation, but it is only part of the story. Nature is usually more subtle than brief explanations suggest. An airplane wing does more than possess a special shape. It is also tilted at a small angle relative to the oncoming airflow. Engineers call this the angle of attack. As the airplane moves forward, its wings redirect the surrounding air. a tremendous amount of air is deflected downward. According to Newton's third law of motion, if the wing pushes the air downward, the air pushes the wing upward with an equal and opposite force. At the same time, the wing's shape and the airflow around it create different pressure distributions above and below the wing. These two descriptions do not contradict one another. They are simply two ways of describing the same physical phenomenon. It is the combination of redirected airflow, pressure differences, angle of attack, and many other aerodynamic effects that produces the lift, allowing an airplane to fly. Perhaps that is the most beautiful part. No miracle is taking place. Nature is simply, patiently, following its own laws. That always reminds me of life itself. Often we notice only the result: a mature person, a gifted artist, a compassionate physician, a brilliant scientist. It is like watching an airplane soaring through the sky. We admire its beauty, yet rarely notice the countless invisible forces working together to make that flight possible. No success is lifted by a single cause, just as no airplane flies because of one simple equation. Carl Gustav Jung once wrote in Modern Man, "In search of a soul, your vision will become clear only when you can look into your own heart. Who looks outside dreams. Who looks inside awakes." Perhaps science teaches us the very same lesson. If you wish to understand something, do not look only at its surface. Look for the invisible forces quietly at work beneath it. Now let us leave the sky behind and return to Earth. Perhaps you have watched a soccer match, or a tennis game, or simply thrown a ball in a park. Sometimes the ball suddenly curves sideways. It seems to change direction even though nothing touches it. That phenomenon is known as the Magnus effect. When a spinning ball flies through the air, the surrounding airflow is no longer symmetrical. On one side, the ball's rotation causes the nearby air to move faster. On the opposite side, the air moves more slowly. That difference contributes to a pressure imbalance around the ball. The result is a sideways force that bends its path. The ball does not mysteriously decide to turn. The air itself quietly guides its journey. There is something fascinating about that. Air is invisible, yet it possesses enough influence to alter the path of an object traveling at great speed. How many things in life resemble that? A few encouraging words, an unexpected meeting, a single book, one memory. At first, they seem so small, yet years later we discover they quietly changed the direction of our entire lives. Perhaps Jung would have called them meaningful encounters, not because they arrived with great noise, but because they quietly changed the orbit of the soul. Now notice your own body. On a hot summer afternoon, you may have felt sweat forming across your forehead. At first, it seems uncomfortable, yet it is one of evolution's most elegant cooling systems. As water evaporates from your skin, the molecules possessing higher than average energy are more likely to escape the liquid first. As they leave, they carry energy away. The average energy of the remaining water decreases. Your skin loses heat along with it, and you begin to feel cooler. The remarkable point is this: the wind itself does not directly cool your body. Instead, it mainly helps water evaporate more quickly, making that cooling process more effective. That is why even a gentle summer breeze can feel so wonderfully refreshing. Perhaps this is one of nature's most beautiful lessons. Sometimes, to become lighter, we must learn to let go. A drop of water does not cling to every one of its molecules. Those carrying the most energy quietly depart from its surface, and what remains becomes cooler. That is physics. Yet it is also a beautiful image of the human spirit. There are worries, regrets, old burdens. The tighter we hold them, the more exhausted we become. Sometimes peace arrives not by gaining something new, but by quietly allowing certain things to leave. Albert Einstein once said, "Life is like riding a bicycle. To keep your balance, you must keep moving." It is such a simple sentence. Yet when we think about the wind, about airplanes, about spinning balls curving through the sky, about water molecules quietly evaporating, we begin to notice that everything is moving. Nothing remains completely still. The air moves. The molecules move. Our bodies move. Even life itself is a continuous flow of energy. Perhaps movement itself is what creates balance, not stillness. The night has now become wonderfully gentle. Perhaps there is a gentle breeze outside your window. You cannot see it, yet the leaves are softly trembling. The curtain moves almost imperceptibly, and the warmth of your own skin is quietly flowing into the surrounding air. Nature has never needed complexity to become extraordinary. An airplane wing, a spinning ball, a breeze, a drop of sweat. Each is telling the same story. A story of invisible forces, of energy, and of the delicate balance that quietly supports the world every day. As the last gentle breeze from our previous story settles into silence, as the airplane disappears beyond the clouds, and the tiny droplets of sweat carry away the day's warmth from your skin, perhaps you begin to notice that the wonders of physics are not confined to the sky. They also live in the kitchen, in a kettle beginning to boil, in a cup of tea still releasing steam, in a pot quietly cooking dinner, and in the small flame that has accompanied humanity for hundreds of thousands of years. Perhaps the simplest things are where nature whispers its deepest secrets. Imagine yourself standing in a quiet kitchen on a winter evening. A kettle has just reached a boil. You carefully avoid the bubbling water, but by accident, your hand passes through the rising steam. The sharp sting comes almost instantly. Many people have wondered why, if both liquid water and steam are at about 100 degrees Celsius under standard atmospheric pressure, why does steam often cause more severe burns? The answer lies in a special form of energy. When steam touches cooler skin, it condenses back into liquid water. During that phase change, it releases a large amount of energy known as the latent heat of vaporization, or, more precisely during condensation, the latent heat of condensation. That means steam transfers not only its temperature, it also releases additional energy as it changes from a gas into a liquid. That extra energy delivers more heat into the skin, making the burn potentially much more severe than contact with liquid water at the same temperature. Nature is always that careful. Behind what appears to be a simple event, there is often a deeper story. Perhaps human emotions work in much the same way. Sometimes, what hurts us is not merely what stands before us, but everything it carries with it. A sentence, a memory, a farewell. Behind that single moment often lies an entire unseen history. Steam is much the same. We notice only the thin white mist. Yet what is truly being transferred is invisible energy. Now turn your attention to the humble pressure cooker, quietly doing its work. At first glance, it seems little different from an ordinary pot. Yet a tightly sealed lid and a small pressure valve completely change the way water boils. Under normal atmospheric pressure, water boils at about 100 degrees Celsius. But as the pressure inside the cooker increases, the boiling point rises as well. That means both the liquid water and the steam inside can reach temperatures higher than they ordinarily could. Food therefore cooks at higher temperatures. Chemical reactions proceed more rapidly. Tough foods soften more quickly. Not because the flame is stronger, but because the physical conditions have changed. A small increase in pressure produces a remarkable difference in the outcome. Perhaps that is also a beautiful metaphor for life. Sometimes what shapes our growth is not merely the passage of time, but the environment around us. Different circumstances can reveal entirely different possibilities that were already waiting within us. There is another wonderfully familiar phenomenon. Leave a metal bar and a block of wood inside the same room for several hours. Eventually, both will reach almost exactly the same temperature as the surrounding air. Yet, when you touch them, the metal always feels colder. Why? The answer has nothing to do with temperature. It has to do with thermal conductivity. Metal conducts heat extremely well. When your warm hand touches its surface, heat flows rapidly from your skin into the metal. The nerve endings in your skin detect that rapid loss of heat. and send signals to your brain. Your brain interprets those signals as cold. Wood behaves very differently. It is a poor conductor of heat. Energy leaves your hand much more slowly. Your skin loses less heat over the same amount of time, so the wood feels warmer. Even though both objects may actually be at exactly the same temperature, perhaps our intuition often works that way as well. Our feelings are perfectly real, yet the causes behind them are not always what we first imagine. Carl Gustav Jung once wrote in Psychology and Religion, "One does not become enlightened by imagining figures of light, but by making the darkness conscious." Perhaps science follows the same path. It never dismisses what we experience. Instead, it patiently looks beneath our experiences to understand what is truly happening. Knowing that metal is not actually colder than wood does not diminish what our hands feel. It simply deepens our understanding of that experience. Knowledge never makes the world less wonderful. It gives wonder greater depth. And now we return to one of humanity's oldest companions, fire. Ever since our ancestors first learned to tend a flame, people have gathered around its light to tell stories, stay warm, prepare food, and dream about whatever lay beyond the darkness. But what is fire, really? At first glance, a flame appears to be an object. It has shape, color, constant movement. Yet in physics, fire is not a material substance. A flame is a region of hot, glowing gas produced during combustion, a rapid oxidation reaction that releases heat and usually emits light. When wood burns, the complex molecules within it break apart and react with oxygen in the surrounding air. The chemical energy stored within those molecular bonds is released. Part of that energy becomes heat. Part becomes the light our eyes perceive. The flame itself is not the thing that is burning. It is the visible expression of the burning process. If you observe a candle closely, you will notice that different parts of the flame display different colors. Near the wick, the flame is often darker because relatively little oxygen is available. The bright yellow region comes primarily from tiny soot particles heated until they glow. Under conditions of more complete combustion, the flame may appear blue, where light emitted by excited molecules and reactive chemical species within the hot gases plays a more prominent role. Even a tiny candle flame is an entire world where physics, chemistry, and thermodynamics unfold simultaneously. Richard Feynman once said, "Nature's imagination is so much greater than man's." Perhaps few things illustrate those words more beautifully than a flame. Human beings see only a flickering light. Nature is orchestrating trillions upon trillions of molecular collisions every second. We feel warmth. Nature is transforming energy according to laws that have existed since the earliest moments of the universe. The more deeply we understand, the more we discover that the most ordinary things often contain the most extraordinary stories. Perhaps that is why Jung believed we must learn to look beneath the surface of things, not to diminish their beauty, but to discover an even deeper beauty. A flame is no longer merely a flame. A breeze is no longer merely the wind. A drop of water is no longer just water. Every phenomenon becomes a doorway into the wonder of nature. And just like the human soul, behind what seems simple, there are always deeper layers still waiting to be discovered. The night has grown perfectly still. Perhaps the wind outside your window has come to rest. Inside the room, every sound seems to drift farther away. Imagine a single candle burning before you. Its flame sways gently, never hurried, never loud. It is doing what fire has done for hundreds of thousands of years, transforming invisible energy into light and warmth. Perhaps the human mind is much the same. Experiences, memories, emotions quietly transform with time. Some things once caused us pain, then gradually become understanding. Some things were once darkness, then one day become a light bright enough to guide someone else. Nature never stops transforming, neither do we. And perhaps that is one of the gentlest laws of the universe. In the next chapter, we will leave the kitchen and its quiet flame behind and continue into an even broader journey, exploring the laws of energy, entropy, and thermodynamics, where we will discover why everything changes with time, why order and disorder always exist together, and what gives the arrow of time its unwavering direction toward the future. Remarkable materials. As the flame from our previous chapter slowly fades, as its warmth still lingers softly in the room, and the kettle has finished releasing its steam, perhaps you feel that you have begun to understand how nature works. Water flows, fire burns, air moves, light travels. Everything seems to obey dependable and familiar laws. And yet, just like the human mind that Carl Gustav Jung spent a lifetime exploring, nature quietly preserves its own gentle exceptions. Some materials behave in ways that completely puzzle our intuition. Some phenomena appear almost magical. A strand of metal can recover its original shape. A liquid can suddenly become solid when struck with enough force. A tiny grain of sand can help create sounds that echo across an entire desert. Not because nature breaks its own laws, but because those laws reach far deeper than our first impressions ever imagined. Let us begin with a phenomenon you have probably encountered without giving it much thought. You step into a darkened room. Someone switches on an ultraviolet lamp. Suddenly, the security markings on a banknote, patterns on a shirt, or minerals displayed on a shelf begin glowing with brilliant blues, purples, and pinks. What has just happened? Have those objects begun producing light on their own? Not quite. This phenomenon is called fluorescence. Certain materials are capable of absorbing higher energy photons, typically ultraviolet light or blue light. Electrons inside the material become excited into higher energy states, but they do not remain there for long. After an extremely brief interval, usually only a few nanoseconds, they return to lower energy states, emitting new photons with lower energies. Those emitted photons are the light our eyes perceive. That is why fluorescent materials glow only while the exciting light is still present, or immediately after exposure. Once the ultraviolet source is removed, the fluorescent glow disappears almost instantly. That distinguishes fluorescence from phosphorescence, in which certain materials continue glowing for some time even after the exciting light has been switched off. It is a subtle difference, yet a beautiful one. Even light has more than one way of telling its story. There is something about fluorescence that always makes me smile. The light we see is not something the material simply keeps. It is a gift returned. One photon arrives, another photon departs. Not exactly the same one, yet enough to continue the journey. Perhaps life unfolds in much the same way. The good things we receive rarely remain with us forever. They are transformed, then passed on to someone else in a new form. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, "We cannot change anything unless we accept it." Perhaps every transformation begins with receiving something first. Even a fluorescent material must absorb light before it can shine in its own unique way. If light can transform itself so delicately, then metals have a story that seems almost borrowed from a fairy tale. Imagine holding a thin metal wire in your hand. You bend it, twist it, even deform it completely. At first, it appears ruined, but then, when you heat it to the proper temperature, it slowly returns to its original shape, as though it somehow remembered what it once was. Scientists call such materials shape memory alloys. The name itself sounds wonderfully poetic, yet the remarkable truth is this: the metal possesses no memory in the human sense. Its extraordinary behavior arises from a transformation between two different crystalline structures, commonly known as martensite and austenite. At lower temperatures, the material can be bent quite easily. When heated into the appropriate temperature range, its crystal structure changes, allowing it to recover the shape that was established during manufacturing. There is no magic involved, only the exquisite order of atoms. That always reminds me of people. Sometimes life bends us in unexpected ways, through loss, disappointment, or circumstances beyond our control, yet somewhere deep inside, there often remains a truer shape toward which the soul quietly longs to return. Jung called this process individuation, the lifelong journey of becoming the fullest version of oneself, not returning to who we once were, but returning to the deepest truth that has always lived within us. Perhaps a shape memory alloy has no soul, yet it reminds us, beautifully, that some structures endure beyond outward appearances. And once again, nature surprises us. Imagine placing a bowl upon the table. Inside is an extraordinarily simple mixture, nothing more than water and cornstarch. You slowly dip a finger into it. The mixture flows like a liquid, but if you suddenly strike it with your fist, it becomes so firm that it seems almost solid. At first, this appears completely impossible. In reality, this mixture is one of the best-known examples of a non-Newtonian fluid. Unlike water or cooking oil, the viscosity of many non-Newtonian fluids is not constant. Instead, it changes depending on the forces or the rate of deformation applied to them. There are many kinds of non-Newtonian fluids. Some become thinner when stirred rapidly, others become thicker. The familiar mixture of cornstarch and water, often affectionately called oobleck, belongs to the category known as a shear thickening fluid. When subjected to a sudden, powerful force, the starch particles become packed tightly together, temporarily resisting flow. For a brief moment, the mixture behaves almost like a solid, but as soon as the force disappears, it slowly returns to behaving like a liquid once again. At first, that seems contradictory. How can something be both soft and hard? Perhaps the answer is that nature is not confined by the tidy categories human beings enjoy creating. We like to classify everything. This is a solid. This is a liquid. This is right. This is wrong. Yet the more deeply we explore, the more we discover that many phenomena exist within wonderfully subtle transitions. Jung devoted much of his life to studying the opposing forces within the human psyche. He understood that every person carries both light and shadow, reason and emotion. Perhaps nature dislikes rigid boundaries as much as the human soul does. Again and again, it reminds us that reality is richer than any labels we choose to place upon it. Richard Feynman once said, "Nature uses only the longest threads to weave her patterns. So each small piece of her fabric reveals the organization of the entire tapestry." Perhaps that is exactly what these remarkable materials are quietly telling us. A little fluorescence, a strand of shape memory alloy, a bowl of oobleck. At first glance, they seem like tiny curiosities. Yet the longer we observe them, the more clearly we see that each reflects the way nature organizes the entire universe. Not rigidly, not monotonously, but with flexibility, elegance, and endless surprise. The night has now grown very deep. Somewhere outside, streetlights continue casting their gentle glow. Somewhere else, a fluorescent material quietly shines beneath ultraviolet light. A tiny medical device relies upon a shape memory alloy to help heal a patient. And in a laboratory, a bowl of oobleck is still making children smile with its delightful strangeness. Nature has never stopped telling stories. Every story simply waits for a mind patient enough to listen. Now that we have left behind the world of materials that glow in darkness, alloys that seem to remember their shapes, and liquids that behave in ways that challenge our intuition, perhaps you are beginning to realize that nature still has another remarkable storyteller, one that has accompanied humanity since the earliest civilizations. It is sand. At first glance, sand seems to be one of the most ordinary materials on Earth. You find it along beaches, beside rivers, across deserts, or perhaps as a few tiny grains clinging to the soles of your shoes after a walk. They are so small that almost no one pauses to think about them. But just like the atoms we explored in the previous chapter, it is often the most ordinary things that hide the deepest secrets. Pick up a handful of dry sand. When you close your hand, the sand keeps the shape of your palm. It behaves like a solid, but the moment you open your fingers, thousands of grains immediately slip past one another, flowing downward in a gentle stream. Now it behaves like a liquid. So what, exactly, is sand? According to modern physics, sand is neither a liquid nor a solid in the ordinary sense. It is what scientists call a granular material. Each individual grain of sand is a solid, but when enormous numbers of grains interact, the entire collection can behave in very different ways, depending on the circumstances. If the grains are packed tightly enough, friction between them becomes strong enough for the entire mass to hold its shape for a time. But when the forces change, the grains begin sliding past one another, and the sand starts to flow. The remarkable thing is this: nothing about the individual grains has changed, only the way they interact. Yet the entire system displays completely different behavior. Perhaps this is one of science's most beautiful lessons. A single grain of sand can accomplish very little on its own, but millions, billions, working together can build sand dunes hundreds of feet high, redirect rivers, shape coastlines, and help sculpt the landscapes of Earth itself. Human beings are much the same. A single neuron cannot think, yet tens of billions of neurons, connected together, give rise to memory, emotion, dreams, and consciousness. Perhaps nature enjoys telling the same story at many different scales. Carl Gustav Jung once wrote in The Structure and Dynamics of the Psyche, the greater the crowd, the more negligible the individual becomes. Perhaps physics invites us to see those words from another perspective. Within a large system, each individual component may seem almost insignificant. Yet, it is precisely the interaction among countless components that gives rise to entirely new properties. Properties no single component could ever possess alone. That is not the disappearance of individuality. It is the emergence of a new level of order, much like Jung's psychology, where countless individual experiences gradually weave together into a unified sense of self over the course of a lifetime. If you have ever wandered through a vast desert, perhaps you have heard an extraordinary story. Some sand dunes can sing. At first, that sounds more like poetry than science. Yet astonishingly, it is true. In certain deserts around the world, under just the right conditions, sand dunes can produce deep, resonant sounds that carry for miles. Scientists call the phenomenon booming dunes, or sometimes singing dunes. The sound can continue for several seconds or even longer, with frequencies that fall comfortably within the range of human hearing. Many ancient cultures believed those mysterious voices belonged to gods, or to the whispering spirit of the desert itself. Today, science has come much closer to understanding the phenomenon. When a large mass of dry sand begins sliding down the face of a dune, millions of grains collide and rub against one another. The astonishing part is that under very specific conditions, when the grains are fairly uniform in size, sufficiently dry, and the dune has the appropriate shape, the motion of enormous numbers of grains can become synchronized. That collective motion generates vibrations traveling through both the sand and the surrounding air, producing the deep sounds we can hear. Scientists continue studying the finer details of exactly how this remarkable phenomenon occurs. But one thing is certain: the desert is not literally singing. Those sounds arise because millions of tiny grains move together in astonishing harmony. Once again, nature requires no magic, only countless small things working together. That always reminds me of a choir. No single voice is powerful enough to create an entire symphony. But when each singer joins at precisely the right moment, something entirely new comes into being. Perhaps life is much the same. Meaning is rarely created only by life's grandest moments. It is built by countless small acts, repeated faithfully over time, that slowly compose the music of a human life. Richard Feynman once observed, It is interesting to think that the things on different scales behave according to the same laws. Although he expressed this idea in different ways throughout his career, its spirit runs through much of his work. Nature does not divide the universe into separate stories. The same physical laws governing the interactions between grains of sand also operate within planets, oceans, and our own bodies. Only the scale changes, the harmony remains. Perhaps Jung would say that each of us resembles a sand dune. No one is shaped by a single experience. We are the sum of countless memories, encounters, losses, hopes, dreams. Each one seems small by itself, yet together, resonating within the depths of the soul, they gradually form a unique identity, not in a single moment, but across an entire lifetime. The night has become wonderfully quiet. Imagine yourself standing in the middle of a vast desert. The stars stretch from one horizon to the other. A gentle wind passes by. Far away, the slope of a dune begins to move. Then, almost imperceptibly, a deep, resonant tone rises into the night. It is not the voice of a single grain of sand. It is the voice of millions moving together in harmony. Perhaps that is how the universe has always spoken, not through noise, but through the resonance of countless small things: an atom, a photon, a drop of water, a grain of sand, a human being. Each is wonderfully humble. Yet together, within nature's remarkable laws, they weave the immense story we call the universe. And perhaps, just as Carl Gustav Jung devoted his life to exploring the deepest layers of the human mind, science patiently listens to every grain of sand within reality, gradually discovering that the greatest beauty does not lie in extraordinary things. It lies in the way countless ordinary things come together to create a world far more marvelous than our imagination can fully grasp. In the next chapter, we will leave behind the singing dunes and journey even deeper into the laws of thermodynamics, entropy, and the arrow of time, where we will explore why everything changes, why order and disorder forever coexist, and what causes the universe to move relentlessly forward through the endless flow of time. Electricity and magnetism. As the deep voices of the singing dunes slowly fade into the night, as the vast desert quietly returns to its timeless silence, perhaps you feel that we have already traveled through many of the wonders of the physical world. From tiny atoms to enormous stars, from light, sound, water, and fire, to remarkable materials that seem almost borrowed from a fairy tale. Yet if there is one mystery even more elusive than anything our eyes can see, it is the invisible forces themselves. You cannot see them, you cannot hold them in your hands, you cannot hear them, and yet they are everywhere. Even now, here in the very room where you are resting, between the atoms of your blanket, among the strands of hair gently touching your pillow, within the screen casting its soft glow, even inside every neuron helping you listen to these words. Perhaps electricity and magnetism are not inventions of humanity at all. They are ancient parts of the universe itself. Let us begin with a phenomenon almost everyone has experienced. Perhaps, as a child, you pulled off a wool sweater on a cold winter day and heard tiny crackling sounds. Or perhaps you reached for a doorknob and suddenly felt a sharp little sting at your fingertip. At first, it seems like one of nature's playful tricks, but it is simply static electricity. Within the world of atoms, positively charged protons remain bound inside atomic nuclei. Negatively charged electrons, however, are much more mobile. When two materials rub against one another, some electrons can move from the surface of one material to the other. No new electric charge is created. The electrons have merely changed where they reside. The object that loses electrons becomes relatively positively charged. The object that gains electrons becomes relatively negatively charged. That tiny imbalance is enough to create electric forces strong enough for us to feel with our own hands. The remarkable thing is this: everything begins with particles far too small to be seen. Perhaps human emotions work in much the same way. A conversation, a glance, a word of encouragement, an unintended remark. At first, each seems so small, yet sometimes the slightest shift in the emotional balance within us can change an entire day, a year, or even a lifetime. Some of the most powerful things cannot be seen, yet they carry tremendous force. Carl Gustav Jung once wrote in The Undiscovered Self, "Everything that irritates us about others can lead us to an understanding of ourselves." Perhaps electric charge teaches us something similar. It is difference that creates interaction. If everything were completely identical, the universe would become strangely silent. No attraction, no repulsion, no motion. It is the smallest differences that make the world come alive. There is a simple experiment that children all over the world love. Inflate a balloon, rub it against your hair or a wool sweater, then gently press it against a wall. Remarkably, the balloon sticks there. No glue, no tape, no hook. What is happening? During rubbing, the balloon typically gains extra electrons and becomes negatively charged. The wall, overall, remains nearly electrically neutral, but as the balloon approaches, the electric charges within the material near the wall's surface shift ever so slightly. Charges of the same sign are pushed a little farther away. Opposite charges move slightly closer to the surface. This tiny redistribution of charge, called polarization, creates an electrostatic attraction between the balloon and the wall. The remarkable thing is this: the wall does not need to be electrically charged beforehand. Its charges only need to shift by an almost unimaginably small amount. That tiny rearrangement is enough to create a noticeable force. It is a beautiful reminder that even the smallest changes at the microscopic level can produce visible effects in the everyday world. Sometimes I think human relationships work the same way. Connection does not always arise because two people are identical. Sometimes the simple presence of one person quietly shifts something deep inside another. No one sees it, no instrument measures it, yet a bond begins to form. Jung devoted many years to studying the subtle ways human beings influence one another through the deeper layers of the unconscious. Perhaps those invisible changes leave the deepest marks of all. Then nature tells us a far more dramatic story. If static electricity is a whisper, lightning is the voice of the sky. Imagine an enormous thundercloud gathering overhead. Within it, droplets of water, ice crystals, and tiny pellets of hail collide endlessly as powerful air currents carry them upward and downward. Through countless collisions, electric charge gradually becomes separated. Typically, the lower portion of the cloud accumulates an excess of negative charge, while the upper portion becomes relatively more positive, although the actual charge structure of a thunderstorm can be considerably more complex. When the electric field between charged regions, or between the cloud and the ground, becomes strong enough to overcome the insulating properties of the air itself begins to ionize. A conductive channel forms, and then, in less than the blink of an eye, an enormous electric current races across the sky. That is lightning, not because positive and negative charges somehow want to meet, but because the system is transitioning into a lower energy state by discharging its accumulated electrical energy. The light from a lightning bolt reaches our eyes almost instantly. The thunder always arrives later. The reason is beautifully simple. Light travels at nearly 300,000 kilometers per second. Sound moves through air at only about 343 meters per second under ordinary conditions. As lightning's tremendous electric current passes through the atmosphere, it heats the surrounding air to temperatures of tens of thousands of degrees Celsius in an extraordinarily short time. The air expands explosively. That sudden expansion creates a pressure wave traveling through the atmosphere. We hear that wave as thunder, which means thunder is not the sound of electricity itself. It is the sound of air responding to the intense heating caused by the lightning. Even thunder is ultimately a story about the atmosphere. Perhaps since humanity's earliest days, people have looked toward thunderstorms with both fear and reverence. Across many ancient cultures, lightning was believed to be the weapon of gods. Today, science has given us a far deeper understanding of the processes behind it. Yet that knowledge has not made the sky any less magnificent. Quite the opposite. Realizing that trillions upon trillions of electrons move together in a single instant, that the entire atmosphere participates in an immense physical process, makes lightning even more astonishing. Richard Feynman once said, "I think nature's imagination is so much greater than man's, she's never going to let us relax." Perhaps he was exactly right. The more deeply we understand nature, the more we discover that reality is richer than our own imagination. The night has become wonderfully peaceful. Perhaps the sky outside your window is perfectly clear, not a single cloud in sight. It is almost impossible to believe that the same gentle sky is capable of producing lightning brilliant enough to illuminate an entire landscape. Perhaps the human mind is much the same. Beneath outward stillness, invisible currents of energy are always moving. Thoughts not yet spoken, emotions not yet named, changes so subtle that no one notices them at first, and then, at precisely the right moment, everything comes together to create a single flash capable of transforming the entire inner sky. As the thunder from our previous story slowly fades beyond the horizon, as those brilliant flashes become only memories within the night, perhaps you are beginning to realize that the story of electricity is far from over. For after every lightning bolt, for behind every bolt of lightning, behind every electron quietly changing its position, behind every invisible force that allows a balloon to cling to a wall, there is still another silent guardian that most of us have never seen. It has no shape, no color, no sound, yet without it, the earth on which we are peacefully sleeping tonight might have become a very different world. It is Earth's magnetic field. If we could see the magnetic field with our own eyes, the sight would surely leave us speechless. Instead of appearing as a simple sphere drifting through space, Earth would seem wrapped in countless graceful curves, extending far beyond the planet. They embrace our world, stretching tens of thousands of kilometers toward the Sunday, and extending even farther in the opposite direction, where the solar wind constantly streams past. For centuries, people imagined that Earth was simply a giant bar magnet floating in space. That picture is useful for explaining many observations, but modern science reveals a story even more fascinating. Earth's magnetic field does not originate from a massive permanent magnet hidden at the planet's center. Instead, it is generated primarily by the geodynamo. Deep beneath our feet, within Earth's outer core, iron and nickel exist in a molten state, driven by heat escaping from Earth's interior. Together with the planet's rotation, this electrically conducting liquid is in constant motion. Those flowing currents of molten metal generate electric currents. Those electric currents, in turn, generate magnetic fields. Together they form a self-sustaining cycle that has endured for billions of years. Which means the invisible shield protecting our world is not a motionless object. It is the living expression of a planet whose deepest interior remains astonishingly active. Perhaps that reminds me of the human spirit. Some people seem wonderfully calm, gentle, peaceful, yet that peace does not exist because nothing moves within them. Quite the opposite. Perhaps it is because they have lived through countless collisions, countless transformations, countless moments of quiet self-correction, that they have finally discovered such steadiness. The surface may appear tranquil, while the depths continue moving silently. Perhaps Earth is much the same. Carl Gustav Jung once wrote in Aeon, "The meeting of two personalities is like the contact of two chemical substances. If there is any reaction, both are transformed." Perhaps nature itself lives through interactions. Without motion, without transformation, there would be no magnetic field. Without encounters, human beings would struggle to grow. Life is not sustained by stillness, but by continuous transformation. There is one small object that helped humanity explore nearly the entire world. It is the compass. Today, in an age of satellites and global positioning systems, the compass seems almost ordinary. But imagine yourself as a sailor 1,000 years ago. Water stretches in every direction. No land is visible. No satellite maps. No radio signals. Only the sky. And a tiny needle quietly turning. The remarkable thing is that the needle almost always settles into a stable direction, not because it somehow knows where north is, but because it responds to Earth's magnetic field. A compass needle is itself a small magnet. It has two magnetic poles. When allowed to rotate freely, it aligns with the local magnetic field. One particularly delightful detail is this. The end, called the north-seeking pole, points toward the region near Earth's geographic North Pole because, in the language of physics, that region corresponds to a magnetic South Pole. Opposite magnetic poles attract, so the compass's north-seeking end is drawn in that direction. It is a tiny detail, yet it reminds us that names and physical reality are not always exactly the same thing. Perhaps a compass resembles intuition. It cannot always explain why it chooses a particular direction, yet when placed within a quiet enough environment, it slowly turns toward its true orientation. Jung devoted many years to studying intuition as one of the fundamental functions of the human psyche. He never regarded intuition as magic. Rather, he saw it as a way of recognizing deeper patterns before conscious thought can fully express them. A compass behaves much the same way. It does not think. It does not choose. It simply responds faithfully to the invisible forces surrounding it. Yet perhaps the most breathtaking expression of Earth's magnetic field appears far from where most of us live, near the planet's poles. During the long nights of winter, where the sky suddenly blossoms into flowing ribbons of green, purple, pink, and crimson light. These are the auroras. For thousands of years, people created countless legends to explain these extraordinary lights. Some believed they were the spirits of ancestors. Others imagined the gods dancing across the heavens. Still others saw them as a bridge connecting earth and sky. Today, science tells us a different story. And somehow, that story is every bit as beautiful. The sun does far more than emit light. It continuously releases a stream of charged particles, composed primarily of protons and electrons. This stream is known as the solar wind. Without Earth's magnetic field, these energetic particles would strike our atmosphere far more directly and intensely. Fortunately, Earth's magnetosphere deflects most of them. Near the polar regions, however, some of these charged particles are guided along magnetic field lines into the upper atmosphere. There, they collide with atoms and molecules, especially oxygen and nitrogen, transferring energy to them. Later, as those atoms and molecules return to lower energy states, they emit light. Oxygen, at different altitudes, can produce brilliant green or deep red light. Nitrogen contributes beautiful shades of blue and violet. What we call the aurora is simply the light emitted by atoms and molecules releasing that stored energy. The sky is not glowing on its own. Rather, it is the atmosphere responding to its encounter with particles arriving from the sunday. Richard Feynman once said, "The imagination of nature is far, far greater than the imagination of man." Perhaps anyone who has witnessed the aurora understands those words a little more deeply. Human beings can paint magnificent works of art, but nature uses the magnetic field of an entire planet, the wind of a star, and the atoms within an atmosphere to create a light show that has continued for billions of years. No audience, no stage, no conductor. Everything simply follows the faithful laws of the universe. Perhaps the most beautiful lesson of this chapter is realizing that the things protecting us are often invisible. No one sees Earth's magnetic field while walking outside. No one feels the countless magnetic field lines embracing the planet. Yet every day, that invisible shield quietly deflects most of the charged particles carried by the solar wind, helping preserve both our atmosphere and the stable conditions that make life possible. Perhaps the human soul possesses invisible magnetic fields of its own, a cherished memory, a sincere love, a quiet belief, a lesson from a parent, a book read many years ago. None of these can be seen, yet each quietly influences the way we think, choose, and continue forward. The night has now grown very deep. Perhaps only a few stars shimmer outside your window. There are no auroras, no thunderstorms, no compass resting beside you. And yet, all of them are still present. Earth's magnetic field continues wrapping itself gently around our planet. Electrons never stop moving. The solar wind continues sweeping across the immense distances between the planets. And somewhere near the polar regions, perhaps at this very moment, the sky is being woven into flowing ribbons of light that we call the aurora. Nature has never needed to announce its beauty. It simply continues following the laws that have governed our solar system since its earliest beginnings. Perhaps the human mind is much the same. Its deepest truths are rarely loud. They resemble a magnetic field, invisible, gentle, yet powerful enough to guide an entire lifetime. And in the next chapter, we will continue that journey by entering the world of thermodynamics and entropy, exploring why everything changes with time, why order and disorder forever coexist, and what causes time itself to seem to flow in only one direction across the vast universe. The sun and nuclear energy, as the shimmering curtains of the aurora slowly fade into the night, as charged particles from the sun continue their silent journey across the immense emptiness of space. And Earth's magnetic field quietly embraces our planet like a guardian that never sleeps. Perhaps you begin to realize that every story we have explored has been pointing toward the same source, a light that awakened long before humanity ever learned to kindle its first fire, a source of energy that has warmed Earth for more than 4 billion years. Every sunrise you have ever seen, every green leaf trembling in the breeze, every drop of water that evaporates into a cloud, every heartbeat of every living creature, each carries something of its gift. It is the Sunday, yet there is something rather fascinating. Although we have seen the sun every day of our lives, most of us instinctively imagine it as an enormous fire burning in the sky. It is a perfectly natural image. But as with so many things in science, the truth is far more extraordinary. Think of a burning candle or a log crackling inside a fireplace. That flame exists because of a chemical reaction. Carbon and hydrogen atoms within the fuel react with oxygen in the air. That process releases energy in the form of heat and light. We simply call it combustion. But if the sun produced its energy the same way, it would have gone dark long ago. Physicists have calculated that if the sun generated energy only through chemical reactions like an enormous fire, its fuel would last only a few thousand to perhaps a few tens of thousands of years. Far too short compared with the sun's actual age of about 4.6 billion years. That discrepancy became one of the great scientific mysteries of the 19th century. What could possibly keep the sun shining for so long? The answer emerged only after humanity began exploring the hidden world inside atoms. The first thing to understand is this: the sun is not a ball of fire. It is primarily a vast sphere of plasma. Plasma is often called the fourth state of matter, alongside solids, liquids, and gases. If enough energy is supplied to a gas, its atoms can lose some of their electrons. The material is no longer an electrically neutral gas. Instead, it becomes a mixture of positively charged ions and freely moving electrons. That mixture is plasma. Unlike an ordinary gas, plasma conducts electricity extremely well and responds strongly to electric and magnetic fields. Remarkably, plasma does not exist only inside stars. You encounter it in lightning, in neon signs, in certain fluorescent lamps, and in many modern industrial technologies. Yet most naturally occurring plasma exists at extraordinarily high temperatures. In fact, when we look across the observable universe, more than 99% of ordinary visible matter is believed to exist in the plasma state, which means what we consider perfectly ordinary here on Earth, rocks, water, and air, is actually the exception. Most of the universe is made of an entirely different state of matter. There is something wonderfully humbling about that realization. Human beings often assume that the world surrounding us represents the standard for the entire universe. Yet the more we discover, the more we realize that Earth is only a tiny island within a vast ocean of difference. Perhaps Carl Gustav Jung's psychology offers us a similar lesson. What consciousness sees is only a small part of the whole. Beneath it stretches an immense ocean of the unconscious. What we call normal is sometimes merely our own experience, not the full extent of reality. Jung once wrote in The Undiscovered Self, "The world today hangs by a thin thread, and that thread is the psyche of man." Perhaps science and psychology are quietly teaching the same lesson. If we wish to understand the world, we must first accept that it is far larger than we ever imagined. If the sun does not burn like a fire, then what is happening inside it? Imagine traveling deep into the sun's core. The pressure grows greater. The temperature climbs ever higher, until it reaches roughly 15 million degrees Celsius. There, hydrogen nuclei no longer drift gently as they might inside a laboratory on Earth. They race about at astonishing speeds. Under those extraordinary conditions, and with the help of quantum tunneling, one of quantum mechanics' most remarkable phenomena, which allows particles a finite probability of passing through an energy barrier that classical physics says they could not cross, some hydrogen nuclei can come close enough for the strong nuclear force to bind them together. Through a sequence of intermediate steps, 4 hydrogen nuclei are ultimately transformed into one helium nucleus. This process is known as nuclear fusion. The remarkable part is this: the helium nucleus has slightly less mass than the combined mass of the 4 original hydrogen nuclei. That missing mass has not it has been converted into energy, according to Albert Einstein's famous equation, E Mach 3. That energy is what has allowed the sun to shine for billions of years. Every second, the sun transforms roughly 600 million tons of hydrogen into helium. About 4 million tons of mass are converted directly into energy, radiating into space as light, heat, neutrinos, and other forms of radiation. Those numbers sound almost unimaginably large. Yet compared with the sun's total mass, the process is gentle enough that our star will continue shining steadily for billions of years to come. Perhaps this is one of the most beautiful ideas science has ever uncovered. The sunlight touching your face each morning is not born from destruction. It is born from union, not from burning something away, but from bringing things together. 4 tiny nuclei become one new structure, and from that transformation comes the energy that nourishes an entire planetary system. Perhaps people are much the same. The most beautiful things in life rarely arise from separation. They grow from connection, a friendship, a family, a community, or the reconciliation of different parts within one's own soul. Jung called that lifelong journey individuation, the gradual integration of what once seemed separate into a more complete human being. Carl Sagan once wrote in Cosmos, "We are a way for the cosmos to know itself." Whenever I think about nuclear fusion inside the Sunday, I remember those words. For the hydrogen nuclei fusing nearly 150 million kilometers away are the source of the light that nourishes forests, oceans, and every living thing. Going back even farther, the heavier elements composing our own bodies were forged inside earlier generations of stars. Perhaps, in a profoundly beautiful sense, the universe does not merely exist around us, it also exists within us. The night has become wonderfully deep. Perhaps the sun now lies on the far side of Earth. You cannot see it, yet tomorrow's sunlight has already begun its journey. Even now, countless fusion reactions continue quietly within the sun's core. New photons are beginning an extraordinarily long voyage through the star's dense interior before eventually escaping into space and crossing the vast distance to Earth. Nature has never been in a hurry. Patiently, it creates light through laws that have operated for billions of years. Perhaps the human soul grows in much the same way. Our deepest transformations rarely appear overnight. They are formed gradually, quietly, like the fusion reactions unfolding within the heart of the Sunday, as the gentle sunlight from our previous chapter slips beyond an imagined horizon. As nuclear fusion continues silently within the core of the star, nearly 150 million kilometers away, perhaps you begin to realize that humanity has spent centuries asking one remarkably ambitious question. Could we ever truly understand the source of the energy that powers the stars? And beyond that, could we learn to harness the energy hidden inside the tiniest atoms themselves? It is a journey that is both dazzling and filled with profound responsibility. It was a journey that transformed science, medicine, archaeology, and even the way humanity understands time itself. If nuclear fusion within the Sun is the story of things coming together, then here on Earth humanity first learned to harness a process that is, in many ways, its opposite. That process is nuclear fission. Imagine a very large atomic nucleus, such as uranium-235. Under the right conditions, after absorbing a neutron, the nucleus becomes unstable. It splits into two smaller nuclei while releasing several additional neutrons and an enormous amount of energy. That energy comes from the tiny difference in mass between the nucleus before and after the reaction. Once again, following Einstein's famous equation, m=. What makes this especially remarkable is that the newly released neutrons can strike other uranium nuclei. If enough of those neutrons continue the process under carefully controlled conditions, the reaction sustains itself. This is known as a chain reaction. Inside nuclear power plants, control rods that absorb neutrons regulate the reaction, allowing energy to be released steadily. That heat produces steam. The steam turns turbines, and the turbines generate electricity. Inside a nuclear weapon, however, the chain reaction proceeds extraordinarily rapidly and without control. Two applications, built upon the same physical principle, yet leading to profoundly different outcomes. Perhaps nature itself does not decide what is good or evil. It is human beings who choose how knowledge is used. That reminds me of a familiar reflection from Carl Gustav Jung. He believed that the greater one's power, the greater one's responsibility toward the shadow within oneself. Knowledge is much the same. A scientific discovery carries no morality of its own. It simply creates possibilities. How we choose to use those possibilities becomes part of humanity's story. Jung once wrote in The Undiscovered Self, "The least of things with a meaning is worth more in life than the greatest of things without it." Perhaps the greatest wonder of all is realizing that we do not stand outside this story. We are part of it. We are beings fashioned from stardust, given a fleeting moment in the lifetime of the universe to look up at the night sky, ask where we came from, and quietly search for meaning within the endless flow of time. And in the next chapter, we will continue that journey by exploring the limits of perception and the remarkable paradoxes of modern physics, where science once again reminds us that the universe is always greater than anything the human imagination can fully embrace. Modern particle physics. As the story of atoms from our previous chapter gently settles, as carbon-14 continues patiently keeping time within ancient pieces of wood, and sunlight quietly begins another day's journey across space, perhaps you realize that our own journey has not yet reached its deepest destination. For if atoms were once believed to be the smallest building blocks of the universe, modern science has quietly opened another door. Beyond the atom, there are still smaller particles, and beyond those particles, there are invisible fields extending throughout all of space. Perhaps the deeper we travel into the material world, the less we encounter the tiny, solid marbles our imagination once pictured. Instead, we discover a universe that is gentler, more subtle, and far stranger than we ever expected. Imagine that one day you become curious about the inner workings of an antique clock. You could open its case, examine each gear. But what if you wanted to understand what lies inside one of those tiny gears? At the scale of the fundamental particles, the challenge becomes vastly greater. They are far too small to be seen through any optical microscope. Even the most powerful electron microscopes do not see fundamental particles the way our eyes see ordinary objects. So how did humanity discover this hidden world? One of the most extraordinary tools ever created by science is the particle accelerator. Its name sounds intimidating, yet the underlying idea is beautifully simple. If we wish to understand what something is made of, sometimes we must collide particles at extremely high energies and carefully study what emerges afterward. It is rather like taking apart a clock in a controlled way, not to destroy it, but to understand it. Modern particle accelerators use electric fields to accelerate charged particles until they are traveling at speeds extremely close to the speed of light. Then magnetic fields guide and bend their paths with remarkable precision. At their largest, these machines occupy tunnels stretching for many kilometers. The most famous example is the Large Hadron Collider, or LHC, at CERN. Located beneath the border between France and Switzerland, its circular tunnel measures about 27 kilometers in circumference. Inside, two beams of protons travel in opposite directions at speeds extraordinarily close to that of light. When they are brought into collision, the concentrated energy at the impact point can produce entirely new particles, according to Einstein's famous relation, Macquardt. This does not mean that energy is created from nothing. Rather, mass and energy are continuously transformed into one another according to the precise laws of nature. Enormous detectors surrounding the collision points record the traces left behind by countless newly created particles, allowing physicists to infer deeper layers of matter's structure. No one directly observes most fundamental particles themselves. We read their stories through the footprints they leave behind. There is something deeply beautiful about the way science works. Human beings cannot see everything with their eyes, yet that has never prevented us from learning how to listen. A trembling leaf tells us the wind is present. Ripples across a quiet lake reveal that a stone has fallen into the water, and inside a particle accelerator, tiny patterns recorded by detectors tell us about particles that existed for only the tiniest fraction of a second. Perhaps understanding does not always begin with seeing. Sometimes it begins with learning how to interpret invisible traces. Carl Gustav Jung once wrote, "In memories, dreams, reflections, the least things with a meaning are worth more in life than the greatest things without it." Those words seem to echo through modern particle physics. A tiny signal inside a detector, a faint curve hidden within the data, an almost imperceptible discrepancy among billions of measurements. Sometimes those smallest clues open an entirely new chapter of understanding. It is not size that determines significance. It is the story being told. Throughout the 20th century, physicists gradually assembled an increasingly complete picture of the fundamental particles. Yet one profound question remained. If particles move freely through space, why do many of them possess rest mass? Why is the electron so much lighter than the proton? Why is the photon massless, while the W and Z bosons possess rest mass? To answer these questions, physicists developed one of the deepest ideas in modern science, the idea of the Higgs field. In modern physics, a field is not a field in the everyday sense of an open meadow. It is a physical quantity that exists throughout space and time. We have already encountered such fields: the electric field, the magnetic field, the gravitational field. The Higgs field is another quantum field of this kind. According to the standard model of particle physics, the Higgs field permeates nearly all of the universe. Fundamental particles interact with this field to different degrees. Those interactions give rise to the rest masses of many elementary particles, including electrons, quarks, and the W and Z bosons. One important point deserves emphasis. The Higgs field does not account for all of the mass of every object. For example, most of the mass of protons and neutrons actually comes from the energy associated with the strong interaction binding quarks and gluons together inside them. Nature is always subtler than our simplest explanations. Many people have compared the Higgs field to a thick fluid through which particles must move. That analogy is useful as a first intuition. But more precisely, the Higgs field is not a literal viscous medium that slows particles down. It is a quantum field governed by its own mathematical laws. And particle interactions with that field are described within the framework of the Standard Model. Metaphors help us begin to understand. Nature itself always goes deeper than any metaphor. In 2012, after decades of theoretical work and experimental effort, scientists working at the Large Hadron Collider announced compelling evidence for the existence of the Higgs boson. The Higgs boson is not the Higgs field itself. Rather, it is the quantum excitation of the Higgs field, much as the photon is the quantum excitation of the electromagnetic field. That discovery did not complete the story. Instead, it confirmed a crucial part of the Standard Model, while opening many new questions about the universe's deepest foundations. Perhaps every great answer becomes the doorway to even greater mysteries. That reminds me of the journey of self-discovery. Jung believed that the deeper we explore the human psyche, the more we realize that we are not merely our conscious selves. Beneath consciousness lies the personal unconscious. Beyond that, the collective unconscious. Hidden depths connecting every individual to something far greater than themselves. Modern particle physics seems to tell a remarkably similar story. The deeper we descend into the foundations of matter, the fewer simple building blocks we find. Instead, we encounter invisible fields, elegant symmetries, and laws that can be expressed only through the language of mathematics. Perhaps the invisible has never been the same as the unreal. Albert Einstein once said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and all science." Perhaps it is precisely that sense of mystery that inspired humanity to build the largest machines ever constructed in order to explore the smallest known particles. Not because we wish to conquer the universe, but because, deep within us, we carry a remarkably gentle longing. The longing to understand, to know where we came from. The night has become wonderfully quiet. Perhaps, outside your window, only a handful of stars sparkle against the deep black sky. It is astonishing to think that somewhere beneath Earth's surface, enormous machines are quietly accelerating tiny particles to speeds approaching that of light, not to manufacture miracles, but to listen to the stories that nature has been whispering for nearly 14 billion years. Perhaps the human mind is much the same. The quieter it becomes, the more it discovers that the most important things are rarely loud. They exist like invisible fields, unseen, untouchable, yet powerful enough to shape the way we understand ourselves and the universe. As the enormous machines from our previous chapter gradually fade into silence, as protons continue their quiet journeys at nearly the speed of light through tunnels deep beneath the Earth, perhaps you feel that we have reached the very foundations of the material world. And yet, just as Carl Gustav Jung would repeatedly discover deeper layers of the human mind each time he believed he had reached understanding, modern physics continues opening new questions. Perhaps the greatest mystery is not what matter is made of, but this: what if every particle in the universe had an almost identical companion, a perfect reflection, a kind of shadow of itself? Imagine standing before a mirror. The person looking back appears almost exactly like you. Only left and right have been reversed. In the world of fundamental particles, nature also seems to delight in creating elegant symmetries. For many particles of ordinary matter, there exists a corresponding antiparticle. The electron has the positron, sometimes called the anti-electron. The proton has the antiproton. The neutron has the anti-neutron. These antiparticles possess the same rest mass and many of the same physical properties as their ordinary counterparts. They differ, however, in certain quantum numbers, most notably electric charge. The positron carries a positive electric charge. The electron carries a negative one. This does not mean that antimatter is reversed matter or matter traveling backward through time. It is simply another form of matter composed of antiparticles, obeying the very same fundamental laws of physics as ordinary matter. a world that is at once familiar and wonderfully strange. The remarkable thing is that antimatter was never merely an invention of imagination. It began as a theoretical prediction. In 1928, physicist Paul Dirac developed an equation describing the electron that successfully united quantum mechanics with special relativity. Unexpectedly, the mathematics also allowed solutions corresponding to a particle with the same mass but the opposite electric charge. A few years later, in 1932, the positron was observed in experiments studying cosmic rays. An idea that had first appeared on paper became part of reality itself. Perhaps nature is always prepared to exceed our imagination. If matter and antimatter both exist, what happens when they meet? The answer is both beautiful and extraordinarily powerful. When an electron encounters a positron, they can undergo a process known as annihilation. This does not mean that energy disappears, nor does it mean that matter simply vanishes without a trace. According to the conservation of energy and momentum, the rest mass of the particle pair, together with their kinetic energy, is converted into extremely energetic gamma-ray photons. Once again, Einstein's equation, E max waved, appears as the bridge connecting matter and energy. The remarkable thing is that nature favors neither side. It simply remains faithful to its laws. Matter can become energy, and under suitable conditions, energy can also produce pairs of particles and antiparticles. Between these two realms, an endless, silent conversation continues. Perhaps that brings to mind the opposing forces within the human soul. Jung devoted much of his life to reminding us that we are not made only of the qualities we readily embrace. We are also shaped by the parts of ourselves we hesitate to face. He called one of those hidden dimensions the shadow. An important distinction deserves to be made here. Antimatter is not Jung's shadow. The comparison is only a gentle metaphor, for both physics and psychology seem to suggest a similar truth. Reality is richer than our first impressions. Behind every familiar thing, there may exist something that complements it, not to contradict it, but to complete the picture. Carl Gustav Jung once wrote in Aeon, "One does not become enlightened by imagining figures of light, but by making the darkness conscious." Those words were never intended as a statement about physics, yet they offer a beautiful attitude toward discovery. Do not fear what is unfamiliar. Patiently seek to understand it. Human beings do not mature by denying what they have yet to comprehend. Science grows in much the same way. Every mystery is an invitation. And then, perhaps the most beautiful question of all appears. If every particle has an antiparticle, if the Big Bang is believed to have produced matter and antimatter in nearly equal amounts, then why does today's universe appear to consist almost entirely of matter? This remains one of the greatest unanswered questions in modern physics. Everything familiar around us, galaxies, stars, planets, human beings, nearly every known cosmic structure, appears to be made of ordinary matter. Had matter and antimatter been created in perfectly equal amounts and then completely annihilated one another, almost nothing would have remained except radiation. A universe like the one we inhabit might never have formed. That suggests that somewhere during the universe's earliest moments, an exceedingly small imbalance developed between matter and antimatter. Only a tiny excess of matter surviving those annihilations would have been enough to build every star, every planet, and every living creature we see today. Physicists have discovered certain instances of CP violation in specific particles, yet the mechanisms currently known are still far too small to fully explain why matter came to dominate the universe. The mystery remains unsolved, another secret that nature has not yet completely revealed. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." Those words were never a surrender. They were an expression of humility. Understanding is not a destination, it is a journey. The more we discover, the more new horizons appear before us. Perhaps the greatest beauty of science is not that it possesses every answer, but that it continues offering questions large enough to make humanity look toward the stars. Sometimes I find myself wondering, What inspires our species to spend centuries studying particles so small that no one can ever see them directly? Perhaps it is not only technology, not only energy, not only knowledge. Perhaps exploring the fundamental particles is also a way of exploring ourselves. Carl Sagan once wrote in Cosmos, "We are a way for the cosmos to know itself." If that is true, then every equation, every experiment, every question about antimatter, every sleepless night spent inside the control room of a particle accelerator becomes a moment in which the universe is trying to understand itself through us. The night has become profoundly still. Perhaps the sky outside your window remains filled with stars. Their light has traveled across years, thousands of years, or even millions of light years, before finally reaching the place where you are resting. Somewhere within that vastness, particles of matter and antimatter continue to be created in the universe's most energetic events. Somewhere, the greatest questions in physics are still waiting for future generations to explore. And perhaps the most beautiful thing is not that one day we may uncover every secret of the universe. Perhaps the greatest beauty is that the universe remains vast enough to nourish our curiosity, mysterious enough to keep the human spirit humble, and generous enough that every answer quietly opens the door to another question. Perhaps the human mind is much like the night sky. The quieter it becomes, the more stars it can see, the more willingly we accept that we do not know everything, the closer we come to wisdom. And in the next chapter, we will step into an even deeper realm of reflection, where physics meets philosophy, where the limits of perception, time, and existence itself invite us to continue exploring who we are beneath the endless sky of the universe. When we first began this journey, perhaps you simply wanted to listen to a few gentle stories before drifting off to sleep. Yet, chapter by chapter, those stories carried us farther than either you or I might ever have imagined. Together, we looked up into the night sky and wondered why the stars shine. We quietly wandered among distant galaxies, listened to the whispers of black holes, followed light that traveled for millions of years before reaching our eyes, then returned to Earth to admire a soap bubble shimmering in the sunlight, a rainbow after the rain, a small flame glowing in the quiet darkness, or the gentle melodies drifting softly through a peaceful room. At first glance, none of these things seem connected. On one side, galaxies stretching across hundreds of thousands of light years. On the other, a tiny drop of water resting on your fingertip. On one side, fundamental particles no one can ever see. On the other, a piece of music you love. Yet, the farther we have traveled through physics, the more clearly we have discovered something extraordinary. They have all been telling the very same story. Perhaps that is the greatest gift physics has to offer. Not formulas, not numbers, but connection. The same laws that guide galaxies around their centers also keep Earth moving around the Sunday. The atoms forged within ancient stars now make up every cell of your body. Photons that left the sun about 8 minutes ago are now gently touching the curtains beside the place where you are resting. Tiny vibrations of the air become sound within your ears, and delicate electrical signals quietly travel through billions of neurons, allowing you to understand every word of this story. There is no true boundary between the physics of the universe and the physics of human life. There is only one nature, expressing itself across different scales. For a very long time throughout history, humanity believed that the heavens and the earth obeyed two different sets of laws. The celestial bodies belonged to a perfect realm. We belong to a world of constant change, yet science gradually revealed something entirely different. The apple falling to the ground and the moon orbiting the earth are governed by the same force of gravity. The light arriving from a distant star and the light from the candle before you are both electromagnetic waves. The carbon atoms inside a leaf and those within the human heart obey the very same laws of quantum mechanics. Perhaps the universe has never truly divided itself. Only our understanding once imagined that everything was separate. Carl Gustav Jung once wrote in Memories, Dreams, Reflections, Who looks outside, dreams. Who looks inside, awakes. Perhaps throughout this journey, we have done both. We have looked outward, toward galaxies, black holes, stars, fundamental particles. Yet the farther we traveled, the more that journey quietly led us back to ourselves. For every new understanding of the universe also revealed something about humanity's place within it, and every deeper look into our own minds reminded us that we have never been separate from nature. Think of a black hole. For many years it was regarded as the ultimate symbol of destruction. Yet modern physics has revealed that black holes do far more than simply swallow everything around them. They are natural laboratories where gravity, space-time, and quantum physics meet under the most extreme conditions imaginable. Even the darkest places in the universe are helping us understand light. Perhaps life is much the same. Sometimes it is the darkest moments that teach us the most. Not because darkness is more beautiful than light, but because only after passing through darkness do we truly appreciate the coming of dawn. Then look toward the galaxies. Each galaxy contains hundreds of billions of stars. Our own Milky Way is only one among hundreds of billions of galaxies within the observable universe. The numbers become almost impossible to imagine. Yet every one of those immense cosmic structures is built from the same fundamental particles we encountered throughout these chapters. Electrons, quarks, photons. Nature seems never to have needed a new alphabet to write the galaxies. It simply rearranged the same familiar letters into ever richer stories. Then we return once more to the atom. There was a time when it was believed to be indivisible. Today we know that within every atom lie nuclei, electrons, quarks, and invisible quantum fields. Yet the deeper we journey into the foundations of matter, the less reality resembles the solid objects our intuition expects. Reality is far more subtle than appearances suggest. Perhaps people are much the same. What you see in another person is only the surface. Beneath it lie memories, experiences, fears, hopes, and dreams that have never been spoken aloud. A soap bubble may exist for only a few fleeting seconds, yet upon its delicate surface, light is constantly interfering, reflecting, and creating colors that endlessly change. Not because the rainbow colors already exist inside the bubble, but because tiny variations in the thickness of the thin film cause different wavelengths of light to reinforce or cancel one another in different ways. A phenomenon governed by remarkably precise physics, creating a moment many people simply call poetry. Perhaps science and beauty have never truly stood apart. They are simply two different ways of seeing the same wonder. Then, after the rain, the rainbow appears. Tiny droplets of water become countless little prisms. Sunlight is refracted as it enters each droplet, reflected once inside, and refracted again as it emerges, separating different wavelengths into their familiar colors. There is no magic involved. Yet understanding the natural laws behind the rainbow does not diminish its beauty. Quite the opposite. Perhaps understanding allows beauty to become even deeper. A small fire burning quietly in a fireplace tells another story. Fire is not a substance of its own. It is a collection of chemical reactions in which fuel combines with oxygen, releasing energy as heat and light. The flame does not exist apart from that process. The flame is that process. Perhaps many things in life are much the same. Happiness is not a destination. It is the way we choose to live each ordinary day. Richard Feynman once said, "Nature uses only the longest threads to weave her patterns." So each small piece of her fabric reveals the organization of the entire tapestry. Perhaps no quotation better captures the journey we have shared. A tiny soap bubble, an atom, a rainbow, a flame, a galaxy, or a black hole. Every piece reflects something about the vast tapestry we call the universe. The night has now become wonderfully peaceful. Perhaps a gentle breeze is moving outside your window. Somewhere far away, a new star is still being born from clouds of gas and dust. Elsewhere, a black hole continues bending space-time with its immense gravity. Here in this quiet room, the soft photons from your bedside lamp still reflect gently from the wall. The air continues to vibrate into sound, and the trillions upon trillions of atoms within your body continue obeying the same laws that have existed since the universe was very young. Perhaps, after everything we have explored together, the most astonishing realization is not how vast the universe truly is. It is recognizing that you have never stood outside it. You have always been part of its story. And in the final part of our journey, before you close your eyes and allow sleep to carry you gently into stillness, we will look back one last time and discover that physics is not found only among distant stars. It quietly accompanies every breath, every melody, every ray of light, and every ordinary moment of everyday life. As our journey slowly approaches its final pages, perhaps you are beginning to realize that the greatest wonder is not how many galaxies we have crossed, how many stories of black holes we have heard, or how many mysteries of the fundamental particles we have explored. The greatest wonder is that, after all those remarkable voyages, we have quietly returned to where we began, back to this small room, back to the pillow gently supporting your head, back to the slow rhythm of your breathing, back to yourself. And then, perhaps you suddenly realize, something unexpected. There has never truly been a boundary between everyday life and the universe. They have always been one. Throughout this journey, we have looked up at the night sky many times. We have watched galaxies turning slowly through the vastness of space, followed light that traveled for millions of years before reaching Earth, stood before black holes, where space-time is curved so profoundly that even light cannot escape beyond the event horizon. We have listened to stories of atoms, of plasma, of the Higgs field, of antimatter, of tiny particles that no human eye can ever directly see. But now, gently bring your attention back to the room where you are resting. Air quietly flows into your lungs. Oxygen molecules diffuse across the tiny air sacs within them and bind to the hemoglobin in your blood. Sodium and potassium ions move across the membranes of your nerve cells, creating delicate electrical impulses that allow your brain to hear every word of this story. The soft light from your bedside lamp reflects from the ceiling, passes through your cornea, lens, and retina, before becoming patterns of neural activity within your mind. Every one of these phenomena is physics, not the distant physics of laboratories, but the physics of life itself. Perhaps that is the most beautiful lesson science has given us. The same laws governing the motion of planets are present in every step you take. The same principles describing light from distant galaxies also explain how you see the face of someone you love. The vibrations that become music are the very same vibrations carrying this voice to your ears. There are not two separate worlds. There is no physics of the universe and physics of human beings. There is only one nature, expressing itself in countless different forms. Perhaps that is why Albert Einstein once said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and all science." Many people believe that science somehow diminishes the beauty of the world. Yet the more I learn, the more deeply I feel the opposite. Knowing that a rainbow is created through the refraction and dispersion of light does not make it any less brilliant. Knowing that stars shine because of nuclear fusion does not make the night sky any less mysterious. Knowing that your own body is built from atoms forged inside ancient stars does not make life seem ordinary. Quite the opposite. Every new understanding feels like another doorway opening onto an even deeper wonder. Carl Gustav Jung devoted his life to exploring the inner world of the human mind. He did not study black holes. He did not build particle accelerators. He did not search for the Higgs boson. And yet, his journey, and the journey of physicists, seem to meet at one beautiful point: humility. Jung once wrote in Memories, Dreams, Reflections, "Who looks outside, dreams. Who looks inside, awakes." Perhaps over these quiet nights, we have done both. We dreamed of galaxies, then awakened to our own souls. We gazed into the vastness of space, then discovered that within every human being, there is also a universe waiting to be explored. Not because the mind obeys the laws of astronomy, but because both journeys demand patience, courage, and the willingness to accept that there will always be more to learn. Carl Sagan once wrote in Cosmos, "We are a way for the cosmos to know itself." Perhaps that is the one sentence I would most like to carry with me after closing the imaginary book of tonight's journey. Pause for a moment and consider it. The atoms within your body were forged inside generations of stars that completed their lives long before Earth itself was born. The calcium in your bones, the iron in your blood, the carbon in every cell, each carries the history of the universe. You are not merely living within the universe is also living within you, through your eyes. It looks once more upon the very stars that gave it birth. Through your questions, it continues its own journey of understanding itself. Perhaps that is one of the most beautiful ideas humanity has ever discovered. Richard Feynman once said, "I think nature's imagination is so much greater than man's. She's never going to let us relax." Indeed, the more we learn about physics, the more we realize that nature is richer than anything we could have predicted. Every answer leads to new questions. Every mystery we solve reveals another one lying even deeper. Yet perhaps that is not discouraging. Quite the opposite. It leaves room for wonder. There are still skies waiting to be explored, still stories waiting to be told, still laws of nature that future generations will one day uncover. The night has now grown very late. Perhaps your eyelids are becoming heavier. Your breathing has become slower and steadier. Your thoughts are settling like the surface of a quiet lake after the wind has passed. Somewhere beyond your window, Earth continues turning upon its axis at a speed you never feel. It continues its journey around the Sunday. The Sun continues orbiting the center of the Milky Way, and our galaxy itself continues its voyage through the vast universe. You do not need to do anything. You do not need to remain awake to watch over it. The universe continues quietly unfolding, just as your heart continues beating while you sleep, just as each of your cells quietly repairs itself throughout the night, just as dreams arrive gently without ever needing to be summoned. Perhaps that is also a very gentle reminder. You do not need to control everything. You do not need to answer every question before closing your eyes. Nature has never been in a hurry, and neither do you need to be. Tonight, let the things you do not yet understand remain like distant stars. Let the unanswered questions become part of the beauty, and allow yourself to rest. For tomorrow, the light will return. The laws of physics will once again quietly support every step of life. The atoms within your body will continue their work with astonishing precision, and the universe, just as it has for nearly 14 billion years, will continue telling its endless story. Thank you for spending these peaceful nights with me, traveling from the smallest particles to the grandest galaxies, from the first light of the stars to the deepest reflections of the human soul. If, somewhere within these stories, you found a little peace, a little curiosity, or simply a quiet moment to let your mind rest after a long day, then perhaps our time together has truly meant something. Now, take one slow, gentle breath in, and quietly breathe out. Allow your shoulders to soften. Let your final thoughts dissolve like the night's mist, and let the wonders of the universe continue their silent work while you drift into a deep, peaceful, and gentle sleep. Sleep well. Good night.